Today we're going to talk about the limit of a function. When we have a limit of a function, we write the following. The limit as x approaches some value a of f of x equals L. In words, this becomes the following. The limit of f of x as x approaches a is L. We could also write this as f of x approaches L as your x value approaches a. So let's do an example. Let's compute the limit as x approaches 1 of our function, we'll call this function x minus 1 over x squared minus 1. Well, what we can do is we can pick some values of x and plug it into our function and see what happens as x gets closer to 1. So let's create a table. We'll have a column for our x value and a column for our f of x. So if x were 0.5, our f of x would be 0.667, and actually going on forever. If x were 0.9, our f of x is 0.526. If x were 0.99, our f of x is 0.5025. If x is 0.999, our f of x is 0.50025. And if our x was 0.9999, our f of x is going to be 0.500025. So you might notice a pattern. As our x value is going towards 1, our f of x value is going towards another number. And we'll just confirm this and we'll check out when x is a little bit greater than 1. So let's start from the other way. For our x value is 1.5. What's the f of x value? Well, in that case, it's 0.4. When x is 1.1, we have it's 0.476. When it's 1.01, it's 0.4975. When it's 1.001, it's 0.49975. And as you see, it is getting closer to 1. So therefore, we can conclude that as our x value gets closer and closer to 1, the limit as x goes to 1 of x minus 1 over x squared minus 1 is equal to, not 1, it's equal to 0.5. And if we were to actually graph this function, y equals x minus 1 over x squared minus 1, what we get is the following graph. It looks something like this, where we have a hole right here when x is 1, but the value of that hole is at 0.5. So even though there's a hole, so the function does not exist at that point, it's still the limit. That function goes all the way towards it. Everything points towards it. It just doesn't include that point. So the limit is just saying, where do all the indications say the function is going towards? So if we're to look at a graph, we might say that if we have some graph that looks like this, if right here, that's our a of our function f of x, the limit as the function approaches, or as x approaches a, so we just look and we see as x gets closer to a, what is the value of the function, and that limit is whatever this point is. But sometimes we're concerned only about what happens as we approach a from a certain side, from either the left side or from the right side. When we want to write the limit as x approaches a from just one side, we write it as the following. The limit of f of x as x approaches a, and if we're going from the left side, we write a negative sign. Then we say this equals L. In words we write the limit of f of x as x approaches a from the right, or excuse me, from the left, is L. Now, similarly, you could write the right-hand limit, and the right-hand limit would just be written instead of the limit of f of x as x approaches a. From the right side, we just use a plus instead of a minus, but it means the limit of f of x as x approaches a from the right side is L. So we have the limit where it approaches from the left side, and the limit where it approaches from the right side. And so now we put all this together, all the different limits we've learned, and we have the following. We have given the limit as x approaches a of f of x equals L. We have this is true if and only if we have the following. The limit as x approaches a from the left-hand side of f of x equals L, and the limit as x approaches a from the right-hand side of f of x equals L. So what we have is we have just the limit of f of x as x approaches a equals some value L. That is true only if we have both the left-hand limit and the right-hand limit equaling the same thing. Alright, let's do an example. Say we have some function that looks like this, and it does something like that, and then we have another gap right here, but it goes right there. So let's put this at 1, 2, 3, and let's have 1, 2, and -1, -2. So this is our function f of x. Let's determine what the limit of f of x is when x approaches 1 from the left side, the limit of f of x as x approaches 1 from the right side, and just give myself a little bit more room, and the limit of f of x as x approaches just 1. What is this? Well, if we look at this, and as x approaches 1 from the left side, this is the value 1, what does the function look like as we approach 1? Well, if we're approaching 1 from the left side, it goes right here to the value of 2. So we have our answer for this first one is 2. But what about as it approaches 1 from the right side? Well, from the right side, we're over here. So we're approaching 1 from the right, and it goes down to -2. Okay. So now we said, what's the limit as x approaches 1? Well, the limit only equals a number if and only if these two limits are equal, but these two limits are different. Since they're different, we can say that the limit does not exist. Now let's compute the limit as x approaches 3. So we'll do three things. We'll find the limit of f of x as x approaches 3 from the left side, the limit of f of x as x approaches 3 from the right side, and the limit of f of x as x approaches 3. Well, as x approaches 3 from the left side, we're going, and we come right here. So that would be 2. As x approaches 3 from the right side, we're coming up down here, and we hit, and that would also be, excuse me, not 2, 1. It would be 1, and it's also 1 right here. And finally, since we have the left and right hand limits are both equal to 1, the limit as x approaches 3 is just 1. But note, what is f of 3? The value at 3 is actually 0. So the actual value of f of 3 equals 0 doesn't necessarily have to equal the limit. Now sometimes the limit of a function doesn't equal an actual value. An example of that might look like if our function does something like this, goes all the way up to infinity, and from the right side it also goes all the way up to infinity. So if it goes up to infinity, we have the following. We write it as the limit as x approaches some value a of f of x is equal to infinity. Similarly, it might go down to negative infinity, and we would write the limit as x approaches a of f of x is negative infinity. So we might even have something like this. We might have a graph that does this, and it goes all the way up to infinity, and it doesn't actually quite touch this line. It just goes arbitrarily close and gets very large. So this was the limit as x approaches some value a from the left side of their function f of x, and that's going to be infinity. So this right here is the point a, and this is our function f of x. We might also have, say, go down to negative infinity, in which case it might look like this. So that's our point A, and this is f of x, and so this is the limit as x goes to a. Oops, I've been writing the wrong sign. F of a goes to a from the left side of f of x equals, in this case, negative infinity. Now you may recall that these points from algebra, these values, are actually what we call vertical asymptotes of functions. So we have a definition that says the vertical line x equals a is what we call a vertical asymptote of the line y equals f of x if at least one of the following is true. And what we'll have is we have the limit as x approaches a from the left side of f of x is infinity. The limit as x approaches a from the right side of f of x is infinity, or the limit as x approaches a of f of x is infinity, or the limit as x approaches a from the right side of f of x is negative infinity, or the limit as x approaches a from the left side of f of x is negative infinity, or the limit as x approaches a of f of x is negative infinity. So if any of these cases happen, then we have what we call a vertical asymptote. Now that we know what limits are, we're going to calculate limits, and we're going to use the limit laws to do this. So first we're going to suppose that c is constant, and we'll also suppose that the limits exist for the following: the limit as x approaches a of f of x, and the limit as x approaches a of g of x. So if these two limits exist, then we're going to have the following. We have first 1, the limit as x approaches a of the quantity f of x plus g of x is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So this is the sum law, where we take the limit of the sum of two functions is the sum of each of their limits. Similarly, we have the difference law, which says that if we're taking the limit as x approaches a of the quantity f of x minus g of x, that's equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. The next thing, 3, we have if we're dealing with a constant multiple. So the limit as x approaches a of some constant c times our function f of x, this is just equal to the constant times the limit as x approaches a of f of x. So if we have some constant, all we need to do is just multiply that constant by the limit of the function. Now, we have two more. So number 4, this is going to be the product. So if we have the limit as x approaches a of the product of two functions, f of x times g of x, this is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. And finally, we have the fifth law that we're going to go over right now, and this is going to be the quotient law. And this says that the limit as x approaches a of the quantity f of x over g of x is equal to the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. But this is provided that the limit as x approaches a of g of x is not equal to 0, because then we'd be dividing by 0. So this is if the limit as x approaches a of g of x is not 0. So for example, if I told you that the limit as x approaches 3 of f of x is 2, and the limit as x approaches 3 of g of x is negative 4, then if we were to calculate the limit as x approaches 3 of f of x plus 2 g of x, we can use the law of limits. So what we have here, first of all, is addition. So we could separate this into the limit as x approaches 3 of f of x plus the limit as x approaches 3 of 2 g of x. But notice right here, 2 is a constant. And so by using the constant, we can pull the constant in front. And so this we get is the limit as x approaches 3 of f of x plus 2 times the limit as x approaches 3 of g of x. And we know that the limit as x approaches 3 of f of x is going to be 2 from right up here. And the limit as x approaches, let me just make a little bit smaller. So we have this first limit is 2 plus 2 times negative 4. So we have this is equal to negative 6. So there are a couple more limit laws that we have. So number 6, this is the limit as x approaches a of the quantity f of x raised to the power n is going to be the same as the limit as x approaches a of f of x all raised to the power n. And this is the case where n is some positive integer. We also have the limit as x approaches a of just some constant c. Well, that's just going to be c. Because it's constant, it never changes. It's always going to be c. Number 8, we have the limit as x approaches a of x is equal to, well, this is pretty intuitive as well. Well, if x approaches a, then the limit of x should just be a, since x is going towards a. We also have, for 9, the limit as x approaches a of x to the power n is equal to a to the power n. And this is just for some positive integer n. Number 10, we have the limit as x approaches a of the nth root of a, excuse me, the nth root of x. This should equal the nth root of a, where again a or n is a positive integer. And we're going to assume that a is also positive. And next, we have number 11. And this law says that the limit as x approaches a of the nth root of f of x is equal to the nth root of the limit as x approaches a of f of x. Okay. And again, if n is even, we're going to assume that what's in the radical is positive. So let's do an example. Let's calculate the limit as x goes to 5 of 2x squared minus 3x plus 4. Well, we have three things going on. We're adding and subtracting, so we can separate this into three limits. The limit as x goes to 5 of 2x squared minus the limit as x goes to 5 of 3x plus the limit as x goes to 5 of 4. Now, for this first one right here, we're multiplying by a constant, so we can pull that out. This becomes 2 times the limit as x goes to 5 of x squared minus, we also have a constant 3, so we can pull that out, 3 times the limit as x goes to 5 of x plus, and the limit of a constant, 4 is a constant, so this is just going to be 4. We already found that part. Now, what we have, the x squared, that can be rewritten as the following. So this is going to be 2 times the limit as x goes to 5 of x quantity squared minus 3, and then now the limit as x goes to 5 of x is just going to be 5. And then we have plus 4. And so the limit right here inside is going to be 5. So we write that now as 2 times 5 squared minus 15 plus 4. And we get this is equal to 39. Now, we have a property, and this says that if f is a polynomial or a rational function and the value a is in the domain of f, then we have the following. Then the limit as x goes to a of f of x is just simply f of a. Now, this relates to something we call continuous at the point A, but we'll talk about that later. Many times we can use this direct substitution and it will make life easy, but sometimes we cannot. So for example, if we're trying to find the limit as x approaches 1 of x squared minus 1 over x minus 1, what can we do? If we plugged 1 right into this, we would get 1 squared minus 1 over 1 minus 1, and so we'd be dividing by 0, and we cannot do that. So we know that 1 is not in the domain. But if we were to simplify this, we simplified the expression and we rewrote it as x squared minus 1. Instead, we wrote it as x minus 1 times x plus 1. When we divide it by x minus 1 and we divide it by x minus 1, we see that we cancel, and this is just x plus 1. So if we were to then plug that in, what we get is the following. We get the limit as x goes to 1 of x plus 1, and this is a polynomial, so we can straight substitute, and so this becomes 1 plus 1, which is 2. We also have another property, and this says that if f of x equals g of x when x is not equal to a, then regardless if it's not equal to a, we know that the limit as x goes to a of f of x equals the limit as x goes to a of g of x, provided that limit exists. So an example of what this might look like is if we have, say, two functions, and one function looks like this. This is our f of x. And then we have a second function that looks like this. So this is our point A and our g of x. And these two functions are the same everywhere except at the point A. At the point A, g of x has a value up here. But it doesn't really matter because their limits are both going to point down here. Now we have a theorem. And this theorem states that the limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the left side of f of x equals L, and that equals the limit as x approaches a from the right side of f of x. We have another theorem that states the following, that if f of x is less than or equal to g of x, when x is near a, and this except for when possibly it's equal to a, and the limits of f and g both exist as x approaches a, then we have the following. The limit as x approaches a of f of x is less than or equal to the limit as x approaches a of g of x. And this should be sort of intuitive. If one function is less than the other, then the limit of that function is less than or equal to the limit of that one. And the last theorem we're going to talk about is one that actually has a name, and this is called the squeeze theorem. And this says, given three functions, and if the functions f of x is less than or equal to g of x is less than or equal to h of x, when x is near a, except possibly at a, and if we have that the limit as x approaches a of f of x equals the limit as x approaches a of h of x equals some value L, then the limit as x approaches a of g of x is L. So what this is saying is that if we have three functions, f, g, and h, where f is less than g is less than h, and if the limit as x goes to a of f of x equals h of x, then that means that we're squeezing g of x, the limit, to be the same value. So let's do an example. Let's try and show that the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. Well, we cannot reuse the following. We cannot write it as the limit as x goes to 0 of x squared times the limit as x goes to 0 of sine of 1 over x, because this does not exist. So what we'll do is we now look at x squared times sine of 1 over x. Now we know that sine of 1 over x, sine of anything really, will vary between -1 and 1. And so therefore, we can bound this by just saying that negative x squared is less than or equal to x squared times sine of 1 over x is less than or equal to positive x squared. Because we know that sine of 1 over x varies between -1, that's where we get this, and +1. And so now applying the squeeze theorem, what we get is we're going to find the limit as x goes to 0 of negative x squared. Well, that right there, as it goes to 0, is just simply 0. And the limit as x goes to 0 of positive x squared is also 0. And so therefore, we know by the squeeze theorem that if we have something like this where it's all between, then we can conclude that the limit as x goes to 0 of x squared sine 1 over x is in fact 0. Today we're going to talk about the precise definition of a limit. And so we begin by saying let f be a function defined on some open interval that contains the number a, except possibly at a itself. Then we say that I'm going to change my font right here, that the limit of f of x as x approaches a is L, and we write the following. We write the limit as x approaches a of f of x equals L. So we have this if, let me move this up a little bit. So we have this if the following. If for every number we're going to call this number epsilon, so for every number epsilon that's greater than 0, there is, or there exists, a number delta greater than 0 such that we have the following. Such that if 0 is less than the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than not delta, but epsilon. So it's less than epsilon. So what we have is that if we have the distance between x and a, if that is less than delta, then we have that the distance between f and L is less than epsilon. Graphically, what this looks like would be the following. So if we have our graph, we have x and y, then we have some function like this. This would be our f of x. And if we had some arbitrary x point, excuse me, I meant a. So if we have some arbitrary value a, and it goes right here, and if that's what the limit would be, and that limit is L, then what this says is that if we're given some epsilon, so let's just say epsilon looks something like this. This has a length of epsilon, and then we also have another length, epsilon, going down. So this upper bound right here goes from the point L, and we add epsilon, so this is really L plus epsilon. And then this lower point right here is L minus epsilon. So we have a region. We start at L, and we basically say if we go just a little bit up or a little bit below, that's what epsilon says. So if there's an epsilon like that, what we can say is that there's going to exist some sort of delta such that the difference between your A value and your delta value, or excuse me, and your actual X value will be within that delta. So go ahead and extend this line from here. We extend it right there. We'll bring that down over here. Again, up here, we'll extend, and then we'll bring that down. So, as long as we're within this region for our X value, then this satisfies. So, what do I mean? First of all, I'll go ahead and label the delta. We have delta here, and then this point right here is going to be A plus delta, and then over here would be A minus delta. So, looking at this definition, and this says that as long as our X value is the difference between our X value and A is less than delta, so we're somewhere in this region. So if our X value is close enough over here, then our Y value will fall within this region. And that's what it means for something to be continuous. If your X value is close enough, then your Y value is going to be close enough. And that will happen as we get arbitrarily small. So let's do an example. Let's find a number delta such that if 0 is less than x minus 3 is less than delta, then we'll have that the absolute value of f of x minus 2 is less than 0.5. So we need to find what delta is. So let's go ahead and graph this, and I'm giving you the graph. So the graph will look something like this. And so we have the point where an x is 3. That would be over here. And the y value for that would be 2. So I'm getting all this by looking right over here, 3 and 2. And then our epsilon, how far we're varying in the y direction, is 0.5. And so we would have at 2.5 up there and 1.5 down here. And if I were to follow that over here and then all the way down, what I would get down here is the value 2.6, and then follow this all the way to here and down, I get the value 3.8. So notice that these are different lengths. The length between here and here, and the length between here and here. So the length between 2.6 and 3 is 0.4, and then the length between 3 and 3.8 is 0.8. So what would our delta be? What we need to do is find a delta that guarantees if we're within that width. So if we're in some region, then the y values will also be in that region. So what we want to do is we want to pick the smallest region, and that's what our delta would be. So we would say delta is equal to 0.4. In this section, we're going to talk about continuity. So we'll begin with definition. Definition: a function f is what we say continuous at a number a if the following: the limit as x approaches a of f of x equals f of a. So it's continuous if the limit is equal, the limit as x goes to a is equal to f at that point a. Notice that we're assuming three things. First of all, that f of a is in fact defined, meaning it's in the domain. Second, that the limit as x goes to a of f of x exists. And finally, we're assuming that the limit as x goes to a of f of x is equal to f of a. We also have, as another definition, if f is defined near a, we say f is discontinuous at the point a if f is not continuous at a, meaning right here that the limit as x goes to a of f of x does not in fact equal f of a. So if we have a graph that looks something like this, this is continuous at all these points except right here at this value. It's not continuous, so it's discontinuous right here. We might even have a function, say f of x is equal to x squared minus x minus 2 divided by x minus 2. Well, if x is equal to 2, we'd have 0 in the denominator, and that's not possible. So x cannot equal 2. Therefore, it's discontinuous at that point x equals 2. Now we have another definition, and this definition says that a function f is continuous from the right of a number a if we have the following: the limit as x approaches a from the right side of f of x is equal to f of a. And f is what we say with the next definition. F is continuous from the left of a number A if we have that the limit as x approaches A from the left side of f of x is equal to f of A. So graphically, what this might look like is if we have a graph like this, and we have something like that, and that's our point A. This is our function f of x. Well, if we look at f of x from the right side, it is equal to, f of x is equal to the right-hand limit. And so, therefore, this graph would be continuous from the right at this number A. Similarly, if we had a graph that looked like something to this effect, go up there and then below, we do that, then this would be continuous from the left of some number A. We have another definition, and this states that a function f is continuous on an interval if it is continuous at every number in the interval. Now we have a theorem and this theorem states that if f and g are continuous at the point A, and if the value c is a constant, then the following functions are also continuous at A. One, f plus g will also be continuous. 2, f minus g will be continuous. 3, the constant c times f is continuous. 4, we have the product f times g. And 5, we have the quotient f divided by g is also continuous. And this is if we assume that the denominator, g, evaluated at the point A, is not 0. Now we have another theorem. And this theorem states two things. A, any polynomial is continuous everywhere. that is continuous from negative infinity to infinity on the interval. Second part of the theorem states that any rational function is continuous wherever it is defined. That is, it is continuous on its domain. So let's take a look at an example. Find the limit as x approaches negative 2 of the quantity x cubed plus 2x squared minus 1 all over 5 minus 3x. Well, this is a rational function, and taking a look at this rational function, what's its domain? Well, the domain of this is all real numbers except when the denominator is 0, so except when x equals 5/3. And if we look here, we found this limit when x goes to negative 2. Well, negative 2 is in the domain. So now what we can do with this limit is that if we define the function f of x to be this whole x cubed plus 2x squared minus 1 divided by 5 minus 3x, and if we're trying to calculate the limit as x goes to negative 2 of x cubed plus 2x squared minus 1 over 5 minus 3x, this is just the same as the limit as x goes to negative 2 of f of x. But we know that negative 2 is not, or is in the domain, negative 2 is in the domain of this function f of x. Because the only thing that's not in the domain is 5/3. So therefore, we can write it as just simply f of negative 2. And what is f of negative 2? Well, we plug that in, and that would be negative 2 quantity cubed plus 2 times negative 2 squared minus 1 all over 5 minus 3 times negative 2. And simplifying this, what we get is negative 1 over 11. We next have a theorem that states the following. The following types of functions are continuous at every number in their domains. So first we have polynomials. Second, we have root functions, and this includes square roots, cube roots, and so forth. We also have rational functions and trigonometric functions. So, for example, on what interval would the function f of x equals negative 3x to the 4 plus 5x squared minus 18, when would this be continuous? Well, this is a polynomial, and so because it's a polynomial, it's defined everywhere, and so it's continuous everywhere by this previous theorem. So it is continuous on the interval, so continuous on the interval negative infinity to positive infinity. What about, do another example, and let's call this g of x, and let's do a rational function, so let's do 3x squared minus 7x plus 11 divided by x squared minus 9. Well, we want it to be, it'll be continuous anywhere in its domain. So what's the domain of this? Well, since we're dividing by something, we can't have the denominator equal 0. And so the domain is all numbers except when x is 3 or negative 3. So all values x such that x cannot equal plus or minus 3. And therefore, it would be continuous for every number except for positive or negative 3. So we would write that as negative infinity to negative 3, negative 3 to 3, and then 3 all the way on to infinity. This includes all numbers except for 3 and negative 3. And finally, we'll do one more example. And so here we have, let's see, we did fg, we'll call this function h of x. And so h of x is the square root of x plus 1 over x minus 1 minus x plus 1 over x squared plus 1. Well, what is the domain for this function? What we see here is we can break this down into 3 smaller functions by our previous theorem. If we define, let's say, capital F of x to be square root of x, capital G of x to be x plus 1 over x minus 1, capital H of x is x plus 1 divided by x squared plus 1. Then we just need to figure out what are the domains for each of these. Well, the domain for f of x, capital F of x, is all real numbers greater than or equal to 0. We cannot have a negative in the square root, so this is 0 to infinity. The domain for the second one, it's all real numbers except for negative 1. So really, this is negative infinity, or positive 1. So negative infinity to 1, union 1 to infinity. And this last one, it includes, well, we would never be divided by 0, so our domain is all real numbers, negative infinity to infinity. So we have these 3, combining them, what we end up with is we have to make sure that it's not negative, so we got to include this, but we also know that it cannot include the point 1. So we get for our domain, and therefore the interval where it's continuous, from 0 to 1, but not including 1, and then 1 onto infinity. And that would be our answer. We got another theorem, and this theorem states that if f is continuous at the point b, and the limit as x approaches a of g of x equals b, then we have the limit as x approaches a of f of g of x, now this is the composition of functions, is equal to f of b. Okay? So what does this mean? Well, in other words, we get that the limit as x approaches a of f of g of x, this is equal to f of the limit as x approaches a of g of x. We have another theorem, and this theorem states that if g is continuous at the point a, and our function f is also continuous at the point g of a, then the composite function given by f of g of x equals f of g of x. This is continuous at a. And finally, we have one last theorem left to go. So this theorem is a big theorem and it has a name. And this is called the intermediate value theorem. And what this intermediate value theorem says is, suppose f is continuous on the closed interval a to b, and let capital N be any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c in the interval a to b such that f of c equals n. So I'm going to actually draw this out for you so that it might be a little bit more clear. So we're going to have our axis, so we have x, we have y, we have our function f of x. So if we have a point A right here, and then over here we have the point B, so we bring this up, we get f of A, we have f of B right here, and then we're assuming that n, capital N, is between f of A and f of B, so let's call it n right there. What this says is that there exists some point C where C falls somewhere between A and B such that f at that value is equal to C. Well, looking right here, right there, that's one possible value for C, and we'll call that C1 because we have another point that could have been C, or even another point that could have been C. But as long as there's one. The intermediate value theorem is used often when you're trying to find the root, or show at least that a root of an equation exists. So if we have some function, f of x is equal to 4x cubed minus 6x squared plus 3x minus 2 equals 0, and I ask you to show that there exists a root, or in other words a 0, between 1 and 2, what we would first do is calculate what is f of 1. Well, f of 1, plugging this in, we get 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2. So 4 times 1 cubed minus 6 times 1 squared plus 3 times 1 minus 2. That's a minus. And we end up with this is negative 1. And we all know negative 1 to be less than 0. F of 2, well, this is 4 times 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2, and this is 12, which is greater than 0. And so that capital N that we dealt with, we know that we'll call that capital N the point 0. So what we have is something like this. Something like this. So this is our x-axis, and this is the y-axis. And we know when x is 1, we're negative, we're somewhere down here below the axis. But then when x is 2, we're above the axis. And this is a polynomial function, so we know it's continuous. So in order to get from below the axis to above the axis, you have to cross somewhere between 1 and 2. To get from below to above, you have to cross the axis. Now, I'm not saying exactly where it is. All this says is that it crosses the axis somewhere between negative 1 and 2. Who knows? It might cross many times. But we're just trying to show that there exists at least one crossing in that interval. Now we're going to shift gears a little bit and talk about velocities. So we're going to say that f of x is the position of an object. Now when you think of velocities, you might think about moving in a car, and the speed limit is given by miles per hour, or distance over time. So we would say that the average velocity is equal to the displacement over time, which in this case would be f of a plus h minus f of a all over h. But as you know, if you're driving in the car, your speed or your velocity changes constantly. And so if you want to find the instantaneous velocity, we're going to say that the instantaneous velocity is given by v of a, and that's going to be as time gets smaller and smaller. So not averaged over your whole time span, but almost instantly. So as your change of time becomes very, very small, or the limit as that gets closer to 0. So we write it the limit as h goes to 0 of f of a plus h minus f of a all over h. And this is the formula for the instantaneous velocity. So let's do an example. Say a ball is dropped from a height of 450 meters above the ground. What's the velocity after 5 seconds? Well, in order to find that, we need to first figure out what's the position vector, or the position function. So that is a standard equation. This is going to be, we call it S, or f of x, or f of t rather, for time. And this is 4.9 times t squared. So this right here is something that we will be given. Now, to find the velocity after 5 seconds, we need to figure out the velocity v of t is going to be the limit as h goes to 0 of our f of t plus h minus f of t divided by h. So this is the limit as h goes to 0 of f of t plus h. So again, we'll do that right down here. So this is f of t plus h, which is going to be 4.9 times the input squared. So 4.9 times t plus h, quantity squared, which is equal to 4.9 times t squared plus 2 th plus h squared. So plugging that in, we get 4.9 times the quantity t squared plus 2th plus h squared, and then minus f of t, which is 4.9 times t squared all over h. So this becomes the limit as h goes to 0, and everything has 4.9, so I can factor out 4.9 from the numerator, and so we get t squared plus 2th plus h squared minus, since we factored out the 4.9, we're just left t squared over here all over h, and now our t squareds cancel, and so moving this up, we get the limit as h goes to 0, and notice that each term has an h in it. So we can factor out the h. So we get h times the quantity 2t plus h all over h, and our h's now cancel. And so this is the limit as h goes to 0 of 2t plus h. And now since we don't have an h in the denominator, because we had an h in the denominator over here, we couldn't evaluate it when h went to 0, because we'd be dividing by 0. But we don't have that problem anymore. So this is just 2t plus 0, or just 2t. Excuse me, I forgot we had the 4.9 this whole time. So this is 4.9 times all this, 4.9 times all that, 4.9 times all that, and 4.9 times all of that, which means this is going to be 9.8 times t. So this is, we get v of t is 9.8 times t. And if we're trying to find the velocity after the ball dropping for 5 seconds, this is 9.8 times 5. Plugging this in, we get that this is going to be 49, and we're dealing in meters per second. And if I were to ask, what is the time when the ball hits the ground? Well, we would need to figure out time. So recall, the position vector is going to be f of t is equal to 4.9 t squared. That's a t, not an x. So f of t is 4.9 t squared. We wanted the position to be on the ground, so it will have traveled 450 meters. And so this is just a problem that we can solve. And so we solve this, we get t squared is 450 over 4.9, which means that t is approximately 9.6 seconds by taking the square root of both of these. So it hits the ground after 9.6 seconds. Well, what's the speed when it hits the ground? What's its velocity? Well, the velocity when it hits the ground, we just use this formula that we found. V of t is 9.8 times our time, 9.6. And so we get that this is about 98 meters per second. So if you drop the ball at 450 meters above the ground and you let it fall, when it hits the ground, it'll be traveling and hitting the ground. Excuse me, this is 94 meters per second. It'll hit the ground at 94 meters per second. Now we have another definition. And we say that the derivative of a function f at a number a So a derivative of a function f at a number a, and we're going to say this is going to be denoted by, when we write derivatives, what we write is going to use this function f of a, but then we write this prime. We call this a prime. It looks like an apostrophe, but it's a prime, f of a. And we're going to give the equation for f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a divided by h. And this is going to be provided that the limit exists. So if the limit exists. So this is the derivative of a function f at a number a. Now, an equivalent way of writing this, from just like how earlier there were two different ways of writing it, we can rewrite the derivative as the following. We can rewrite, so this is a new thing, f prime of a is equal to the limit as x goes to a of f of x minus f of a divided by x minus a. All right, so let's do an example. Find the derivative of the function f of x is equal to x squared minus 8x plus 9 at the number a. So what we have to do is we want to find f prime of a, and by definition, that is the limit as h goes to 0 of f of a plus h minus f of a all over h. So let's figure out what's f of a plus h. So if f of x is x squared minus 8x plus 9, f of a plus h is going to be a plus h squared minus 8 times a plus h plus 9, which is a squared plus 2ah plus h squared minus 8a minus 8h plus 9. Okay, so we have, this is the limit, h goes to 0, of a squared plus 2ah plus h squared minus 8a minus 8h minus 9, and we're subtracting f of a, so this would be minus x squared minus a negative, so this is going to be plus, or excuse me, not x, it should be a squared, plus 8a minus 9, and this is going to be all over h. So simplifying, we get, let's see, we have our, oops, this should be a plus 9, not a minus 9. Okay, so now we have our a squared and our minus a squared cancels, and then our plus 9 and our minus 9 cancels. So we get the limit, oops, as h goes to 0 of 2ah plus h squared, and then our negative 8a and our positive 8a also cancel. So minus 8h, and that's it. All divided by h. Now if you notice, everything has an h in it, so we can cancel out our h's. That h cancels, and the h squared just become power of 1, and then we divide the h in the denominator. So this is now the limit as h goes to 0 of 2a plus h minus 8, and we can now evaluate this limit when h is 0. So this is 2a plus 0 minus 8, or 2a minus 8. So this is equal to our derivative evaluated at the point A. So now we have another way of expressing the tangent line, and we say that the tangent line to the function y is equal to f of x at the point a comma f of a is the line through the point a comma f of a whose slope is equal to the derivative f prime of a. So this is derivative of f at a. Now we have something called the instantaneous rate of change. And this instantaneous rate of change is equal to the limit as delta x goes to 0 of delta y over delta x. So rate of change, the change of y over change in x, just like our slopes. So this is one way of writing it, or we could rewrite it as the limit as, say, your point x2 goes to your point x1 of f of x2 minus f of x1 over x2 minus x1. And this is if something we have, like delta x is given 2 points, and that's really our x2 minus our x1, and then our delta y is y2 minus y1. So we had some sort of curve like this, and we had x1, x2, that would be f of x1, f of x2, or we can just say that this length is delta x, that length is delta y. And so finally, we have one last thing in this section, and this is the derivative f prime at a is the instantaneous rate of change of y equals f of x with respect to x when x is equal to a. In this section, we'll talk about derivatives and rates of change. But before we start, we'll talk about something called a tangent. A tangent line is some sort of line that touches a curve. But it doesn't cross the curve, and so we should assume that this tangent line will have the same direction as the curve and at that point of right at that point of contact. So for example, if we have a curve that looks something like this, the tangent right here at that point should be a line that touches right here and has that same direction. If we had the tangent point down here is going downward, and so the tangent line would look something like this. So if we were to have some curve that looks something like this, we have x and our y-axis, and then we have some point right here. We call this point a, and if this is our function f of x, this value would be f of a. Now if we picked some arbitrary value x, let's just say some x values over here, and then we had, this would be our f evaluated at that x value, we have 2 points. Now if we're trying to find the tangent line right here, we want the tangent line to go through here and have something like that. Okay. So right there is we have a straight line. Well, if we want to find the equation of a line, what we need to figure out what's the slope. So now we know the equation of a slope is m is the change in height over, so the change in the y value over the change in the x value. The change in the y value is f of x minus f of a, and the change in the x value is x minus a. That's our slope. Just rise over run. So now we'll have our first definition, and this definition will say the following. The tangent line to the curve y equals f of x at the point a comma f of a is the line through our point with slope m equals, now taking a look at this, we pick some arbitrary x, but this is somewhat accurate, but if our point were way out here, maybe let's say over here, that's not a really good representation of what the slope looks like. So what we want is we want as close as possible to pick our x value to get a more accurate slope. So if we want it to be as close as possible, we take the limit as x approaches a, so we want x to be very, very close to a. So we're taking x as it gets closer and closer to a. So we want this limit of f of x minus f of a divided by x minus a, provided the limit exists. So that's our definition of a tangent line. Sometimes we actually will call a tangent line, or rather the slope of a tangent line, the slope of the curve. So let's do an example. Find the equation of the tangent line to the curve y equals x squared plus 3 at the point 1, 1. So what we want to do is find the equation of a line. When we find the equation of the line, one of the forms we can use would be y minus y1 equals m times the quantity x minus x1. This is called the point slope formula because we have our point x1, y1, and we have our slope m. Well, we already know our point, that's 1, 1. So substituting, we get y minus 1 equals m times x minus 1. So all we need to do is figure out what m is, and we'll be done. So let's go ahead and do that. So remember, the definition for the slope is going to be given. M is the limit as x approaches our a value. And remember, this 1, 1, that's really our a comma f of a. So this is the limit as x approaches 1, really the x value of the point we're doing, of the quantity f of x minus f of 1 divided by x minus 1. Well, let's substitute. What's f of x? F of x, well, that's right here. So that's going to be, so we take the limit as x approaches 1 of x squared plus 3 minus, I'll put these in parentheses, minus, what's f of 1? Well, plugging in 1 for x, we get 1 squared plus 3 all over x minus 1. If I take out the parentheses, we get, this is x squared plus 3 minus 1, because 1 squared is just 1, minus 3 all over x minus 1. And our 3 and minus 3 cancel. And so we're left with the limit as x approaches 1 of x squared minus 1 over x minus 1. Now, we can't just plug this right into the limit, because if we plugged in 1, we'd be dividing by 0 right here. But you might have noticed that x squared minus 1 can be reduced. So we now can write this as limit as x minus 1. X squared minus 1 becomes x minus 1 times x plus 1 divided by x minus 1, and now we can cancel. So this is the limit as x approaches 1 of just the quantity x plus 1. And now we can plug in 1 in for x, and so we're left with, this is just going to be 1 plus 1, which is 2. So our slope is 2. Plugging it back into the formula, so we get y minus 1 is equal to 2 times the quantity x minus 1. And so this is our answer. Now this is a perfectly acceptable answer for me, but if you turn it in on the homework, depending on the format, it may not be acceptable. But if you turn it in for quiz or test, this is fine. But I'm going to simplify it just as an exercise. So this is going to be y minus 1 equals 2x minus 2. I just distributed, and now I add 1 to both sides, and so we get y is equal to 2x minus 1. Both of these represent the same line. It's just written in different forms. Now sometimes it might be easier to write, given our curve, something like this, where we had our point, let's say a, and so that would be our f of a, that would be our function. Instead of having some point x out here, what we could do, so I'm going to erase that x, so instead of having a point x like that, what we can write is, let's just say this distance right here would be h. So we say we're just h distance apart from a, which means that the value of that point would be a plus h, and then the y value would be f of a plus h. So now we're just dealing with how far we are away from a. So instead of some value x, we're just saying that a plus h, or we're just going h away from a. So using this notion, we can rewrite the equation for the slope of a line. This is going to be m is equal to the limit as, well, what we were taking before is the limit as the value x was going towards a. So really what that's saying is that the limit of this gap is getting smaller and smaller. So we can say this is the limit as h approaches 0 of, well, the limit is just the slope, so the change in your y value, the rise. So this is going to be f of a plus h minus f of a over the run. How far do we go in the x direction? Well, we're just going h. So this is going to be divided by h. And that's the equation for your slope. So this is another way of rewriting what we learned on the other slide. So let's do an example. Find the equation of the tangent line to the equation y is equal to 3 over x at the point 3, 1. Okay, so this 3 over x, that's our f of x. So let's begin. We wanted to find the equation of a line, so that's going to be y minus 1 is equal to m times x minus 3. And now we need to find our slope, m. So that's going to be m is equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h. Now notice we can't plug in 0 for h right now because we'd be dividing by 0, which is not something we can do. So we will start simplifying. So this is limit as h goes to 0, f of a plus h. Well, what happens if you plug in a plus h into this function? that's really just your x values. So this becomes 3 over a plus h minus f of a is 3 over a. So just take a little note right here. If your f of x is 3 over x, f of a is 3 over a, all we're doing is just simply taking whatever's the input and writing it wherever their x was. So in our case we had, this is f of a plus h. This becomes 3 over a plus h. The same way you might treat something like, if this is just a box, this is just 3 over that box. Whatever goes inside gets replaced. And now continuing back here, this is all divided by h. Well, what we have is we're subtracting two fractions, and when we work with fractions, we want to find a common denominator. So this becomes the limit as h goes to 0 of 3 over a plus h times a over a minus 3 over a times a plus h over a plus h all over h, which simplifies to the limit as h goes to 0 of 3a minus 3a minus 3h all over a times a plus h all over h. So what I did there was I just distributed this right there. So we get 3a minus 3a, that cancels, and so we end up with the limit as h goes to 0 of negative 3h divided by a times a plus h, and this is all over h, and so if we're dividing by h, let me just pull this up again, this is all going to be over h. And now remember that our a value was 3. That was the x value of the point. So plugging that in, let me go ahead and just give myself a little bit more space again. So plugging that in, we get the limit as h goes to 0 of negative 3h divided by 3 times 3 plus h all over h. So if we're dividing by h, it's the same as multiplying by 1 over h. So we have something like that. And now our h's will cancel. Those h's cancel. So we take the limit as h goes to 0 of, and then also our 3's cancel. So this is just negative 1 over 3 plus h. And now we take the limit as h goes to 0. This becomes negative 1 over, negative 1 over 3 plus 0, or just negative 1/3. So that's our slope. Going back up here, filling it in, we get our equation is y minus 1 is equal to negative 1/3 x minus 3. And that's our answer. Previously we talked about the derivative of a function at a point. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. But now in this section, instead of just talking about the derivative at a single point, we'll think of the derivative as an equation. And so we will have, instead of at a single point, at some arbitrary value x, or some input value of x, f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x, f of x all over h. So this is the formula for the derivative at any point x, or as a function of x, rather. Now let's say we have the graph of some function, and the graph might look like this. So this is x, y, and this is our function, f of x. If we wanted to graph the derivative of this function, what would that look like? So we wanted to find f prime of x. Well, remember, the derivative is really the slope of the line at each point. So let's examine the slopes. Well, we have a positive slope going up here, then it becomes negative, then positive and negative and positive and negative. Well, when it goes from positive to negative, right here at this peak, it is zero slope. And same thing down here. If you're going from a negative to positive, you pass zero. So right here is the zero slope, 0, and 0. So we can fill in all those gaps. So this point right here gets translated down to here, 0. This point is also 0. This point becomes 0. This point is also 0. And then here, that's also 0. So now we have 3 points for our derivative. Now looking back over here, we have a positive slope. Positive slope means it's going to be above the axis. Positive means we're above, so we're some value above the axis. Now looking over here, it's a negative slope, so we would be below the axis. So we're going to come down negative, and then we go back up to 0. And if you look right here, this slope right here is a negative, but it's not too steep. Over here, it's a very steep, and then it's not too steep. So if it's not too steep, it's a smaller number. So not too steep right here means negative, but just a small negative. So something like this. Very steep over here is negative and a large negative. And then over here we have a negative, but it's not that much of a negative, so it's smaller. So we might have it looking something like that. And same thing, as we go over here, we're going to be increasing, so it's a positive slope. The slope is not too big right here, it's a small positive. It's a bigger positive, and then it goes back to a small positive. So let me just draw that in. So it's small positive, a bigger positive, and then a smaller positive. So small positive, big positive, and a small positive. And our graph might look something like that. And then same thing in this section right here. Small positive, it becomes steeper and then not as steep. So, or excuse me, all negative. So negative, back up. And then over here we have positive. So it goes positive and back down. And then finally, this is all going to be negative. And so we're going to be negative. And this is sort of a sketch of what the derivative might look like. Really, what we do is we first look at what are the zeros, and that's these peaks. And we can tell all those points. The zeros tell us when it crosses the axis. And then the slope tells you if it's positive, then you're above the axis. If it's a negative slope, then you're below the axis. Now let's do an example. If we're given f of x is equal to x cubed minus x, let's find the formula for the derivative. Well, f prime of x is equal to the limit as h goes to 0 of the following: f of x plus h minus f of x all over h. So this is the limit as h goes to 0 of, well, we need to figure out what's f of x plus h. Well, that would be the following. This would be x plus h quantity cubed minus x plus h, all minus x cubed minus x all over h. Now notice we have x plus h quantity cubed. So I'm already going to tell you what that is. You can calculate it yourself, but x plus h quantity cubed is x cubed plus 3x squared h plus 3x h squared plus h cubed. And you can find that on your own just by multiplying out. So we have the limit as h goes to 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed, and then a minus and negative means we have a plus x. This is all going to be divided by h, and so we can cancel some things. Our x cubes cancel, and then our x's will also cancel. So we're left with the limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed minus h, all divided by h. Now notice everything has an h, so we can start canceling our h's. This h cancels, this h squared becomes h just to the power 1, this h cubed becomes h squared, and this h cancels, and when we divide h divided by h, you're just left with 1. And then we cancel out our denominator. So this becomes the limit as h goes to 0 of 3x squared plus 3x h to the power 1 plus h squared minus 1. We can evaluate this now, and so we get this is equal to 3x squared plus 3x times 0, because we're evaluating when h is 0, plus 0 squared minus 1, or 3x squared minus 1. And that's our answer. So if we're given the function f of x is equal to x cubed minus x, the derivative f prime of x is 3x squared minus 1. Okay. And so if we're to graph this, what this looks like is the following. The cubic function, x cubed minus x, looks something like this. The graph of the derivative, f prime of x, is a parabola. So if we're to graph that below, we would see, well, right here, it's a maximum. It has a slope of 0. So that's where it crosses. And we also have a minimum, another slope of 0. It's right here. And then we see over here, we have a positive slope and another positive slope. So we're going to be above the axis, like this, and like this. And then we see in the middle, we have a negative slope, so we'll be below the axis. We start off at a small negative, it becomes steeper, and then become a smaller negative. So small negative, steeper means it's a larger number, and then back to a smaller number, and that's exactly what this is. This is a parabola. And so you can see the difference between f of x and f prime of x. Let's do another example. If we have our function f of x is the square root of x, what's the derivative of the function? Well, to find that, we get f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So we get the limit as h goes to 0 of the square root of x plus h minus the square root of x, all divided by h. Well, what can we do in a situation like this? When you see the subtracting two different square roots, the first thing you want to think about is rationalizing the numerator. And what I mean by that is by multiplying by the conjugate. So we multiply by almost the same thing, but instead of it being minusing, we add the two. So we get square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. So what this does is this simplifies the numerator. We have two things multiplied by each other. So for example, if we had a minus b times a plus b, that's the difference of squares, and this becomes a squared minus b squared. Well, if each of these are the square root, what we would have is the square root of x plus h squared. So the square root of x plus h, quantity squared, is just going to be x plus h. And then minus the square root of x, quantity squared, just is going to be x. And then our denominator would be h times this whole thing on the right, square root of x plus h plus square root of x. But we can simplify this, and so we get the limit as h goes to 0. Well, the numerator is x plus h minus x, so our x's will cancel, and we're just left with h on the numerator divided by h times the quantity square root of x plus h plus the square root of x. And now notice they both have an h in it in the numerator and denominator, and that cancels, so we're left with the limit as h goes to 0 of 1 over the quantity x plus h, square root of x plus h, plus square root of x. Now we can evaluate it when h is 0, and so this is 1 over the square root of x plus 0 plus the square root of x. So this is 1 over square root of x plus square root of x, which is 1 over 2 square root of x. So the key to this problem was recognizing if we had two square roots, we would multiply it by the conjugate and rationalize the numerator. So we'll do another example where if we're given f of x is x divided by x minus 1, the derivative f prime of x is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is the limit as h goes to 0 of f of x plus h becomes x plus h divided by x plus h minus 1 minus x over x minus 1 all over h. So we're subtracting two fractions. So what we want to do is find a common denominator. And so that common denominator is going to be x plus h minus 1 times x minus 1. And so in order to make this first fraction have that denominator, we need to multiply it by x minus 1 over x minus 1. And then the second one, what we need to do is multiply it by x plus h minus 1 over x plus h minus 1. And again, this is all still over h. So we have the limit as h goes to 0, and now we'll distribute and multiply this out. So we get the following. We get x squared plus xh minus x minus h minus x squared minus xh plus x all over the common denominator of x plus h minus 1 times x minus 1. And since we're dividing by another h, it's the same as multiplying by the reciprocal, multiplying by 1 over h. And so we can start canceling. Our x squareds cancel. And I think I made a mistake somewhere. Oh yes, right here. So what we had, this should be x squared minus xh. Instead of this being an h, this should have been a plus x. So we had x times 1, or minus x times negative 1 will give us a plus x. So there's the mistake that I had. So now we have our negative x, and this x right here cancels. And so we're left with the limit, as h goes to 0, of xh minus h minus xh. Oh, and those xh's will also cancel too. So rather, we're just left with, these cancel, so we're just left with minus h over x plus h minus 1 over x minus 1 times this 1 over h that we had at the end. Now, that means our h's will cancel, and we're left with the limit, as h goes to 0, of negative 1 over x plus h minus 1 times x minus 1. Evaluating the limit when h is 0, we get this is negative 1 over x plus 0 minus 1 times x minus 1. Well, this term is just x minus 1, so this is negative 1 over x minus 1 quantity squared. Now we have a definition, and this definition says that a function f is differentiable at a if f prime of a exists. Then we say it is differentiable on the open interval, or on an open interval, say this interval is from a to b, or really it could also be from a to infinity, or let's say negative infinity to a, or even negative infinity to positive infinity. So on some interval, we have it's differentiable if it is differentiable at every number on the interval. We now have a theorem, and this theorem states the following. If f is differentiable at the point A, then f is continuous at A. So now you might ask yourself, when would a function not be differentiable? We'll talk about that in a minute. Now, when can a function not be differentiable? There are three possibilities. The first possibility is that something called a corner exists. And what that means is that you might have a smooth curve, and then all of a sudden it goes right here and it goes just straight down. Not smooth, it's just a little kink in the curve. Something like that and like that. When you see that in the graph, it is continuous, but it's not smooth. There's a little corner happening. So the first thing is a corner. The second thing is that if we have a discontinuity, meaning we might have the graph that looks like this, and then it continues like that. It's not continuous at that point right here, and so it is not differentiable at that point. Now the third possibility is that if there is a vertical tangent line, so meaning that the limit as x approaches a of f prime of x is equal to infinity, or the vertical tangent line is at the point x equals a. Now, we found that given a function f, we can find its derivative and we denote it that way. But the derivative is a function on itself. We can take the derivative of the derivative, in which case, if we have f prime and we take its derivative, we could write it like this. And this is what we would say is the second derivative of f. And so another way of writing this, if we have that y is equal to our function f of x, the derivative d dx of the following, dy dx is equal to d squared y over dx squared. This is a notation used by Leibniz. So this first term, this is really saying the derivative of. This is another way of writing the first derivative. So instead of writing f prime of x, we could have written it as dy dx. And then this term over here, this is what we call the second derivative. Similarly, we can calculate the third derivative. So y triple prime can also be written as f triple prime of x, which means we're taking the derivative d dx of the second derivative, so d squared y dx squared, and what that comes out to is d cubed y dx cubed. Now these are just ways of writing the same thing. You might see it as just the triple prime, or you might see it like this, but it just all means the same thing, the third derivative. So let's do an example. If we're given f of x is equal to x cubed minus x, find the first, second, and third derivatives. From the earlier video, we found that the first derivative, f prime of x, is equal to 3x squared minus 1. So to find the second derivative, f double prime of x, we just need to take the derivative of this, of the first derivative. So this is equal to the limit as h goes to 0 of f prime of x plus h minus f prime of x all over h. So we have the limit as h goes to 0 of 3 times the quantity x plus h squared minus 1 minus 3x squared minus 1 all over h. So we get the limit as h goes to 0 of 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 all over h. Now our 1's will cancel and our 3x squareds will also cancel, leaving us with the limit as h goes to 0 of 6xh plus 3h squared all over h. And now we can cancel our h's, and our h squareds cancel. So this is the limit as h goes to 0 of 6x plus 3h. And now evaluating that when h is 0, we get this is 6x plus 3 times 0, or just 6x. So filling that in up here, we get that the second derivative, f double prime of x, is 6x. And then finally, to find the third derivative, we get f triple prime of x is the limit as h goes to 0 of the second derivative of f of x plus h minus the second derivative of f of x all over h, which is the limit as x goes to 0 of, remember the derivative is just 6x, so we have, this is going to be 6 times x plus h minus 6x all over h. So we get the limit as h goes to 0 of 6x plus 6h minus 6x over h, and our 6x's cancel. So this is the limit as h goes to 0 of 6h over h, which cancels, and that is just 6. So, moving all the way back up to the top. There we go. Moving all the way to the top, we get our third derivative is just 6. So we had our function f of x, our first derivative, our second derivative, and our third derivative. Now that you're familiar with finding the derivative of a function using the limit definition, we're now going to go over some formulas that will make your life a little bit easier. So first of all, recall if we have f of x is some constant, like f of x is equal to 3, that's the line y equals 3, and that's a horizontal line. Well, what's the slope of that horizontal line? The slope of that horizontal line is 0. So the derivative of f of x equals, or f prime rather, is going to be 0. So any sort of constant function we're going to have, it's going to be 0. So the derivative of a constant function will be dx of some constant is equal to 0. Next, we'll take a look at what happens if we have our f of x is just simply the line x. So really we're looking at the straight line y equals x. Well, what's the slope of that line? The slope of that line is just 1. So we have that the derivative is going to be dx of x is just 1. So this is, now we're starting to look at different powers. Now what about the derivative of the function f of x equals x squared? Well, if we use the definition, f prime of x is equal to the limit as x, or rather, excuse me, as h approaches 0 of f of x plus h minus f of x all over h. So this is the limit as h approaches 0 of x plus h quantity squared minus x squared all over h, which is the limit as h approaches 0, x squared plus 2xh plus h squared minus x squared all over h, and we can cancel our x squareds. So this is the limit as h approaches 0 of 2xh plus h squared all over h, and we can cancel our h's. So we're left with the limit as h approaches 0 of 2x plus h. Evaluating this when h is 0, we get this is 2x plus 0, or just 2x. So therefore, we get that if our function is f of x is x squared, the derivative f prime of x is 2x. It can also be shown that if your f of x is x cubed, just the derivative of x, f prime of x is 3x squared, and even if f of x is x to the 4, we get that the derivative of f is going to be 4x cubed. And you might notice there's a pattern going on, which leads us to the next rule. This is called the power rule. And the power rule says that if n is a positive integer, then we have the following. Then d dx, so the derivative of x to the nth power is just the power n times x raised to the power minus 1. So if you know this formula, then you won't have to compute the limit or the derivative by using the limits. So let's do some examples. So let's calculate 1 if we're given, let's say, f of x is equal to x to the 6. 2 if we're given that g of x is x to the 100. 3, how about h of t is equal to t to the 7th? And maybe, how about k of t, or maybe let's use r. K of r, so that should be an r, is equal to r cubed. So to find the derivative of each of these, we would have f prime of x, or you might see it written as d dx of f, or d dx of x to the 6. Well, we take the power 6 times x to the power minus 1. If I just slide this over a little bit, to the power minus 1, so x to the 6 minus 1, which is 6 x to the 5th. Same thing for our g. So g prime of x is d dx of x to the 100, which is going to be 100 times x to the 100 minus 1, or 100 x to the 99. The derivative of h, so h prime of t, well, since we're dealing with t, instead of writing d dx, this would be d dt of t to the 7, and this is going to be 7 times t to the 7 minus 1, or 7 t to the 6. And finally, for r, for our k, so the derivative of k with respect to r, so d dr of r cubed is going to be 3r to the 3 minus 1, or 3r squared. The next rule we have is the constant multiple rule. And the constant multiple rule will, states the following. If c is a constant, and then the function f is a differentiable function, then we have the following. We have that the derivative dx of c times our function f of x is just equal to the constant c times the derivative of f of x. So we can actually pull the constant out in front. This way we don't need to compute a whole nother derivative. We just take the constant in front and then we can figure out what the derivative of f of x is. So an example of this would be if we're trying to compute the derivative of 5x to the 6. This is the same as computing 5 times the derivative of x to the 6. Because 5 is just a constant, we pulled it in front right here. And now we know the derivative of x to the 6 by using the power rule. So this is going to be 5 times the derivative of x to the 6 is 6, x to the 6 minus 1, or x to the 5th. So we have our answer is 30 x to the 5th. The next rule that we have is called the sum rule. And the sum rule says that if we have two functions, f and g, and they are both differentiable, then what we have is the sum of the two, or the derivative of the sum of the two, d dx of f of x plus g of x is equal to the sum of each of their derivatives, d dx of f of x plus d dx of g of x. Another way you might write this using the prime notation is that f plus g prime is equal to f prime plus g prime. The next rule we have is the difference rule. And this says, similar to the sum rule, that if f and g are both differentiable, then we have that the derivative of the difference of the two is going to be the difference of the derivatives, meaning d dx of f of x minus g of x is equal to d dx of f of x minus d dx of g of x. So in other words, if we take f minus g prime, this is f prime minus g prime. So if we did an example and we're trying to find the derivative of the following, 3x to the 7 minus 4x to the 5th plus 2x to the 4 minus 7x plus 2, well, we can break this up into individual pieces. So this is going to be the derivative of 3x to the 7 minus the derivative of 4x to the fifth plus the derivative of 2x to the 4 minus the derivative of 7x plus the derivative of 2. Well, this first one, the derivative of 3x to the 7, well, 3 is a constant, so we can pull that out, and that's 3 times the derivative of x to the 7. Minus, and then the next term we can pull out 4, so we get the derivative of x to the fifth, plus we can pull out 2, so we get the derivative of x to the 4, pull out 7 times the derivative of x, plus, well, the derivative of a constant is just 0, so we don't need to worry about that. Now, the derivative of x to the 7 is 7x to the 6, because we took power 7 and subtracted 1. The derivative of x to the fifth is going to be 5x to the 4. Then we get plus 2, and the derivative of x to the 4 is going to be 4x cubed. And the derivative of x is just x. So really, the derivative of x, think about it, is x to the power 1. So that's 1 times x to the 1 minus 1. Or, well, 1 minus 1 is x to the 0, and anything to the 0 power is 1. So this is just 1. So here we have 21x to the 6 minus 20x to the 4 plus 8x cubed minus 7. And there's no x here because it's really x to the 0 power. The next rule we have is called the product rule. And the product rule states the following. If we have two functions f and g, and they are, again, both differentiable, then we have the following. Then we have the derivative dx of the product f of x times g of x. That's equal to, this is where it may not be as intuitive, f of x times the derivative of g of x plus g of x times the derivative of f of x. Okay, so if we have the derivative of the product, it's the first term times the derivative of the second plus the second times the derivative of the first. So let me write this in prime notation, and this says that if we have f times g and the derivative of that, this is going to be f times g prime plus g times f prime. So let's do an example. Let's say we have some function like this. Let's say we have our function capital F of x is going to be 6x cubed times 7x to the fourth. Well, you can think of this as our f, and this would be our g. So the derivative of capital F is going to be the first term, 6x cubed, times the derivative of the second term, 7x to the 4, plus the second term, 7x to the 4, times the derivative of the first term, 6x cubed. And now we can compute each of these. So this is going to be 6x cubed times the derivative of 7x to the 4. It's going to be 7 times the derivative of x to the 4 is 4 times x cubed, because we're taking 1 less than the power, plus 7x to the 4 times 6 times the derivative of x cubed is 3x squared. And so multiplying 6 times 7 times 4, we get 168, and then x cubed times x cubed would give us x to the 6, plus, and then multiplying out over here, our 7, our 6, and our 3, we get 126, and then x to the 4 times x squared is also x to the 6, so this can simplify to 294 x to the 6. The next rule is called the quotient rule. In this rule, people can get confused. So let's go over this carefully. The derivative of the quotient f of x divided by g of x, this is equal to the following: g of x times the derivative of f of x minus f of x times the derivative of g of x, all divided by g of x quantity squared. The difficult thing with this is knowing which one comes first. Since we're subtracting, order does matter. So we need to make sure that we go in this order. And then in prime notation, this is going to be, rather not r, but f over g prime equals g times f prime minus f times g prime over g squared. So doing an example for this, we'll do the following. If we're given that our function, let's call this f of x, is equal to x squared plus x minus 2 divided by x cubed plus 6, the derivative, f prime of x, is going to be the following. So we look at our numerator and our denominator. So we're going to take the denominator, which in this case is going to be x cubed plus 6, times the derivative of the numerator minus the numerator, x squared plus x minus 2, times the derivative of the denominator, x cubed plus 6, all divided by the denominator squared. So this becomes x cubed plus 6. The derivative of x squared is going to be just 2x. The derivative of x is 1, and the derivative of negative 2 is 0. Minus, we get x squared plus x minus 2. So this is a plus minus 2 times the derivative of x cubed is 3x squared. The derivative of 6 is 0. All divided by x cubed plus 6 quantity squared. Moving along, we can distribute this x cubed plus 6 times 2x plus 1, and so we get 2x to the 4 plus x cubed plus 12x plus 6 minus 3x to the 4 minus 3x cubed plus 6x squared, all divided by x cubed plus 6 quantity squared. And we can now start combining terms. So our x to the 4s combine, and so we get negative x to the 4. Our x to the power 3 will combine, and so we get for that minus 2x cubed. We only have one x to the power 1, so we get plus 12x. Oops, I skipped the x squared. So the x squared, this term, we get plus 6x squared, and then plus 12x. And then we have plus 6. And this will all be divided by x cubed plus 6 quantity squared. This is the answer. It's not nice, but it is the answer. And now we revisit the power rule, and the power rule will actually apply before, instead of just assuming n is a positive integer, we can assume if n is any real number, then we have the following. So then we get dx of x to the power n is n times x to the n minus 1. And this works for any power, any value n. So if we have, for example, the derivative of x to the pi, because pi is a number, 3.1415 and so forth, that's going to be pi times x to the pi minus 1. We may also have it as a fraction. So this might be the derivative of x to the 1/2 is going to be 1/2 x to the 1/2 minus 1, or 1/2 x to the negative 1/2. What about if we have a negative number? Well, same thing applies. So the derivative of x to the negative 3 is going to be negative 3 x to the negative 3 minus 1, which is negative 3 x to the negative 4. Now we'll do some examples. If we're given f of t is the square root of t times a plus b times t, find the derivative, find f prime. Well, when computing derivatives and seeing square roots, the first thing I do is rewrite it as t to the power 1/2 times a plus b t. So you'll almost always want to write square roots and anything with a radical in terms of the power. So calculating the derivative f prime of t, what we have is the product. And so the derivative of the product is going to be the first term, t to the 1/2, times the derivative of a plus b times t, plus the second term, a plus b times t, times the derivative of the first term, which is t to the 1/2. So this becomes t to the 1/2 times the derivative of a is a constant, so that's 0. Derivative of b times t is just going to be b, plus a plus b times t, times the derivative of this is 1/2 t to the power 1/2 minus 1, or negative 1/2. So we get b times t to the 1/2 plus a plus bt times 1/2 t to the negative 1/2. And that's your answer. You can leave it like this, but if you feel more comfortable writing it back as a fraction or as a radical, you can do that. B to the square root of t plus a plus bt times 1/2, and t to the negative 1/2 means it moves down to the bottom, and then that is just the square root of t. So we would have had divided by 2 times the square root of t. And the final example that we'll go over today is going to be dealing with a quotient. So if we're given y is equal to the square root of x divided by 1 plus x squared, if we wanted to find a derivative, that will be the following. The derivative is going to be the denominator, 1 plus x squared, times the derivative of the numerator. If you recall, if we had something like f over g prime, the derivative of this is going to be g times f prime minus f times g prime divided by g squared. So that's what we have right here. This is our g. This is going to be our derivative of f. And then continuing on, we get minus f, so minus our numerator, square root of x, times the derivative of the denominator, 1 plus x squared. So this is going to be 1 plus x squared. The derivative of x, of square root of, the derivative of square root of x, which is really x to the 1/2, is 1/2 x to the negative 1/2 minus, and I'm just going to rewrite square root as x to the 1/2. The derivative of 1 plus x squared, well, derivative of 1 is 0, and the derivative of x squared is 2x. Oops, I forgot that this whole thing is all going to be divided by the denominator squared. 1 plus x squared squared. So this is all divided by 1 plus x squared squared. And so simplifying this, we get 1 plus x squared times, well, times 1/2, which is the same as saying divided by 2. And just like in the last example, x to the negative 1/2 can be written as 1 over the square root of x. Minus, the next thing is square x to the 1/2, or square root of x, times 2x divided by 1 plus x squared quantity squared. And so here I'll summarize in the table of all the differentiation formulas. We have the following. So we have the derivative of a constant is just 0. We also have the derivative of x to some power n is just n times x to the power n minus 1. You just subtract 1. If we're multiplying by constant, we have c times f. The derivative of that is equal to c times the derivative of f. If we're adding two functions, we have f plus g in the derivative. This is the derivative of f plus the derivative of g. If we are subtracting two functions, f minus g, that's going to be f, derivative of f minus derivative of g. And then we have the product. If we have f times g, that's just f times the derivative of g plus g times the derivative of f. And finally, the quotient. If we have f divided by g, the derivative of that whole thing is g times the derivative of f minus f times the derivative of g divided by g squared. These are all very important formulas that you'll need in order to calculate derivatives. In this section, we're going to talk about the derivatives of trigonometric functions. So recall what the graph of sine of x looks like. And sine of x starts at 0. It goes up, comes back down, goes back up, and repeats. And same thing like this. And it has a period of 2 pi. Halfway of that would be pi. And then we fill out in the middle of all of these. This would be 3 pi over 2, this would be pi over 2, and then negative as well. So this is the graph of y equals sine of x. Or let's call this f of x is y equals sine of x. Now, what would the graph of the derivative look like? Pi, so bringing all these down, we have pi, we have 3 pi over 2, and 2 pi. So the graph of y equals the derivative f prime of x. Well, when we start by graphing the derivatives, we want to look at the maximums and minimums because that means the slope is 0, and so it crosses right here on the axis. Now, looking over here, we have a positive slope. It's increasing, so it's positive. So we're going to be, it's going to be with a high positive value, and it gets lower and lower until we hit 0. So we have a high positive number, and it gets smaller and smaller until you hit 0. And then you have a negative slope. Starts off with a little bit of negative, and then a lot, and then just a little bit. So little negative, big negative, little bit negative. And then, oh, excuse me, that was wrong. Little bit negative, big negative, and then goes back down to a little bit negative. And then over here, we have positive, it's increasing. And so small negative, bigger negative. And as you see, this is kind of a crude graph, but this kind of looks like the function that we might have seen this before. This kind of looks like a sine function or a cosine function, but it does look very trigonometric. And it would repeat back here too. Now we have a couple of equations that I'm going to give you. We have that the limit as theta approaches 0 of sine of theta over theta. Well, what do you think this is? As theta gets towards 0, well, sine is also going towards 0, but theta is also going towards 0. In fact, in this case, it's just equal to 1. Now we have another one that looks at the limit as theta goes to 0 of cosine theta minus 1 over theta, and this time that is equal to 0. And now the derivatives of sine and cosine, and we'll talk about that right now. If you noticed from the graph from before, it sort of looks like the derivative of sine of x is actually equal to cosine of x. So this is a pretty important one. Derivative of sine of x is equal to cosine of x, and the derivative of cosine of x, not quite equal to sine of x. In fact, it's actually equal to negative sine of x. So let's do an example. If we have y is equal to x squared times sine of x, calculate its derivative. So dy dx is equal to the derivative of x squared times the derivative of the second term, so derivative of sine of x, plus sine of x times the derivative of the first term. So this is derivative of sine of x we know to be cosine of x plus sine of x times derivative of x squared, 2x. So this is our answer, but I'm just going to rewrite it. X squared cosine of x plus 2x sine of x. So let me give you all the derivatives of trigonometric functions. So we have the first one, the derivative of sine of x, and that is cosine of x. The second one is the derivative of cosine of x, and that is going to be negative sine of x. The third derivative is the derivative of tangent of x, and this is a little bit different. Derivative of tangent is going to be secant squared of x. And for tangent, if you forget how that the derivative is secant squared, you can always reprove it by looking at tangent is sine over cosine and using the quotient formula. The next derivative is d dx of cosecant of x, and that's going to be negative cosecant of x times cotangent of x. And then we have the derivative of secant of x, and that's going to be secant of x times tangent of x. And these two, again, if you forget how to do that, you can always rely on the quotient formula, because cosecant of x is 1 over sine of x, and then you can use the quotient rule, or you can even use the power rule, sine of x to the power -1, to solve all this. And the final trig function that we have is the derivative of cotangent of x, and that's just negative cosecant squared of x. Now let's do an example. If f of x is equal to secant of x divided by 1 plus tangent of x, what is the derivative f prime of x? Well, we're going to use the quotient formula, which says the following, which says the denominator 1 plus tangent of x times the derivative of the numerator plus, or excuse me, not plus, but minus the numerator times the derivative of the denominator, 1 plus tangent of x, all divided by the denominator squared. So here we have, this is going to be 1 plus tangent of x. The derivative of secant of x is secant x tangent x minus secant of x times the derivative of 1 plus tangent of x. Well, the derivative of 1 is 0, and the derivative of tangent of x is secant squared of x, all divided by 1 plus tangent squared of x, quantity squared. Now, we're going to simplify, but notice that there's a secant of x in all these terms. So I'm going to first factor out secant of x. And so what I have left after I factor out secant of x is going to be 1 plus tangent of x times tangent of x minus secant squared of x, all divided by 1 plus tangent squared of x, quantity squared, or secant of x times the quantity tangent of x plus tangent squared of x minus secant squared of x, all over 1 plus tangent squared of x, quantity squared. Now, we could be done, but we can actually simplify this just a little bit further. Notice we have a trig identity that says tangent squared of x plus 1 is equal to secant squared of x, or rewriting this, tangent squared of x minus secant squared of x is equal to -1. And so we can simplify this further. secant of x times tangent of x minus 1 all over 1 plus tangent squared of x quantity squared. So this is our final answer. But if you use this one right before it, that would be acceptable in class. The final example that we're going to do today is going to be the following. Find the limit as x approaches 0 of sine of 7x divided by 4x. Now recall that we do know what would happen if we took the limit as theta goes to 0 of sine of theta over theta, and that equals 1. The thing here is that we don't just have, it's not just x, it's 7x. So we need to do some simplifications first. Now, if it looked something of the form, the limit as 7x approaches 0 of sine of 7x over 7x, that would equal 1. Because instead of writing theta, we just wrote 7x each time we saw it. So, is there a way that we can do that? Let's take a look. So, this is going to be the limit as x goes to 0 of sine of 7x over 4x. And now what we're going to do is we're going to rewrite this, and we're going to multiply 7 over 7. So now this is going to be the limit as x goes to 0 of, and I'm actually going to swap places of this 4 and 7. So we're going to have, this is going to be sine of 7x divided by 7x times 7 over 4. And it's important to note right now that if we have sine of 7x, this is not equal to 7 times sine of x. So just make sure to note that. And that's why we're having problems, and we need to make further simplifications. Now, we're going to make the substitution theta is equal to 7x. Okay? So this is going to be the limit. So instead of writing 7x, this is sine of theta over theta and then times 7/4. The only thing is that now x was going to 0. So looking here at the substitution, if x goes to 0, what does theta go to? Well, theta will also goes to 0. So as x goes to 0, so does theta. So theta also goes to 0. So this is the limit as theta goes to 0. And now this looks like the form that we know. This is going to be, this whole thing is just 1 times 7 over 4, and so our answer is 7/4. Today we're going to talk about the chain rule. If we're given some function, let's say capital F of x, and that function is equal to sine of x squared plus 1, how would you calculate the derivative of this? Well, what we have here is this here is a composite function. A composite function looks something of the form like y, if that were equal to our f of x, then that would look like little f composed of the function g of x. Or you might see it with a little circle like this, f of g. So in this case, our outer function, little f, would be something like this. We'd say y is equal to little f of, for now we're just going to ignore that, and so that's little f of u. And our outer function dealing with right here is going to be the sine. So we'd say this is just sine of some u. And then for our inner function, what would u be? Well, u is our g of x, and the inside of this, the inside of the sine, is x squared plus 1. So now taking the derivative of this whole thing, the composite function sine of the quantity x squared plus 1, we would have to take the derivative of sine, but we also have to take the derivative of x squared plus 1. So this leads us to the following. If we wanted to take the derivative with respect to y, or the derivative of y, excuse me, with respect to x, what we would do is take the derivative by looking up here. So if y is this, or rather y is this, the derivative of y with respect to, well, if we look here, it's a function of u. So this would be the derivative of y with respect to u times, then we take the chain rule, and this is the derivative of u with respect to x. So now I'm going to go ahead and write this up formally. The chain rule states the following. If g is differentiable at the point x, and f is differentiable at g of x, then the composite function and we're going to define that to be capital F is little f of little g. So defined capital F of x is little f of little g of x. Then this is differentiable at x, and then the derivative, capital F prime, is given by the product, and I'm going to move that up, give me some space, is given by the product, capital F prime of x equals little f prime of g of x times g prime of x. Or another way of writing this is that if y equals f of u and u equals g of x, then we have for the product rule, or rather the chain rule, excuse me, dy dx is dy du times du dx. So now we'll go ahead and actually solve the example that we started with. We defined our function capital F of x to be sine of the quantity x squared plus 1, and so if capital F was equal to little f of g of x, this capital F of x, then our f of some u is going to be sine of u, and our g of x was the inside, so x squared plus 1. we can compute each of these derivatives. And so f prime of u is, derivative of sine is cosine of u, and g prime of x is equal to x squared plus 1. Now, what was our u? What is the u that we're dealing with? Well, that's right here. Sine of u is the inside of the sine. So we know that u is equal to x squared plus 1. Now, using the formula that we have, we know that the derivative of capital F of x is equal to f prime of g of x times g prime of x. Okay, and so this u right here, that was just our g of x. So plugging it in, we get f prime is cosine of u, and u was x squared plus 1. So this is cosine of the quantity x squared plus 1 times g prime, and g prime, oh, excuse me, this is wrong. It's the derivative of x squared plus 1. So the derivative of x squared is 2x. So this is times 2x. And this is our derivative. So basically what we need to do when we're taking the derivative of a composite function is take the outside function, in this case sine. The derivative of sine is cosine, and you leave everything else the same, and then you multiply it by the derivative of the inside. The derivative of x squared plus 1 is 2x. And there you go. So if we put that into words, what we have is that this is the derivative of the outer function, but we're going to evaluate it at the inner function. And then all that is going to be multiplied by the derivative of the inner function. Okay, so the chain rule says we have some big function like this. You take the derivative of the outer function, f prime, evaluate it at the inner function g of x, and multiply that whole thing by the derivative of the inner function, g prime. So let's do another example. So if we had y is equal to 3x squared plus 1 raised to the power 2, now we could expand this and then take the derivative of that, or we could just take the derivative using the chain rule. So using the chain rule, the outer function here is something that's being squared. So our little f of u is u squared, and then the inner function g of x is 3x squared plus 1. So the derivative f prime of u is just 2u, and g prime of x is 6x. So the derivative dy dx is going to be the derivative of the outer function. So the derivative of the outer function f is 2 times the original function, 2 times the inner function, 2u, so this is 3x squared plus 1 multiplied by the derivative of the inner function, 6x. And there you go. Now you could simplify this. This would be 12x times the quantity 3x squared plus 1, or 36x cubed plus 12x. So this leads us to a new rule, the chain rule involving a power rule. So the power rule combined with the chain rule. And so for that, what we have is that if n is any real number and u equals g of x is differentiable, then we have the following. The derivative with respect to x, so d dx of u to the power n is equal to n times u to the n minus 1, that's the derivative of u, times the chain rule, times the derivative of u with respect to x. Okay, so what we did here is the power rule. So anything to the power n becomes n times that function to the n minus 1. But if u is a function, we want to also take the derivative of u. So an alternate way of writing this would be the following. d dx of g of x to the power n is n times our function g of x raised to the n minus 1 times g prime of x. So let's do another example. If we're given the function g of x is equal to the quantity t minus 2 divided by 2t plus 1 to the power 9, we can compute its derivative. G prime of x is going to be, remember, we're taking the derivative of the outside. What's the outside function here? That's the power 9. So the derivative would be 9 times the inside function to the power 8. Right? Anything to the power 9 would be 9 times that raised to the power of 8. And then we have to take the derivative of the inside times the derivative of the inside, t minus 2 over 2t plus 1. Now it's a little bit harder because we have to use the quotient rule. So we get 9 times the quantity t minus 2 over 2t plus 1 to the power 8 times the quotient rule. Remember, the quotient rule says the denominator, 2t plus 1, times the derivative of the numerator, in this case the derivative of the numerator is 1, minus the numerator, t minus 2, times the derivative of the denominator. The derivative of 2t plus 1 is just 2. All divided by the denominator squared. And so we can go ahead and expand this, and what we would get is the following. We get 9 times the quantity t minus 2 to the 8 over 2t plus 1, oops, that should be a plus 1 to the 8 times, and then this fraction we get, from here we get 2t, and so we get 2t plus 1 minus 2t minus a negative, so plus 4 all over 2t plus 1 to the power 2. Give me a little bit more space. We can then get 9 times t minus 2 to the power 8. Our 2t's will cancel, and then our 1 plus 4 gives us 5. And then all in the denominator, 2t plus 1 to the 8 times 2t plus 1 to the 2 will give us 2t plus 1 to the 10. So 9 times 5 gives us 45, so that cancels. 45 times the quantity t minus 2 to the 8 divided by 2t plus 1 to the 10. And that's our answer. Now what if our function f of x is sine of cosine of tangent of x? Well, to take the derivative, we just apply the chain rule, and we're going to apply it twice. So we have sine of all this stuff on the inside. So taking the derivative, we first take the derivative of the outer function. Derivative of sine would give us cosine. In fact, I'm going to change my color right here, just so that we can see that. So derivative of sine is going to be cosine, and the inside stays the same, of cosine of tangent of x, times the chain rule, times the derivative of the inside. So we're going to take the inside right here, so the derivative of cosine of tangent of x. And so we get the following. So this is going to be, this equals cosine of tangent of x times, well, the derivative over here, derivative of this, it's another composite function. The derivative of the outside, so the derivative of cosine is going to be negative sine of tangent, the derivative of cosine is negative sine, times the chain rule, times the derivative of the inside, times d dx of tangent of x. And so, putting this all together, we get cosine of tangent of x times this negative. I'm going to put the negative all the way in front. So negative of the whole thing times sine of tangent of x times the derivative of tangent is secant squared of x. And so this right here is the derivative. Now most of the functions we've dealt with so far are of the form y is equal to f of x, and we can write everything just in terms of x. But sometimes there's other equations that aren't as simple. For example, the equation of a circle is x squared plus y squared equals 5 squared. And this is a circle with radius 5. How would you take the derivative of this? Because we can't just solve it in terms of y. We could get y squared is 25 minus x squared, but when we solve for y, you're going to get y is equal to plus or minus the square root of 25 minus x squared. And so we actually get two functions, the positive square root and the negative square root. So what we do when we have something like the equation of a circle is the following. If we're given x squared plus y squared equals 25, and we want to take the derivative of everything, we write it as the derivative with respect to x of x squared plus y squared is the derivative with respect to x of 25. We're taking the derivative of both sides. Now, the derivative going through this first term, the derivative of x squared with respect to x, so that would be d dx of x squared plus the derivative of y squared with respect to x, d dx of y squared, and then d dx of 25. So let's compute each of these derivatives. Well, the derivative with respect to x of x squared, so this right here is just 2x. For now, I'm going to leave this as it is. And then the derivative of 25, that's a constant. So that's just 0. But we need to first figure out what this derivative is. So I'm going to change my color, and we got to figure out what that derivative is. So the derivative with respect to x of y squared is going to be the following. We can use the chain rule, and so that's the derivative with respect to y of y squared times the chain rule, the derivative of y with respect to x. So the derivative of y squared with respect to y is just 2y, and then times dy dx. So putting this all together, we get 2x plus 2y times dy dx is equal to 0. And when we solve for the derivatives, usually what we were trying to find is dy dx. Going ahead and moving this all up, we'll rewrite everything in terms of dy dx. So we subtract 2x from both sides. So we get 2y times dy dx is negative 2x. Our 2's will cancel. And then dividing both sides by y, we get dy dx is negative x over y. And that is your derivative. So now, just kind of put everything all in one site. And what we did, we wanted to find the derivative of this whole thing. And so you can think about it as going through just taking the derivatives. The derivative of x squared is 2x. The derivative of y squared, thinking of y as a function of x, so of y squared is 2y times the chain rule dy dx, and then the derivative of 25, so the derivative constant is 0. Rearranging terms, solving for dy dx, we get the following, negative x over y. All right, let's do another example. If we're given that y squared is equal to x squared plus sine of xy, solve for the derivative dy dx. Well, we're going to go through our function and just take the derivative as we go through. The derivative of y squared is 2y times dy dx equals the derivative of x squared is 2x plus the derivative of sine, so this is sine of something on the inside. So derivative of sine is cosine of the things inside. So cosine of xy times the chain rule times the derivative of the inside. The derivative of the inside, well, that's going to be the product rule. Okay, and we'll do that right now. So the derivative of the inside of x times y is the product rule. Product rule says the derivative of the first term times the second term plus the derivative of the second term times the first term. Well, derivative of x is just 1, so this is 1 times y, or just y, plus the derivative with respect to x of y is just dy dx times x. So we can plug this in to right there. And we get the following. We get 2y times dy dx is equal to 2x plus cosine of xy times the quantity y plus dy dx times x. Now we want all the dy dx's on one side, so we need to do some simplification. We're going to expand this on the right, so this is going to be y times sine of xy plus, I'm going to move the x in front, x cosine of xy times dy dx. And now what we want is we want all the dy's dx's on one side. So I'm going to move this term over to the left side by subtracting. So we get 2y dy dx minus x cosine of xy dy dx equals 2x plus y cosine of xy. On the left side, they all share the term dy dx, so I can factor that out. So we get 2y minus x cosine of xy times the quantity dy dx, and then we have 2x plus y cosine of xy. And the last step, we want to get dy dx by itself. And so we're going to divide by 2y minus x cosine of xy. 2y minus x cosine of xy. And so the final product, or the final derivative, dy over dx is equal to 2x plus y times cosine of xy, all divided by 2y minus x cosine of xy. And this is your derivative. Today we're going to talk about related rates. So we'll begin with an example. Now the volume of a sphere is given by the following. V is 4/3 pi times the radius cubed. But if we wanted to find what is the change of volume over time, that is dv dt, the derivative with respect to time, well, we take the derivative, this is going to be 4/3 times pi, but we're dealing with r and not t. But as the volume changes, increases or decreases, so will the radius. So in fact, we're going to use the chain rule and take the derivative of r cubed. Derivative of r cubed is 3r squared. Now this simplifies, our 3's will cancel, and so we get that the derivative of the volume with respect to time is 4 times pi times r squared. Now remember, the chain rule says that if we take the derivative of r squared, we also have to add dr dt. So this is going to be times dr dt. And so now if we have the, for the example, we say we have a balloon increases, so air is being pumped into balloon, and then a balloon is increasing in volume at a rate of 100 cubic centimeters per second. How fast is the radius increasing? If the radius of the balloon is 25 centimeters. So what we're going to use is this equation we have right here. We're going to use dv dt is equal to 4 pi r squared times dr dt. Now what sort of information are we given? We're given that the volume is increasing at a rate of 100 cubic centimeters per second. So volume is increasing at a rate, so this is going to tell us our dv dt. We're also given the radius is 25 centimeters, so that's our r. And then finally, what are we trying to find? We want to find how fast is the radius increasing. That is, we want dr dt. So let's plug in what we have and solve. dv dt is 100, and that's equal to 4 pi. Our radius is 25, so times 25 squared times dr dt. We're trying to solve for dr dt. And so, moving everything around, what do we get? Divide both sides by 4 pi times 25 squared, 4 pi times 25 squared. We get that dr dt is equal to, we simplify 100 over 4, and then 4 times 25 is 100, but we have 100 squared, so this is just 1 over 25. 25 pi. And so that is the rate that the radius is increasing. And then our units here were centimeters per second. Now for our next example, what if we had a ladder resting on a wall and the ladder is 10 foot long? So it looks something like this. 10 foot long ladder, and we have some x length and a y length. If you forget to hold the bottom of the ladder down here, and the bottom of the ladder starts to slide away from the wall, so we have a 10-foot ladder, and the bottom slides away at a rate of 1 foot per second, and you're standing at the top of the ladder and you want to know how fast is the top of the ladder going down the wall. So what do we do here? We want to know how fast the ladder is going down the wall. In this case, we don't have a nice equation like we did for the volume of a sphere, but that's all right. What do we have here? We have a right triangle. So we can relate all the sides using the Pythagorean theorem. And that says that x squared plus y squared equals the hypotenuse squared, which is 10 squared. And now, what are the pieces of information that we're given? It's going away from the wall at a rate of 1 foot per second. So if it's going away, that's your x direction, and the rate is changing. So this is your dx, dt. And what are you trying to find? You're trying to find how fast is the ladder moving away from the wall. And so this is how fast the ladder is moving away from the wall. That would be, or moving down the wall rather, that would be your dy dt. And let's say we want to find this when we are 6 feet from the wall. When we're 6 feet from the wall. So that's our x value. So we want to find out when x, so that's when x is 6. So we can plug this in. First of all, let's take the derivative. We're going to use the chain rule again. So we get 2x times the chain rule, dx dt, plus 2y times dy dt is equal to, well, what's the derivative of 10 squared, or of 100? Since it's a constant number, that derivative is 0. So now, plugging things in, we have 2. Our x value is 6. So 2 times 6 times dx dt, and we know dx dt is 1 from up here, plus 2. Now, do we know our y? No, we don't know our y, but we can figure it out because of the Pythagorean theorem. If x is 6, we can figure out y. So this is going to be 6 squared, because that was our x value, plus y squared is equal to 10 squared. Now solving this, or if you recognize this is a 3, 4, 5 triangle, we end up with y is equal to 8. So this is going to be 2 times 8 times dy dt equals 0. And so what we get is we get 12 plus 16 dy dt equals 0. Moving things around, we get that your dy dt is equal to negative 3 over 4 feet per second. And that makes sense that there's a negative because you're moving downwards. Your y value is decreasing. That's our answer. Now let's say we have water going into a tank that's in the shape of an inverted cone. So it looks something like this. And so given this, and we have water going into the tank at a rate of 9 cubic feet per minute, we have it going into 9 cubic feet per minute. And this tank, it has a height of 10 feet, and the base of the radius is going to be 5 feet. So this tank right here is 10 feet tall. So height is 10 feet, and then the radius at the base, that's going to be 5 feet. So right here, that radius is 5 feet. So if we add water to it, water might come up at this level. So it might not be all the way up. But the tank itself is 10 feet tall and has a radius of 5 feet. Now, what I want to know is how fast is the water rising when the water in the tank is 6 feet deep. So when this height is going to be 6 feet, how high is the water changing? Well, we need to do a couple of things here. First of all, what's the equation for the volume of a cylinder? That equation is going to be V is equal to 1/3 pi times your radius squared times your height. And so we'll let the radius be x, and then we'll let the height be y. So volume is 1/3 pi times x times y. Now, unlike the other problems that we did, we only had two variables. We had v, and then we had something else. We didn't have x and y. We didn't have v, x, and y. We only want two. Is there a way that we can reduce this to just two variables? Well, if you take a look at this, we actually can. And this is by using similar triangles. So taking a look at the triangles, we have one triangle like this with a height of 10 and a radius of 5. If we look at the other triangle and we had some height, let's say y, then we could figure out that the x value, or the radius, would be some x value. And so looking at these ratios, what we have is x over y is equal to 5 over 10. Or if we solved for x, x is equal to y over 2. And so now we can actually plug this in for x. So the volume can now be expressed as 1/3 pi times, instead of x, it's going to be y over 2 times y. Or, in other words, it should be x squared. So the volume is 1/3 pi the radius squared, so this is really the area of a circle. So this should be a squared right there. Okay, so volume is 1/3 pi times y over 2 quantity squared times y. Or volume is equal to pi over 12 times y cubed. And now we can calculate, finish this equation, or this problem. So taking the derivative, we get dv dt is equal to pi over 12 times 3 y squared, we're using the chain rule, times dy dt. Our 3 and our 12 cancel. So this is really pi over 4 y squared dy dt. So if we look back at what the original question was stating, and that was we had water going in at a rate of 9 feet per minute, and that should be cubic feet per minute, and we wanted to find when it was 6 feet deep. So that was when y is 6 feet. We'll have the following. So the change in volume, what was coming in was 9. So this should be 9 equals pi over 4 times the change in height, which was 6, squared times dy dt. 6 squared is 36 divided by 4. That right there simplifies to 9. And our 9's will now cancel. So we have 9 over here and 9 over here, and they cancel. So we have 1 is equal to pi times dy dt. Solving for dy dt, we get that is just 1 over pi. And then the rate, the units rather, is feet per minute. So there's a couple of strategies that we can use when dealing with these types of problems. The first is to read the problem carefully. The second thing, it really helps to draw a diagram, and this is if possible. The third thing is to introduce notation. So in the problems that we gave, they didn't say dy dt is equal to so and so, or solve for dx dt. They just said what is the change of height the rate of the change in height. And so we had to introduce our own notation to do that. So introduce your notation, and then you assign symbols to all quantities that are functions of time. Then the next thing we do is we express the given information and the required information, or rather the required rate, in terms of derivatives. The fifth thing is to write an equation that relates the various quantities of the problem if necessary, use geometry to eliminate one of the variables to eliminate one of the variables by substitution. And that's what we did in the last example. We had three things, and we could substitute, we had v, x, and y, and when we found the ratio, we could eliminate our x variable by substituting. X was y over 2. Number 6. Use the chain rule. Okay, we're going to use the chain rule to differentiate both sides of the equation with respect to our variable t. All right, and the last step for solving these types of problems, 7, substitute the given information into the resulting equation and solve for the unknown rate. And so these steps will help you with your problem solving on related rates. Now today we're going to talk about linear approximations and differentials. Now if you recall, given some sort of curve like this, and this is the curve y is equal to f of x, the tangent line at some point right over here, at some point a, so we'll say this is a comma f of a, the tangent line is going to go right through that, but have this and have the same slope. So the tangent line y is equal to, let's call this L of x. Now the point of this is that we might be able to calculate what f of a is, but we might not be able to calculate, or it might be very hard to figure out what f of x is when x is really near a. And so what we could do is use this tangent line to help us approximate it, because the tangent line near when x is a is a pretty good approximation to the curve y equals f of x. So if you see, when we're here, we're pretty close. As we get further away, there's more of an error to where the y value is, but nearby, it should be pretty close. Now, if you remember the equation of a line using the point-slope formula, that is y minus y1 is equal to m times the quantity x minus x1. If we moved our y1 over, we have the equation y is equal to y1 plus m times x minus x1. And this is if we have some point x1 comma y1, and we have a slope that's going to be m. Now, if the point that we have is this point a comma f of a, what we can do is our y1 value is f of a, and then our x1 value is our a, and what's the slope at that point? Well, the slope is the derivative, so it's going to be f prime at a. So we have f of a plus f prime of a times the quantity x minus a, and that is what that's going to be an approximation for f of x. So let me rewrite that a little bit better. So the approximation f of x is approximately equal to some point f of a that we know plus f prime at a times the quantity x minus a. And again, to help you remember this formula, rather than having to remember it from scratch, if you just think about the point slope formula, you'll be able to fill in the details. So this is what we call a linear approximation, or the tangent line approximation. Okay, so this is the linear approximation. Or the tangent line approximation of f at the point A. And if we wrote for the linear function, capital L of x is equal to f of a plus f prime of a times the quantity x minus a, so using this, this is what we call the linearization of f at a. So let's do an example. Let's find the linearization of the function f of x is equal to the square root of 1 plus x at the point x equals 0. Okay? So what we have here is a square root function. And yeah, we know some of the square roots, but do we know, for example, the square root of 1.2? Well, we can approximate that using our linear approximation. So remember, the formula for the linear approximation, L of x is equal to f of a plus f prime at a times the quantity x minus a. So we're going to need this, but first of all, in order to do all that, we need to figure out certain things. So in this case, our a is 0. So we want to figure out what is f of 0. Well, f of 0 is going to be the square root of 1 plus 0, which is just 1. And then we got to find the derivative, f prime at a, or f prime of 0. So let's first figure out the derivative. So the derivative of this, and remember, our f of x, another way to write the square root is 1 plus x to the power 1/2. So this is going to be 1/2 the quantity 1 plus x to the negative 1/2. Or 1 over 2 times the square root of 1 plus x. And figuring out what this is, evaluating at 0, our f prime at 0, this is 1 over 2 times the square root of 1 plus 0, or just simply 1/2. So now we have everything, and we can plug it into the linearization, and we get L of x is equal to f of 0 plus f prime of 0 times x minus 0. Well, x minus 0, that's just x. So f prime of 0, we get from right here, it's just 1. So 1 plus f prime at 0, that's going to be right here, 1/2 times x. So our linearization is just 1 plus x over 2. So what this is saying, this is the linear approximation for the square root of 1 plus x is approximately equal to 1 plus x over 2. This is when x is near 0. So let's actually test this. Let's see how accurate we are. So if we're, let's say, near 0, or when x is near 0, let's say when x is 0.2. So we're trying to find the square root of 1 plus 0.2, which is the square root of 1.2. Now, according to the approximation, let me see if I can just move this down a little bit. There we go. So the approximation says the following. The approximation says that this should be 1 plus 0.2 over 2. That's what we said right here. In fact, I'll box that, or I'll box it right here. So this should be approximately 1 plus 0.2 over 2, and that is going to be 1.10. Now if you plug this in on your calculator, you find that the true value for this is 1.095445. So we're close-ish, but let's see. This really works well when we're near 0. So let's get a little bit closer to 0. Let's say 1 plus 0.05. So we're taking the square root of 1.05. This is going to be, according to our linear approximation, 1 plus 0.05 over 2, which gives us 1.025. And if we plug this on our calculator, what do we get? We get 1.024695. That's closer to the true value. Let's see if we can get better. Let's get even closer to 0. So we're going to say 1 plus 0.005. Okay, so that's going to be 1.005, which is approximately equal to 1 plus 0.005 all over 2. And according to the linear approximation, we get this is 1.00250. But the true value, if you use a calculator, this is 1.0024497. We're getting closer and closer to the true value. The closer and closer we get to 0. The closer that this number gets to 0. But this is just our linear approximation, and that's what we use it for. We know how to take the square root of certain numbers, like when x is 0, and we can use that to find other values. So if I said, find the linear approximation of f of x equals the square root of 1 plus x at the point x equals 3, what we can do is the following. So 3 is really our a, and so we want to find L of x at the point a equals 3. Well, we need a couple of things. We need to figure out what is f of 3. Well, f of 3 is the square root of 1 plus 3, which is the square root of 4, or just 2. We need to compute the derivative, and so we know the derivative over here is going to be the derivative at 3 of f. Remember, we calculated the derivative on the other slide, so that was 1 over 2 times the square root of 1 plus a. So 1 plus 3, and so this is going to be 1/4. So the linearization L of x is going to be, remember, L of x is going to be f of a plus f prime of a times x minus a. So we get L of x is f of a, which is 2 from right here, plus the derivative, which is going to be 1/4 times x minus a times x minus 3. So that's our approximation, which, using some simplification, ends up being 5/4 plus x over 4. Now we're going to shift gears and talk about differentials. So let y equals f of x, and let this be a differentiable function. Then we say that the differential and the differential dx, this differential is an independent variable, and then we say that the differential dy that is going to be a dependent variable. So the differential dy is a dependent variable, and so this is defined as the following. We're going to define it to be dependent, so it's going to have some sort of dx in it, so the derivative f prime times dx, and that's why it's dependent, because it depends on whatever the x value is. Now geometrically, what this looks like is the following. So if we have our curve, that's the curve y equals f of x. We have some point right here. We'll say that that point is P, and so that point corresponds to some x value. And then we're going to add some delta x to it. So this point right here would be x plus delta x. So we go up to here, and at some distance, delta x, we're right here. But if we approximated it at p, and we had some linear approximation, or even the tangent line, as you may, it goes like that, and it doesn't quite fit. We have this error right there. So if we extended this all the way up, and we call this our point R, and we call this intersection Q, then what we would have, and we'll maybe extend this over here, we'll call this the point S. So this distance that we have right here is delta x. Our change in the y value, this would be our delta y. Now if we're using differentials, our dx is going to be the same as our delta x. But if we're looking up here, this big change in y, that is dy. So our delta x is the same as dx, but our delta y is right here, and then the dy adds all this extra stuff up there. So if we were to express this in terms of an equation, what we get is delta y is equal to f of x plus delta x minus f of x. So that's how we can get our delta y. It's just the y value right here, f of x plus delta x, minus this height, which happens to be the same as f of x. Now we know this is the slope, and so we know slope is rise over run. So the slope f prime of x is rise dy dx, rise dy over dx, which means that rearranging this, we get dy is equal to our slope f prime of x times dx. And so here we have two equations that we can use for differentials. So I know this may seem confusing, so we're going to do an example using these two equations. I should probably have highlighted them, but I'll just underline them in a different color. Okay, so example, we're going to compare our delta y and our dy if we're given y equals f of x, which is the function x cubed plus x squared minus 2x plus 1, and we're given that x changes from 2 to 2.05. Okay. So take a look at this equation, these two equations. I'm going to move the screen so you're not going to be able to use them anymore. Okay. So let's begin. What we're going to have is we want to figure out what is our delta y and what's our dy. To do that, what do we need? We need a couple of pieces of information. To find delta y first, well, delta y, that was our f of x plus delta x. So that would have been our f of 2.05. And then we minus our f of x, so minus f of 2. So let's figure out what's f of 2.5. So f of 2.5, plugging it in to this equation. right here. I already did that. And so f of, excuse me, not 2.5, 2.05. F of 2.05 is 9.717625. And f of 2 comes out to just 9. So our delta y is 9.717625 minus 9, which is 0.717625. That's our delta y. Now we're going to find dy. So dy is given by the following: f prime of x times dx. So again, on the side, we need to figure out what's f prime of x. So f prime of x is the derivative of this whole thing. Derivative of x cubed is 3x squared, plus the derivative of x squared is 2x, and then the derivative of negative 2x is negative 2, and the derivative of 1 is a constant, so it's 0. So that's f prime of x. And so if we're doing this at dy is equal to f prime of 2, and then our dx is our 0.05, f prime of 2 is equal to the following: 14. And so, plugging in, we get dy is 14 times 0.05, so we get our dy is going to be 0.7. And you see these two, our delta y and our dy, they're in the same ballpark, but they are in fact different. Now let's do one more example. In this last example, let's have that the radius of a sphere, and this is actually going to be something that we might calculate, and this was measured to and found to be 21 centimeters. And when we measure this, it might have a possible error in the measurement of at most 0.05 centimeters. So what is the maximum error in using the value of the radius to compute the volume of the sphere? Okay, so what we did is we measured the radius, but somehow using the tools that we did, our tools might give us a maximum error of 0.05, or a possible error in our measurement of 0.05 centimeters. What's the maximum error that we could get when we compute the volume? So, well, the volume of a sphere, V, is equal to 4/3 pi r cubed. If we let the dr equal delta r, and this is going to be our error in the radius, then the corresponding error in our volume would be this delta v. And we can approximate our delta v using the differential. So, the differential, taking the derivative, we get dv is equal to, the derivative over here is using the power rule, we bring the 3 in front, it cancels with that, so it's just 4 pi r squared times dr. And so if we're doing this when the radius r is measured to be 21 and the possible error in r is measured to be 0.05, we get dv is 4 times pi times 21 squared times 0.05. And so therefore, we get our dv is approximately equal to 277 cubic centimeters. So we computed the volume, and the volume can have an error of 277 cubic centimeters. That might seem pretty big, but it might not, because depending on the size of what we're dealing with. And so this is something that we're going to take a look at, and that's something that's called a relative error. And let me actually put a little color to this. So this is a relative error. And the relative error is essentially the following. You take your error and you divide it by what the whole thing was. So we're going to take our delta v. Let me just write this back in black. So we're going to take delta v and divide it by v. So how big is the error compared to the actual volume? And so maybe that's going to be approximately equal to dv over v, which is dv is 4 pi r squared times dr over 4/3 pi r cubed. So that's 3 times dr over r. And so looking at what we had, what we get, since we had our r and dr, this is going to be 3 times 0.05 over 21, and that's approximately about 0.007, and if we converted this to a percent, this is 0.7%. That's pretty good, less than 1%, and this percentage that we call, that's something that's called the percentage error. Now we could have solved this without this equation right here. All we needed to do was find our error, or divide it by the total volume. So we could have taken 277, and if we knew what the volume was, divided by the volume. In this case, we didn't, but we could have actually computed it by the volume is 4/3 pi r cubed. Today we're going to talk about maximum and minimum values. So we'll begin with the definition. If we let C be a number in the domain of, and we'll call the domain D, of a function f, then f evaluated at that point C is going to be called the following. It's going to be called the absolute maximum is the absolute maximum value of the function f on D if f evaluated at C is greater than or equal to f of x for all x in your domain D. And then we say that the absolute minimum value of the function f on the domain D is if we have f of c is less than or equal to f of x for all x in D. And so let's take a look at an example. Let's say we have a graph and our domain is just going to be something like this. And that's all we're dealing with. Well, what is the absolute maximum value? This is because there is no value, an f of x value that's higher than that. And then this would be the absolute minimum value because there is no value that's lower than that. And so if we said like this was the point C and maybe this is the point D, then f of c is greater than or equal to f of x for every x that falls in this domain. And similarly we would say f of d is less than or equal to f of x for every x in the domain, and that's where this curve is our function f of x. We have another definition, and this definition begins with the number f of c is one of the two following things: a local maxima or maximum value if we have the following. So it's local maximum value of our function f if f of c is greater than or equal to f of x when x is near c. And then we have the second definition, that this says that it is a local minimum value of our function f if f of c is less than or equal to f of x when x is near the point C. So what I mean by that is the following. So if we have our function, and let's say we're still in our domain, and we look to be something like this. Now, this point right here is the absolute minimum because there's nothing else that's lower than that. But this point right here is a local minimum because if we're near that value, so we're near in terms of x direction, it's the lowest point near it. So this is a local minimum. This point up here is the absolute maximum. There's nothing else higher than that. But this is a local maximum, and this is also a local maximum, because if you go near that, anywhere near here, there's nothing else greater than that. If we pick the point over here, there is something greater. It's right here. If you pick the point right here, it's something greater. So none of those points are local maximums. Now we have a theorem, and this theorem is special and it has a name, and this is called the extreme value theorem. The extreme value theorem states the following. If our function f is going to be continuous on a closed interval, and this interval would be from the point A to B, then your function f attains an absolute max value, and we'll call that f of c, and an absolute minimum value, and we'll call that point f of d at some numbers c and d in the interval from a to b. So where c and d are in the interval a to b. So let's take a look at a couple of examples. Y equals x squared, well, that's a parabola, and so that we know that the domain is going to be from negative infinity to positive infinity, and so the absolute maxima is going to be none, because that's a parabola that goes all the way up like this, so the absolute max, there's going to be none, and the absolute min, well, there is an absolute min, and that's going to be the absolute minimum value. So if we're asking for the value, that's the y value, it would be 0, and this is at x equals 0. Now, if we're still looking at the function y equals x squared, but our domain is not negative infinity to positive infinity, we're going to look at just from the point 0 to 2. So really, if we're looking at this curve, it maybe is like some point from here to here. So we're looking at just that curve. Then it does have a maximum value, and the maximum value is going to be right at the top when x is 2. Okay, so the absolute max is when x equals 2, and if you plugged in 2 into your function, 2 squared is going to be 4. So the absolute maximum value is 4, and the absolute minimum will still stay 0, and this is at x is 0. And this is because of the extreme value theorem. Since we had a closed interval and f of x equals x squared, that's continuous. But if we weren't on a closed interval, and let's say we looked at some interval from 0 to 2, we include the point 2, but we don't include the endpoint 0, then what happens is the following. Well, 2, we still have the maximum at 2 because we included the value 2. So the maximum is 4, and that's when x is 2. But 0 is not included. So what's the lowest value we can get? We can start looking when x is, say, 0.1. We can get closer to 0. When x is 0.01, we can still get closer. When x is 0.001, and so forth. So we can get so close, but there is no exact value where we get the smallest. So in this case, there's no absolute minimum. Now we have a theorem called Fermat's theorem. And Fermat's theorem states that if f has a local maximum or minimum at some point C, and if the derivative of f at C, so f prime of C, exists, then the derivative f prime of C is equal to 0. Now, I'm not going to prove it, but if you think about it, it can sort of make sense. Taking a look at a curve, something like that, a curve like this. Well, this point right here is a local maximum. What's the slope at that maximum? Well, over here, the slope is positive, and then this is also positive. Down here, the slope is negative, and the slope is negative. And so to go from a positive to a negative slope, right here at that maximum value, the slope is 0. And so the slope, meaning the derivative of that function, is 0. And same thing for the minimum. We're going at a negative slope. We have a negative slope. And right at the minimum, the slope is 0. And so that's where we get this. F prime at C is equal to 0. So an example might be if we have the function g of x is equal to 3x squared plus 4x plus 9, find the local maxima and minima. Well, in order to do that, we'll take the derivative, g prime of x, and this is going to be 6x plus 4, and we want to find when the derivative is equal to 0. And so now we solve. So we get 6x is equal to negative 4, or x is negative 4 over 6, which is negative 2/3. Now that's the x value, and make sure when you're trying to find the local max or min, you want to find the y value. So we plug it back in. G of negative 2/3 is equal to 3 times negative 2/3 squared plus 4 times negative 2/3 plus 9. So this is going to be 3 times 4/9 plus negative 8/3 plus 9. And this simplifies to 4/3 minus 8/3 plus 27/3, which is equal to 23/3. Next, we have a definition. And this definition states that a critical number of a function f is a number C that's in the domain of f such that either the derivative f prime at c is equal to 0, or f prime at c does not exist. So if the derivative is 0, meaning it's going to be a local maximum or a local minimum, or if the derivative does not exist, that's a critical number. So let's do an example. Find the critical points for the function h of x is equal to x to the 2/3. Critical points are when the derivative is 0 or the derivative doesn't exist. So let's calculate the derivative. That is 2/3 x to the negative 1/3. Or this is going to be 2 over 3 times the cube root of x. Now the cube root can be negative because you could take, for example, the cube root of negative 27, and that would be negative 3, because negative 3 times negative 3 times negative 3 is negative 27. So that's fine. But we have something in the denominator. And so we cannot have 0 in the denominator. And so we know that if x were 0, then we'd be dividing by 0. And so 0 is our critical point, because h prime of 0 does not exist. So our answer, x equals 0, is a critical point. Now the last thing we're going to cover in this section is called the closed interval method. The closed interval method says to find the absolute maximum and minimum values of a continuous function f on a closed interval from a to b. Then we look at 3 steps. First, find the values of f at the critical points, or the critical numbers of f in the open interval a to b. Then step 2, find the values of f at the endpoints of the interval. And then the last step, step 3, then you take the largest value of the values from steps 1 and 2. So, and that's going to be the absolute maximum. And finally, the smallest of the values is the minimum, or the absolute minimum. So the smallest of the values is the absolute minimum. And so these are the steps to finding the absolute max and the absolute min. So we'll do one example and find the absolute max and min. So find the absolute max and min, and we'll just say the values, meaning the y value of our function f of x equals 8x minus x to the 4 on the closed interval -2 to 1. So what do? We first take the derivative. F prime of x equals 8 minus 4x cubed. We want to find the critical number, so we want to find when this is 0 or undefined. Well, this is going to be defined everywhere, so we'll just find out when it's 0. If we add 4x cubed to both sides, we get 8 is equal to 4x cubed, or 2 is equal to x cubed. And so therefore, taking the cube root, we get that x is equal to the cube root of 2. And substituting in, we get our y value, f of the cube root of 2 is equal to 8 times the cube root of 2 minus cube root of 2 to the power of 4. And plugging this on the calculator, this is about 7.56. Now we need to check the endpoints, and so we're checking the endpoints. F at -2 and f at 1. Well, f at -2 is going to be 8 times -2 minus -2 to the 4th. And that's going to be -32. And f at 1 is going to be 8 times 1 minus 1 to the 4th, which is 7. So what we have here is that this is the minimum value. So this is the absolute minimum. Now the absolute maximum, this was a little trick, or a trick question rather. 7.56 is greater than 7, but remember, we said that our interval had a maximum value of 1. What is the cube root of 2? Well, the cube root of 2 is a little bit greater than 1. It's about 1.26. So even though this y value is greater than here, the x value didn't fall in our domain, and so our absolute maximum was at 7. So when you do problems, make sure that your answer falls within the domain. Today we're going to talk about the mean value theorem. We'll begin with a theorem, and this theorem is called Rolle's theorem. Rolle's theorem says the following. Let f be a function that satisfies the following three hypotheses. The first one says that f is continuous on the closed interval a to b. The second criteria says that f is differentiable on the open interval a to b. And then the third criteria states that f of a equals f of b. If all three of these things are met, then we can conclude there is a number c that's in the interval a to b, so c falls between a and b, but not on the endpoints, such that f prime of c is 0, meaning the derivative of f at the point c is equal to 0. So what is this saying? Let's take a look at some examples. So if we have our function, and we have the point a and the point b, and our function f is a horizontal line, f of a equals f of b, it's differentiable in this function, and it's continuous, then there's some point in the middle, let's say right here, c, where f prime of c is 0, meaning the derivative is 0, so it has a slope of 0, and that's true because this is a horizontal line. We could have another case that looks like the following. Let's say we have the point A over here, B over here, and our graph looks something like that. This is continuous, this is differentiable, and f of A equals f of B, but this point right up here is horizontal, or it has a slope of 0. F prime of C, so our C would be right there, is 0. There's other cases that we might look at, and those cases might look something like, if you have the point A, the point B, we might have f of A, f of B look like that. We might have something like this. Now we'll have multiple places where we have f prime at C is 0, so we could have, this could be our C1, and that could be our C2. But all we're saying is that there exists at least one point C. Okay? And then finally, we could just have, for A and B, it would look like, oh, I just did that. It would, it would look the other way. And so we have that one. So let's do an example. Show that the equation x cubed plus 3x plus 1 equals 0 has exactly one real solution. So if we call this our function f of x, notice that f of negative 1 is going to be negative 1 cubed plus 3 times negative 1 plus 1, which is negative 3, and f of 0, well, that's just going to be 1. So we know we're crossing from negative to positive, and the intermediate value theorem says that if you have something that's going to be negative, and then it's going to be positive, and it's a continuous function, which this is, since it's a polynomial, it has to cross the axis. Now it could cross multiple times, but now we're trying to show that it crosses just once. Now if it did cross more than once, we might have something where it would look like this. It crosses one time, crosses 2 times, and then it goes back up, maybe even 3 times. But Rolle's theorem would say that if this were to happen, where we have these two values are equal, then we would have to have the derivative at some point is going to be 0. So let's calculate the derivative. Derivative is going to be f prime of x is 3x squared plus 3. But notice, this can never be 0. This is always going to be greater than 0 because x squared is always a positive number. And if you add 3 to a positive number, it's always going to be positive. So there's never going to be the point when it's equal to 0, which means that we can't satisfy Rolle's theorem. And thus we only have 1, 0. Now the main point of Rolle's theorem is so that we can actually use it for the mean value theorem. Now we go to the mean value theorem. The mean value theorem states the following. Let f be a function that satisfies the following. 1, f is continuous on the closed interval a to b. 2, f is differentiable on the open interval a to b. If these two hypotheses are met, then there is a number c that's in the interval a to b such that f prime of c is equal to f of b minus f of a divided by b minus a. Or we could write this equivalently as follows. If we multiplied out, we could have written it as f of b minus f of a is equal to the derivative f prime of c times the quantity b minus a. So now in order to think about this, what is the derivative? Well, the derivative is basically the slope, which is the rise over the run. So what we have is that if we have some point A and maybe some point B where it's not necessarily A, and to get from A to B, connecting the slope from A to B, we have a line that looks like this with that slope. Somewhere on this curve, right here, the derivative is not the same, not right here, but maybe somewhere right there we have a derivative where the slope is going to be the same. We might have something else. Say we have some point A over here, some point B up there, and the graph looks something like this. Connecting these 2 points, that's our slope. Maybe we'll have a point right here, as well as a point right here. So let's do an example using the mean value theorem. Take a look at the function f of x equals x squared. Now we know this is a parabola, and parabola looks something like this. It crosses at the origin. At the point 1, it's at 1. At 2, it's 1, 2, 3, it's 2 squared. It would be 4. Let's take a look at the interval from 0 to 2. It's continuous from 0 to 2. It's differentiable on the open interval 0 to 2. So the mean value theorem says that there's some point C such that f prime of C is equal to f of 2 minus f of 0 divided by 2 minus 0. Well, f of 2 is 2 squared, so 4 minus 0 squared, or 0, over 2 minus 0. So this is going to be 2. So we need to find that point C that exists. Well, what's the derivative first of all? What's f prime of x? That would be 2x. And so if we wanted f prime of c to be equal to 2, then we get that c is equal to 1. And we know that 1 is in this interval between 0 and 2. And so looking just at this graph, where the line looks like that, the slope right here at 1, 1 should also be that same slope. Now let's do a different type of example. Let's suppose that if a car accelerating from 0 takes 8 seconds to go 352 feet, its average velocity for the 8-second interval is going to be the distance, 352 feet, divided by 8 seconds. And the units would be feet per second. So this is 44 feet per second. The mean value theorem, which I'm just going to abbreviate with its initials MVT, says that at some point during the acceleration, the speedometer must read exactly 44 feet per second, or 30 miles per hour, or 44 feet per second. And that sort of makes sense. If you're accelerating, you have to pass that certain point. Now we have a theorem And this theorem states the following. If the derivative f prime of x equals 0 for all x in an interval a to b, then f is constant on that interval a to b. If the derivative is 0 for all that value, it's just a horizontal line. That's all this is saying. And finally, we have a corollary. And the corollary states the following. If f prime of x is equal to g prime of x for all x in an interval a to b, then f minus g is constant on that interval a to b. In other words, that is f of x equals f of g plus some value c, where c is a constant. Today we're going to look at how the derivatives affect the shape of a graph. The first thing we'll look at is an increasing and decreasing test. This test says that A, if our derivative, f prime of x, is greater than 0 on an interval then our function f is increasing on that interval. And then B, that if the derivative f prime of x is less than 0 on an interval, then f is decreasing on that interval. And so let's take a moment and think about this. If the derivative is greater than 0, that derivative is the slope, and if the slope is positive, it's increasing. If the slope is negative, it's decreasing. So let's do an example. If we're given the function f of x is equal to x cubed minus 12x minus 5, identify the open intervals in which this function is increasing and the intervals in which it's decreasing. Okay, so we want to find increasing and the intervals where it's decreasing. If we have a function that, say, goes up, it increases, and then it starts to decrease, that point where it changes, that's one of our critical points. So let's first find the critical points, because then that will tell us where all of these different intervals are. We take the derivative, f prime of x, so we get 3x squared minus 12. That's our derivative. To find the critical points, we set the derivative equal to 0. So we get 3x squared minus 12 equals 0. Solving for x, we get 3x squared equals 12, x squared equals 4, or x is equal to plus or minus 2. So you have two critical points at negative 2 and at 2. So if we broke off then looked at this on a number line, we would have negative 3, negative 2, negative 1, 0, 1, 2, 3, and so forth, off to positive and negative infinity. So we know we have a critical point at negative 2 and a critical point at positive 2. And since there aren't any other critical points, if we're on this side, we're either all decreasing or all increasing. And in this interval, all increasing or all decreasing. Because if we were to increase and then decrease again, going up to go down, you must have a local max or a local min. So we're all going to be the same in each of these intervals. So we have the intervals negative infinity to negative 2, negative 2 to 2, and then 2 to infinity. Now we need to figure out if we're increasing or decreasing. And that is simply just plugging a number in each of these intervals into the derivative and seeing if that derivative is positive or negative. So here, let's pick the point, for this first interval, let's pick the point negative 3. So we'll pick f prime of negative 3. So that's 3 times negative 3 squared minus 12. And that ends up being 15. So that's greater than 0. So in this interval right here, we are increasing. And then we'll pick a point in the middle between negative 2 and 2. And so let's say 0. So f prime of 0. And so that is just negative 12, which we know is negative. So that's decreasing. And finally, we pick a point between 2 and infinity. And let's just say f prime of 3. You could pick any point you want. You could pick f prime of 10. But f prime of 3 is what I'm going to go with. So we get 3 times 3 squared minus 12. And we get 15 again, which is positive. So it's increasing in that interval. So to write out our final answer, what we would say would be on the interval, let's say negative infinity to negative 2, it's going to be increasing. The interval negative 2 to 2, it would be decreasing. And then finally on the interval 2 to infinity, it would be increasing again. The next thing we'll look at is something called the first derivative test. And what this says is, suppose that C is a critical number of a continuous function f. Then the first thing, A, says that if f prime changes from positive to negative at the point C, then f has a local maximum at C. The second thing says that if f prime changes from negative to positive at the point C, then f has a local minimum at C. And so what these are saying is that if we're going from positive to negative, then we have a maximum. If we go from going down to a negative slope to a positive slope, we have a minimum. And then finally, C, the third thing, says that if f prime is positive to the left and to the right of C, or if it's negative to the left and right of C, then f has no local maximum or minimum at C. So if the slope is positive on both sides of C or negative on both sides of C, then it's not a maximum or a minimum. So let's do an example. Find the critical points of f of x equals x to the 1/3 power times x minus 4. Now, we could use the product rule, or what we could do is just multiply this out, and this would be x to the 4/3 power minus 4 x to the 1/3 power. Now, in addition to finding the critical points, let's also identify the intervals which f is increasing and decreasing, and find the function's local and absolute extreme values, meaning the maximum and minimum. So the derivative f prime of x is going to be 4/3 x to the 1/3 power minus another 4/3 x to the negative 2 power, or 2/3 power. And I got this 4/3 by multiplying 4 times 1/3. So to find the critical points, we set the derivative equal to 0. We set that equal to 0. And so now solving for this, we can get rid of the 4/3 by, let's say, dividing everything by 4/3. And so we get x to the 1/3 power minus x to the negative 2/3 power equals 0. Now to solve this, what we're going to do is we're going to factor out an x to the negative 2/3. So if we factored out x to the negative 2/3 from x to the 1/3, what we would get would just be x. Because x to the 1 times x to the negative 2/3 is x to the 1/3 minus 1 equals 0. So this is x minus 1 over x to the 2/3 equals 0. So now, solving for x, we get x is equal to 1. That's the zeros. But also, note that we have an x in the denominator. And so that means that x equals 0 is a critical point, because a critical number is when the derivative is 0 or the derivative does not exist. So these are our two critical numbers. So now we're going to go ahead and make some space. And we're going to draw the number line. And that number line, so our numbers are 0 and 1, so we'll start with a point less than that at -1, 0, 1, and we'll go ahead one more to 2. Remember, our derivative, f prime of x, is equal to 4/3 times x to the 1/3 power minus 4/3 x to the negative 2/3 power. And we're going to have 3 intervals. The first interval is going to be from -infinity to 0. The second interval will be from 0 to 1, and then the third will be from 1 to infinity. So for this first interval, we'll pick a point in that interval. Let's say -1. So we'll check out f prime of -1. And so we get 4/3 times -1 to the 1/3 minus 4/3 times -1 to the negative 2/3. We get -8/3, which is negative. So on this interval right here, we have, since it's negative, it's decreasing. And then we'll pick a point between 0 and 1. Let's just say f prime of 0.5. If we were to plug that in, we get that that is also going to be negative. So this is less than 0. And since it's less than 0, it's still decreasing. So just because we have a critical point, that doesn't necessarily mean that it's a max or min, or that it changes signs. And then finally, we'll pick a point in the interval from 1 to infinity. How about 2? If we're to plug this in on a calculator, we get that that is greater than 0, so it's increasing. So here we have the intervals where it's increasing and decreasing, and we have a local max or min when it changes from increasing and decreasing. So right here, where it changes from decreasing to increasing, we get that 1 is a local, it's going to be a max or min. So if you go from going down to going up, we have a local minimum. So we have the local minimum at x equals 1. And so the value of that, plugging in f of 1, what we get is f of 1 is -3. So that's the value of the local minimum. So we've looked at what the first derivative tells us. Now we'll take a look at what the second derivative tells us. But first we'll begin with the definition. And this definition states that if the graph of f lies above all of its tangents on an interval, let's call this interval I, then we say it's called concave upward on that interval I. And then similarly, if the graph of f lies below all of its tangents, on an interval I, then it is called concave downward on that interval I. So what does that even mean? So let's take a look if it's concave up. So if we have a graph that looks like this, and this is our graph f, where are all the tangent lines? The tangent line goes this way, tangent line goes this way, the tangent goes this way, and so forth. And each of those tangents, f is going to be above the tangents. Now if we have a graph that goes like this, let's call this graph G, we'll have a tangent that goes like this, tangent that goes like this, tangent that goes like this, and in each of these cases, G, our function, is going to be below the tangents. And so this first one, this is concave up, and this is concave down. So now we know what the definition of concavity is. Let's actually figure out how we test for it. So the concavity test goes as follows. We're going to first A, if you take the second derivative, f double prime of x, and if that derivative is greater than 0 for all x in that interval I, then the graph of f is concave upward on your interval I. And then B, if the second derivative of f is less than 0 for all x in the interval I, then the graph of f is concave downward on that interval I. So let's do an example. If we have the curve y equals x cubed, now that graph, you may be familiar with that. The cubic function looks something like this. So let's figure out when it's concave up and concave down. So if we call this our function f of x, the first thing we do is take the first derivative, f prime of x, so we get 3x squared. And then we take the second derivative, f double prime of x, and so we get 6x. And we want to find when this derivative, this second derivative, is going to be positive or negative. Well, we know that this derivative is going to be positive when x is going to be from 0 to infinity. As long as x is positive, the second derivative is positive. Your second derivative is negative when x is between negative infinity and 0. So it's going to be concave up. So that tells us it's concave up. Concave up from 0 to infinity. Concave down from negative infinity to 0. So taking a look at here, from 0 to infinity, we see it does have that upward motion, or the upward appearance, and then we have that concave down from 0 to negative infinity. We'll do another brief example, and this is the curve f of x equals x squared. We know this is the parabola. So we take the first derivative, f prime of x is 2x, and the second derivative is just going to be 2. Well, we know 2 is always greater than 0. If that's always greater than 0, then this curve is always concave up, meaning it's concave up from the interval negative infinity to infinity. And take a look at this. This is always going to be concave upwards. Now we have another definition. And what this definition states is a point P on a curve y is equal to f of x is called an inflection point if f is continuous there, so at that point, and the curve changes from concave up to concave down, or vice versa. So, or changes from concave down to concave up. So as long as the concavity is changing, then we have an inflection point. So now, if you recall from the example that we had just done, where we had y is equal to x cubed, at 0, the graph of this, it went like that, and it went like this. In this region, it was concave up. In this region, it was concave down. And so that point where it changes from concave up to concave down, that is the inflection point. Right here where it changes from concave up to concave down. So you can kind of see it right there drawn on the graph. And finally today, we're going to talk about the second derivative test. The second derivative test states the following. Suppose f double prime of x, so the second derivative, is continuous near the point C. Then we have two things. If f prime of C is 0, So if the first derivative is 0, meaning it's a critical point, and the second derivative at the point C is greater than 0, so meaning it's concave up, then f has a local minimum at the point C. And then B, if f prime of C is 0 and f double prime of C is less than 0, then f has a local maximum at C. So what does this represent? If we were to have a curve, and say we have a curve that looks like this, f prime at C is 0, so the derivative is 0. So these 2 points we have derivatives, and the derivatives are 0. Now we look at the second derivative. Is it concave up or concave down? Well, right here it's concave down. So if it's concave down, then it has a maximum. Right here it's concave up. So if it's concave up, meaning second derivative is positive, then it's a minimum. And also you may notice about right here, the concavity switches. That's the inflection point. It goes from downward to upward. And finally, if the second derivative is equal to 0, well then this test doesn't really tell us anything. It could be a local max, it could be a local min, or it could be neither. So we don't really know. So let's do an example. F of x is equal to x to the 4 minus 4x cubed plus 10. We'll take the first and second derivative. First derivative, we get 4x cubed minus 12x squared. The second derivative is 12x squared minus 24x. To find the critical points, we want to set the first derivative equal to 0. So we get 4x cubed minus 12x squared equals to 0. We can factor out 4x squared, and we're left with x minus 3 equals 0. So we have critical points are x equals 0 and x equals 3. Plugging these 2 points into our second derivative, we get f double prime of x. We'll put in the first point 0, so f double prime of 0 is just going to be 0. Well, that doesn't really tell us anything, but that's all right. We plug the second point, f double prime of 3, in, and then what we get is we get 12 times 3 squared minus 24 times 3. We get 36, which is positive. So if the second derivative is greater than 0, meaning it's concave upward, so we have something like concave upward, that means it's a minimum. So x equals 3 is at the minimum. Today we're going to talk about the limits at infinity as well as horizontal asymptotes. So we begin with an intuitive definition of a limit at infinity. Let f be a function defined on some interval. Let's call this interval a to infinity. Then the limit as x goes to infinity of f of x equals L means that the values of f of x can be made arbitrarily close to the value of L by requiring x to be sufficiently large. Now, another notation for this, you might see instead of the limit as x goes to infinity of f of x equals L, you might also see f of x goes to L as x goes to infinity. Now, what this all means is essentially if we have some curve, let's say, so that's our x-axis and our y-axis, and let this be the line y equals L. We may have the graph do something like this, but eventually it'll get very, very close to L. So this is an example as x goes to infinity, your function f of x. So this is y equals f of x is L. You might see something else. You might see something like, again, where this is L, the function might look like that. Or even something that oscillates. So we might have something where this is, so this is our x, y, and that's the line L. We might have something that does this. But it does get closer and closer and closer to L. Next, we have a definition. This says that let f be a function defined on some interval negative infinity to a. Then we write the limit as x goes to negative infinity of f of x is equal to L, and likewise this means that the values of f of x can be made arbitrarily close to L by requiring x to be sufficiently large in the negative sense. And so what that could look like graphically would be, we have x and y, and this is the value L, and our graph might come like that, going towards L all the way negative. Now we have a third definition. And this definition states the line y equals L is called a horizontal asymptote of the curve y equals f of x if either 1. The limit as x approaches infinity of f of x equals L, or the limit as x approaches negative infinity of f of x is equal to L. So we're going to do an example, and our function f of x is equal to x cubed minus 2 divided by the absolute value of x cubed plus 1. The graph of this looks something like the following. And so what we can see is that the limit as x goes to infinity of this function, as it goes to infinity, we approach 1, and the limit as x goes to negative infinity, we approach negative 1. Now we have a theorem that says if r is greater than 0 is a rational number, then the following. The limit as x goes to infinity of 1 over x to the r power is equal to 0. And then we have if r is greater than 0, and this is a rational number such that x to the r power is defined for all x, then the limit as x goes to negative infinity of 1 over x to the r is equal to 0. And so thinking about this for a moment, this can make sense. If we have x, some x in the denominator, and raised to a very large power, your denominator is getting very, very large, and 1 over a large number is very small. And so as this goes to infinity, this goes towards 0. And similarly, in this case, a negative number raised to a very large negative number raised to a power, as x goes to infinity, or negative infinity rather, that also goes towards 0. Now let's do an example. Let's calculate the limit as x goes to infinity of the quantity 5x squared plus 8x minus 3 all over 3x squared plus 2. So what we're going to do here is we want to have our x on a denominator. So for each term in here, we're going to divide by x squared. That's the largest power. So this becomes the limit as x goes to infinity, and we're going to divide every single term by x squared. So 5 x squared divided by x squared plus 8x divided by x squared minus 3 over x squared all over 3x squared over x squared plus x squared, plus 2 over x squared. And then this will equal the limit as x goes to infinity of, well, 5x squared over x squared is just going to be 5 plus 8 over x minus 3 over x squared all over 3 plus 2 over x squared. Now we can actually take the limit and of each of these individual components, and so this is equivalent to the limit as x goes to infinity of 5 plus the limit as x goes to infinity of 8 over x minus the limit as x goes to infinity of 3 over x squared is all divided by the limit as x goes to infinity of 3 plus the limit as x goes to infinity of 2 over x squared. And so now this is equal to this first limit. Well, it's just a constant. This right here is just going to be 5. Now this, according to the theorem that we have, x is raised to the power 1, and so that's a positive power. That means this is going towards, as x goes to infinity, this whole limit is going to be 0. Same thing for this, and same thing for down here. And this is just a constant, so that's going to be 3. So this is going to be 5 plus 0 divided by 3 plus 0, and so your limit here is 5/3. Alright, we'll do one more example. And so let's compute the limit as x goes to infinity of the quantity x minus the square root of x squared plus 16. Well, what do we do here? It may not be apparent at first, but what we're going to do is multiply by the conjugate. And we're going to multiply by the conjugate over itself. So we get x squared plus 16, and then divided by x plus the square root of x squared plus 16. And so this becomes the limit as x goes to infinity of, and the numerator becomes x squared minus, and the square root times itself is just x squared plus 16 all over x plus the square root of x squared plus 16. And this simplifies, the numerator simplifies, our x squareds will cancel, and so this is the limit as x goes to infinity of negative 16, don't forget the negative, divided by x plus the square root of x squared plus 16. And now, the limit, notice that this denominator is of some power, x being positive, and so this is just going to be 0. And that's your limit. Now we're going to take a look at what happens if we have something like the limit as x goes to infinity of f of x, and if this equals infinity. So this is used to say that if our function f becomes large as x becomes large. Okay, similarly, we might also have the limit as x approaches negative infinity of f of x, and that could be infinity. Or we could have the limit as x goes to infinity of f of x is negative infinity, or the limit as x goes to negative infinity of f of x is negative infinity. So an example of this might be if f of x is equal to x cubed. We know x cubed is the function that looks something like this. And so the limit as x goes to infinity of f of x, or of x cubed, is going to be positive infinity. But the limit as x goes to negative infinity of x cubed, looking at the graph, that goes to negative infinity. Now, we'll do another example right here. And if we have the limit as x goes to infinity of the quantity x squared minus x, if we were to use the law of limits, and I'm actually going to show you the wrong way, so I'm going to write it in red. The wrong way of doing this would be using the law of limits, and so this is the limit as x goes to infinity of x squared minus the limit as x goes to infinity of x, and so this is infinity minus infinity. We cannot do this because infinity is not a number. There's no number infinity. You can't take infinity divided by 2, for example. So this is wrong. We don't do this. What we can do is the following. We can actually factor out an x. So this is the limit as x goes to infinity of the quantity x times x minus 1. And now, because we're multiplying two things, this limit is going to be infinity. Both of these terms, x and x minus 1, as x gets larger, they both become arbitrarily large, and so therefore their product also becomes large. Today we're going to talk about a summary of all the ways that we can sketch curves. The first thing we can do is look at the domain. Okay, the domain is all the possible x values that we'd use. The second thing is to look at the intercepts. And they include both the x and the y-intercept. To find the x-intercept, that's when it crosses the x-axis, you set y equal to 0. And to find the y-intercept, you set x equal to 0. The next thing we do is you check for symmetry. Looking for symmetry, we want to see if f of negative x equals f of x. If that's the case, then the function is going to be even. An even function is when it's symmetric about the y-axis. For example, you might have something that looks like this, and then it symmetric like that. And so this is really if f of negative x equals f of x. And then we check if f of negative x equals negative f of x. In this case, this would give us an odd function. Okay. An odd function, the graph of an odd function looks like reflected over the x-axis and then reflected again over the y-axis, like that. And the third type of symmetry we might get is a periodic function. That is, if we have f of x plus p is equal to f of x for some positive constant p. Right? That's where we have our period. For example, trig functions, the graph of y equals sine of x repeats forever. It's periodic. And now, I'm going to move up a little bit. The next thing we're going to look at is asymptotes. So D would be asymptotes. We have different types of asymptotes. The first one we'll discuss is horizontal asymptotes. Horizontal asymptotes are found usually when we take the limit as x approaches infinity of f of x if that limit is some L, or if we take the limit as x approaches negative infinity of f of x and it equals some value L, then that implies the line y equals L is a horizontal asymptote. The next type of asymptote we have would be the vertical asymptote. And the vertical asymptote is if we're taking the limit as x approaches some value a from, say, the right of f of x, if that equals infinity, or if the limit as x approaches a from the right of f of x is negative infinity, or the limit as x approaches a from the left of f of x is infinity, or the limit as x approaches a from the left of f of x is negative infinity. So any one of these, if the limit is going to be infinity as we approach a number from the left or right, then that means that the line, so in this case we had the line y equals L is horizontal asymptote, we get x equals a is the vertical asymptote. There's another type of asymptote that we have, and this is called a slant asymptote. Another name for a slant asymptote is an oblique asymptote, but we'll discuss this another time. Now the next thing that we look for would be E. We're going to look at the intervals of increase or decrease. And this is where we take the derivative, we find f prime, and if f prime of x is positive, it's increasing, and if the derivative f prime of x is negative, then we're decreasing. Then, step F, you look for the local maximum and minimum values. To do this, first we find all the values of f that are critical numbers. Okay? And if you recall, critical numbers are when the derivative f prime of x equals 0, or when the derivative f prime of x does not exist. And then to determine if it's a local max or a local minimum, you take the first derivative test, and if your function is increasing before the critical number and then decreasing afterwards, so if it's increasing before and then decreasing after, we have a local max, or if it's decreasing and then increasing, we'd have a local min. And then step G, you check out the concavity and points of inflection. So concavity and the points of inflection, we're going to take a look at the second derivative, f double prime of x. If your second derivative is greater than 0, then if it's greater than 0, then it's going to be concave up. If the second derivative is less than 0, it's concave down. When it changes concavity, so going from concave up to concave down, or from concave down to concave up, that's our inflection point. And then the last thing, h, now that we have all this information, we sketch the curve. So now let's do an example using all the steps that we have. Sketch the curve y is equal to 2x squared divided by x squared minus 1. So, following our steps, step A, what's the domain? Well, the domain is all real numbers. And in fact, I'll write it as all real numbers except for 1 or negative 1. I'll write it in interval notation. Negative infinity to negative 1, negative 1 to 1, and then 1 to infinity. Okay, now step B. Next we find our intercepts. And so for the intercept, to find the y-intercept, we set x equal to 0. And if x is 0, well, y is also 0. So we get 0, comma 0. And then to get the x-intercept, well, for the x-intercept, we'd set y equal to 0. And in this case, the x and y-intercept is the same. It's 0, 0. Now we could check for symmetry. In this case, if we put negative x into f of x, we get 2 times negative x quantity squared divided by negative x quantity squared minus 1. Negative x quantity squared is just x squared, so this is 2x squared divided by x squared minus 1, which was our original function. This was f of x. So this is telling us that this function is even. Next we'll check for the asymptotes. We'll check for vertical and horizontal asymptotes. To check for the horizontal asymptote, we're going to take the limit as x goes to plus or minus infinity of our function 2x squared divided by x squared minus 1. If we took this and we divided both the numerator and denominator by x squared, what we get is just 2 on the numerator, and on the denominator dividing by x squared, well, x squared divided by x squared is 1, and then 1 divided by x squared is just going to be 1 over x squared. So this is 1 minus 1 over x squared. And now you can see as x goes to infinity, this goes to 0, and so we're left with 2 over 1, or just 2. So that tells us we have a horizontal asymptote at y equals 2. To find the vertical asymptotes, notice that the denominator is 0 when x is plus or minus 1, and this is also coming from our domain, where x couldn't be negative or positive 1. And so if we looked at the limit, we get the limit as x approaches 1, let's say from the right side of our function 2x squared divided by x squared minus 1. Well, this is going to be infinity. And then if we also took the limit as x approaches 1 from the left side of 2x squared over x squared minus 1, this is negative infinity. So this tells us we have a vertical asymptote at x equals 1. And similarly, if we went for negative 1, we get the limit as x goes to negative 1 from the right of 2x squared over x squared minus 1. That's also going to be infinity. Excuse me, it should be a negative infinity, rather. And then this limit as x goes to negative 1 from the left of 2x squared over x squared minus 1. That's positive infinity. So we have a second vertical asymptote at negative 1. All right, we're almost there. Bear with me. E, well, let's first take the derivative, f prime of x. And here we're going to have to use the quotient rule. Okay, so the denominator, x squared minus 1 times the derivative of the numerator, 4x, minus the numerator, 2x squared times the derivative of the denominator, times 2x divided by the denominator squared. This actually simplifies to negative 4x over x squared minus 1 quantity squared. Now, since the denominator is always going to be positive because it's squared, we can just look at the numerator. When is this derivative positive? And when is this derivative negative? Well, f prime of x is going to be positive when x is less than 0. That means when x is less than 0, it'll be increasing. And f prime of x is negative when x is greater than 0. And so that's where we're going to be decreasing. Of course, keep in mind that x can't be 1 or negative 1 because it's not in the domain. Now we're going to find f, which is our local max and minimum values. So we have our derivative over here. That will tell us our critical points. The critical points are when the derivative is 0. So that first one, the numerator is 0 when x is 0, so that's the first critical point. And the critical point also occurs when the derivative is not defined. So when our denominator is 0, our denominator is 0 of the derivative when x is 1 or when x is negative 1. Plugging in all these, we get f of 0, f of 1, and f of negative 1. F of 0 is 0. F of 1 and f of negative 1 is undefined, so they're not a local max or a local min because it's not even in the domain. So we have just f of 0 equals 0. Now this could be a local max or a local min, and so we need to determine which one it is. Now we can use the first derivative test, so we'll pick a point just to the left of it. We'll pick a point, let's say 0.5 or negative 0.5. So if we're on the number line, we're at negative 0.5, 0, and then 0.5. Putting these points into our derivative, f prime of x, or rather f prime of negative 0.5. So the derivative at negative 0.5 and the derivative at 0.5. And we're going to determine if the derivative goes from increasing to decreasing or decreasing to increasing. This gives us something like approximately 3.556 and negative 3.556. And so if we're going before, our derivative is going to be positive And then after 0, our derivative is negative. So since we're changing, this tells us that we have a local maximum. So this is a local max. And the very last thing, last step that we got to do is take the derivative of the derivative, or the second derivative. And if you recall, so our first derivative, f prime of x, was equal to negative 4x over x squared minus 1 quantity squared. Determining concavity, we need to have the second derivative. And so here we go. We're going to take the denominator, which is going to be x squared minus 1 squared times the derivative of the numerator times negative 4 minus the numerator. So minus a negative 4 is a plus 4x times the derivative of the denominator. And this is where it's going to get pretty ugly. So we're going to have to use the chain rule. Derivative of the denominator is going to be 2 times the quantity x squared minus 1 squared times the derivative of the inside, 2x, all over the denominator, which is x squared minus 1 quantity squared, squared. So if you have a squared squared, it'd be raised to the 4th power. Now, all this simplifies, and thankfully it simplifies, and what we end up with is the following. We end up with 12x squared plus 4 divided by x squared minus 1 cubed. Oops, and I just realized this should be to the power 1. Now, if we're determining concavity, if it's concave up or concave down, notice the numerator. This is always going to be positive because x squared is positive, 12 times the positive number is positive, and if you add 4, so this is always going to be positive. So we're only really concerned about this denominator, this x squared minus 1. So we want to see x squared minus 1. When is x squared minus 1 going to be positive? Well, x squared minus 1 is positive only if x is going to be greater than 1 or less than negative 1. So if x is greater than 1 or x is less than negative 1, it'll be concave up. Well, it'll be positive. This is positive, which means this is positive, which means the second derivative is positive. So it's concave up for there. And this is a less than and not a 2. So that's where it's concave up. And when x is between negative 1 and 1, it's concave down. Alright, now we're going to have to try and put all of this together into a graph. So I have everything right here. So let's see what we got. Going through the steps, so we have right here, x cannot be 1 or negative 1. We have an intercept right here at 0, 0, 0, the origin. Looking at c, it's going to be an even function, so we only need to draw half of it, and the other half would be reflected. Now we have part D. These are telling us right here, these are telling us all the limits, and that gives us a horizontal asymptote of 2. These limits give us a vertical asymptote at negative 1 and positive 1. But taking a look at these limits a little bit more careful, what we get is the following. We get, as we go to negative infinity, the limit is 2. So as we go out to negative infinity, we're going to be at 2. And as we go out to positive infinity, we're also going to be at 2. And then we look at the vertical asymptote. These vertical asymptotes say, as we approach So I'm just going to look at the negative 1 right now. So if we approach negative 1 from the left side, it's going to be infinity. So as we approach negative 1 from the left side, it'll be infinity. And we're going towards 2. So we can sort of fill in our gap like that. Knowing that this is an even function, we would get the mirror image, something to be like that. And then the limit as x approaches negative 1 from the right side is negative infinity. So we'd be down here, negative infinity, going upwards. And we'd be going upwards because right here, step E says we're increasing as long as x is negative. So we're increasing. And we're going to keep increasing until we hit this local maximum, 0, 0. So we're going to keep increasing until we hit the local maximum. Local maximum means then it goes around, it turns back, heading downward. And we can see, taking a look at just a reflection, we get something like that. And we can verify the way that we drew it, because as we draw these curves, instead of the curve looking like something funky, we know it's sort of smooth like this, meaning it's concave down when we're between negative 1 and 1. And over here, that's a concave up, and that's also a concave up. And that's how we draw our curves. Today we're going to talk about optimization problems. There are a couple of steps to solving optimization problems. The first thing is to read the problem. Read the problem and understand it. Second thing you want to do is draw a diagram. Okay, so we're reading the problem, we're asking ourselves, what's the unknown? What are we given? What do we want to find? Those types of things. We draw the diagram. These often help us with these types of problems. And then the third thing, introduce notation or variables. For now, let's say what we're trying to optimize, trying to maximize or minimize, let's call that Q. Then, step 4, what we want to do is we're going to express Q in terms of some other symbol. Or whatever unknown quantity or other quantity that we have. And we'll keep doing this until we only have just one variable. So say Q is just a function of x or something to that effect. And after we do that, the last step, step 5, is to basically find the absolute maximum or minimum. I didn't finish my 5 right there, so step 5 would be find the absolute max or minimum. And we'll use one more test that will help us, and this is the first derivative test. For absolute extreme values, meaning maximum and minimum. And what this says is that suppose that c is a critical number of a continuous function f defined on an interval. A says that if the derivative f prime of x is greater than 0 for all x that's less than c, and the derivative f prime of x is less than 0 for all x greater than c, then we conclude that f of c is the absolute maximum value. And b, well, let's just back up for a minute. So if the derivative is greater than 0, so we're increasing for all some values, and then the derivative is less than 0, we're decreasing, we have an absolute max. And then if the derivative f prime of x is less than 0 for all x less than c, and f prime of x is greater than 0 for all x greater than c, then f of c is the absolute minimum. Let's do an example. So we have an open top box, and it's made by cutting small squares out of the corners of a 12 by 12 inch tin. Okay, so if we have a square like this and it's 12 inches by 12 inches, but we cut off the corners like this, and then we fold these tabs upwards. So we were to fold this tab up, this tab up, this tab up, and this tab up, what we would get would be a box where the tabs would go up like that, those tabs will go up, and so forth. The tabs that were once out here, they get brought up like this, and so we have our box. So what we have is we have 12 inches by 12 inches, and we cut small squares out of the corners. What I want to know is how small should these squares be so the box holds as much as possible. Okay. In other words, what we're trying to do is we're trying to maximize the volume of the box. Now we're trying to figure out what these squares we're cutting out of, and so let's call these squares, the length of these squares, x. And so let's try and figure out the formula for the volume of this. So what is the volume? Well, if this whole length is 12, what is this length? That's really just this smaller piece. And we took a side x off and an x off, so this new length is 12 minus 2x. And so this whole square is going to be 12 minus 2x by 12 minus 2x. And how high is this? This height is going to be x. So the equation for volume as a function of our x is going to be our height x times 12 minus 2x by 12 minus 2x, or 12 minus 2x quantity squared. And we can go ahead and write this all out. We'll expand this so we get 144 minus 48x plus 4x squared, or 144x minus 48x squared plus 4x cubed. So we're trying to maximize this, maximize the volume. So let's go ahead and take the derivative. And one thing to note before we take the derivative, remember this whole thing has a length of 12. So if we have x and x, keep in mind that we can't have a negative length, so x can be at most 6. Otherwise, 12 minus 2x would be negative, and you can't have a negative side. So taking the derivative, dv dx, we get 144 minus 96x plus 12x squared. If we want to maximize this, we're going to set this equal to 0 and find the critical points. So we'll set this equal to 0. And what do we get? Well, we can factor out 12. So we get 12 times the quantity, 12 minus 8x plus x squared equals 0. We can factor this one more time. So this is 12 times the quantity, 2 minus x times 6 minus x equals 0. And so therefore our critical points are x equals 2 and x equals 6. But remember, if x equals 6, then we wouldn't have any length. So we can go ahead and disregard this one point. So x equals 2 is how much we'll have to cut off from each side. 2 inches. Now these optimization problems have a lot of application in business and economics. So in these types of problems, you might say define some r of x to be the revenue. You might say c of x would be the cost, and then p of x would be your profit. And so we'd say p of x would be the revenue, what you make, minus the cost. And if you want to maximize your profit, then you find this function and take its derivative. Now for the in economics, the derivative of r, economists tend to use the term marginal revenue, marginal cost for the derivative of the cost, and marginal profit for the derivative of the profit. Today we're going to talk about Newton's method. The goal of Newton's method for estimating a solution for an equation is to provide a sequence of approximations that approach the actual solution. This is what goes on inside a computer or calculator when it tries to find the solution to an equation. In Newton's method, we wish to solve some sort of equation, f of x equals 0. And so if we're to graph something like this, let's just say our function, if it's x and y, this is our function f of x right here. And we want to find when it's 0, so basically the x-intercept. What we do with Newton's method is we begin by just picking some point on this curve. And so let's say this point is the point x1, comma, and then our y value would be f of x1. So this is the point x1 right here. That's straight down. And we're trying to find this point right here. Let's just call that point R. Now if we consider the tangent line to this curve at x1, that tangent line looks something like this. The tangent line will cross down, and we'll say that point will be x2. Okay, so the tangent line of at this curve, we'll call this L1, and it crosses the axis at x2, or just L. To find the formula for the tangent line L, we use the equation y minus our y1 value, and so this is our points that we're using. So the y1 value is really f of x1 is equal to the slope. So we're using the formula y minus y1 equals m times x minus x1, where our slope is really our derivative. So that's f prime at the point x1 times x minus x1. So this is the equation of that line, but we know that line, when it crosses right here at that point, that's at the point x2 comma 0. That's at the point x2 comma 0. So we can plug x2 comma 0 into this equation. So what we get is 0 minus f of x1. So we're plugging in x2 in for x and 0 in for y. So this is 0 minus f of x1 equals f prime of x1 times x2 minus x1. Now doing some rearranging of terms, we can solve for x2, and we get that x2 is going to be x1 minus f of x1 divided by f prime of x1. So now given just some initial point that we picked on this graph, f of x, we can now get this point x2. And notice, this point x2 is going to be closer than our original x1 is to where it crosses the axis. Now let's go ahead and draw another diagram. I'm going to make this one maybe a little bit bigger. So we had our point, this is the point x1, comma, f of x1. This is x1. Right here, that's r, we have our x and y. This is the graph of f of x. We found the tangent line right here. Tangent line crossed. At this point, this is our point x2. So now if we move x2 up to the line, we have another point, x2 comma f of x2, and we'll do the same thing. We'll find the tangent line right there, and it crosses, and we'll get another point x3. Each time we're getting closer and closer. And then from x3, we'll move up, find that, and then they'll get closer and closer and closer. So what would x3 be? Well, using the exact same method we did, we would have found out that x3 was equal to x2 minus f of x2 divided by f prime of x2. So this leads us to the formula for Newton's method. If we have that the derivative does not equal to 0, we can find the nth approximation. So this one right here would be the second approximation. The one that we did above to find x2 would have been the first approximation. And so to find the nth approximation, what we would do is we assume that f prime of x sub n is not equal to 0. Then we're given, and I'll go ahead and change my marker for this. We're given that x to the n plus 1 is equal to x to the n minus f of x to the n over f prime of x to the n. This is Newton's approximation, and we can do this to help us approximate our zeros. And if we do it more and more, we'll get closer and closer and closer towards r. We started off way out here at x1, then we moved, our x2 got a little bit closer, x3 we get closer, and we can get on and on and on. So let's do an example. So if we wanted to find an approximation for the square root of 2, what we would have to do would be to approximate the 0 of f of x is equal to x squared minus 2. So if we wanted to find when this is equal to 0, you could see, manipulating this, we would find that x is equal to 0. Or is equal to the square root of 2. So this is the function we're going to deal with. We need one piece of information, and that's the derivative. So f prime of x, and this is equal to 2x. So now Newton's method will say that x to the n x sub n plus 1 is equal to x sub n minus our f of x, which is x squared minus 2, but remember we're dealing with x sub n instead of just x, so this is x sub n squared minus 2 over the derivative, 2x, or 2 x sub n. Now I'm going to go ahead and just simplify this. I'm going to break up this fraction into two fractions. So we're going to get x sub n squared over 2x sub n. And now we're doing a minus 2. So minus a minus gives us a plus 2 over 2 sub x n. And this simplifies, we get x sub n minus, here our xn cancels, so we get xn over 2 plus, and then our 2's cancel, 1 over x sub n. And we can combine the first two terms. 1 minus a half is just a half. So x sub n over 2 plus 1 over x sub n. This is our approximation that we'll be using in this example. Now, we do know, because we have calculators, what the exact value or a good approximation of the square root of 2 is. And so if we were to calculate square root of 2 to 5 decimal places, we get the square root of 2 is equal to 1.41421. Okay, so we're going to have this, and now let's start computing. It'd be nice if we kind of knew where to begin, and we can sort of figure out that the square root of 2 is going to be between 1 and 2, because we know that the square root of 4 is 2 and the square root of 1 is 1. So we know this, the square root of 2 is between the square root of 1 and the square root of 4. So we know the square root of 2 is between 1 and 2. So we'll have to pick some number. At least that gives us a ballpark area. We're not picking the square root of 2 is approximately 100. So let's start off with x sub 1 is equal to, or x sub 0, our very first thing, is equal to 1. Then plugging it in, what do we get into this equation? So plugging this in, we get into our formula x sub 1, which is x0 over 2 plus 1 over x0, which is 1/2 plus 1 over 1, we get 1.5. And then for the next term, x sub 1, well, x sub 1 we found is 1.5. So we get x sub 2 is going to be x1 over 2 plus 1 over x sub 1, which is 1.5 over 2 plus 1 over 1.5, and this gets 1.4166, repeating forever, and we'll call this 667. And then we'll do x sub 3 would be x sub 2 over 2 plus 1 over x sub 2, which is equal to 1.41667 over 2 plus 1 over 1.41667, and this would give us 1.41422. So we only did a couple of calculations. We started when x is 0, when x is going to be 1, then we got 1.5, 1.41667, and we got 1.41422. Remember, the square root of 2 is 1.41421. And so we could take a look at the error that we had. And so if our value for x0 is 1, x1 is 1.5, x2 is 1.41667, and x3 is 1.41422, the error we get is going to be the first one we're off by 0.41421, and this is negative. Then the next error we got 0.08579, we're getting better. And then we get 0.00246, and then we get 0.00001. 5 digits of accuracy. So this is Newton's method, and we use it to get approximations, and sometimes, in this case, we got an approximation by just using a couple of calculations. Today we're going to talk about antiderivatives. We'll begin with a definition. A function, capital F, is called an antiderivative of the function little f on an interval I if we have capital F prime of x, the derivative of that is equal to little f, and this is going to be for all x in the interval I. So what this is saying is, before, if we had some function little f and we took the derivative f prime, that would be its derivative. Now we're going the other way. We're taking the antiderivative. And this often happens when we have some function little f, or we're going to call it capital F prime, and we know the derivative, but we don't know what the original function was. And so we'd take the antiderivative, and that's what we would get capital F. So let's do an example. If our function f of x is equal to 2x, what's the antiderivative? Well, in this case, we need to think about what function whose derivative is equal to 2x. Well, if you remember, our original function would be x squared. The derivative of x squared is 2x. Similarly, if we have a function g of x is equal to cosine of x, what would its antiderivative be? The derivative of what is cosine? Well, the derivative of sine is cosine. So in this case, sine of x is the antiderivative of cosine, and x squared is the antiderivative of 2x. In the same way that 2x is a derivative of x squared, or cosine is a derivative of sine. But let's say we have functions, f of x is, let's say, 5x plus 4. The derivative of this is 5. But if we also had another function, g of x, who was 5x plus 80, the derivative of g is still 5. So they're both going to be the same. The derivatives are the same as long as we have the constants can be different. And then the rest of the terms are going to be the same. So the 5x's are the same, it's just the constants would be different. So this leads us to a theorem. If capital F is an antiderivative of f on an interval I, then the most general antiderivative of f on I is the following. It's going to be capital F of x, but we're just going to add some c plus c because it doesn't really matter as long as c is a constant. So where c is an arbitrary constant. Because if we took the derivative of capital F, or rather of this whole thing, the derivative of all of this, the derivative of capital F becomes f prime, which is the antiderivative, and the derivative of c is 0. Now let's do another example. Find the most general derivative, or antiderivative, excuse me, of f of x equaling x to the n. Well, we're doing the power rule, and if we're taking the derivative of, say, x to the 4th power, that would be 4 times x to the 4, or excuse x to the 4 minus 1. So if we're going this way, taking the derivative, we're subtracting 1 and multiplying by that power. If we're going to go the other way, then what we would do is we would, instead of multiply, we would divide, and instead of subtracting 1, we would add 1. So we would add 1 up here and divide by that power. And we can test this. What's the derivative of this? Well, the derivative, capital F prime, is going to be the power times our function to the n plus 1 minus 1 power. So n plus 1's cancel, and we're left with just x to the n, which is what we started with. So this leads us to a series of antiderivative formulas. But before we do that, I forgot that I was asking for the most general antiderivative, and so that would be a plus c. And so we'll have a function, and then we'll have the particular antiderivative. So if our function is some constant c, lowercase c, times our function f of x, then the particular antiderivative is still c times times our capital F of x. If we're adding two functions, f plus g of x, then what we get would be the sum of two antiderivatives, capital F of x plus capital G of x. If we have the power rule, n to some power, and we're going to assume in this case n is not equal to -1. If we have this, then we get x to the n plus 1 over n plus 1. That's our antiderivative. If our function is cosine of x, then the antiderivative is sine of x. But what about sine of x? The derivative of what will be sine of x? Well, the derivative of cosine is sine, so really using this first formula, so the derivative of cosine is negative sine, so we would take the negative, and this would be negative of cosine of x. If secant squared of x is our function, the antiderivative, the derivative of what would be secant squared? Well, if you recall, the derivative of tangent is secant squared. And then the derivative, or the antiderivative of secant times tangent of x, well, that antiderivative is secant, because the derivative of secant of x is secant tangent. So let's do an example. Find the general antiderivative of the function f of x is equal to 3 times the square root of x plus, let's say, sine of x. Well, we can rewrite this. So this would be, instead of writing it as a square root of x, we'll write it as x to the 1/2 power plus sine of x. And so the antiderivative of this is, we have two different things, so we can take the antiderivative of each one separately. And so the antiderivative of 3 to the x, 3 times x to the 1/2 would be 3 times the antiderivative of x to the 1/2. The antiderivative of x to the 1/2 would be x to the 1/2 plus 1 divided by 1/2 plus 1 plus the antiderivative of sine. Well, antiderivative of sine is negative cosine of x. And since we're taking the general antiderivative, we're going to add plus c. So here we get 3 times x to the 3/2 divided by 3/2 minus cosine of x plus c. But this 3 and 3/2, well, we can simplify. If we're dividing by a fraction, it's the same as multiplying by the reciprocal. Okay? So now we multiply by the reciprocal, our 3's cancel. So this is just 2x to the 3/2 minus cosine x plus c. Now, an equation that involves derivatives in the original function is an equation that we call a differential equation because they have differentials in them. And usually these differential equations will have some sort of initial condition so that we can figure out what that c value is, that constant we get. So let's do an example. Now recall that if we're dealing with something like s of t, and that's the position, then the derivative of your position, s prime of t, is going to be your velocity. And the derivative of the velocity, or the second derivative of position, so the second derivative is the derivative of the velocity, which is acceleration. And so if we were to work backwards, the antiderivative of acceleration would be velocity, and the antiderivative of velocity is position. All right, so now let's do this example. We have a hot air balloon is ascending at a rate of 12 feet per second and is at a height (80 feet) above the ground. And when it's at 80 feet above the ground, this is when a package is dropped. What I want to know is how long does it take the package to reach the ground. So in this case, we're going to start with the velocity. And so we're going to call the velocity v of t. And I'm going to change my color to blue for the solution, just so that we don't get confused, because there's a lot of words here. Now, the acceleration due to gravity is 32 feet per second squared. And this is for acceleration on Earth. The gravity on some other planet is going to be different. Okay, so the acceleration due to gravity is 32 feet per second squared. So we have a of t equals 32. Now, if we're going up, then gravity is pulling you down, and so we'd write negative 32. And I'm just going to drop the units. Okay. So that's our acceleration. Now, acceleration, and we're going to refer to all these right here, but I'm not going to have it on the screen. So acceleration is really the derivative of velocity. So that's really v prime of t. So let's figure out what v of t is. We want to find the antiderivative. So v of t, the velocity, is the antiderivative of negative 32. Well, it's just negative 32, and so the antiderivative of negative 32 would be negative 32t, because taking the derivative of negative 32t is just negative 32. Now when we take the antiderivative, we're going to add a plus c. We get this constant. So here we have our velocity in terms of time is negative 32t plus c. Now we think about our initial condition. So this right here, initial condition, initially, when time was 0, what is our velocity? So our velocity was negative 32 times 0 plus c, but we were in a balloon that was going up in the air. The initial velocity of the balloon was 12. Because we're moving up, we are ascending at 12 feet per second. So this allows us to be able to figure out what c is, so we can evaluate c, and so our constant is 12. So our new, and let me just change colors for this. So our velocity equation for that is going to be v of t is negative 32t plus 12. So that's our velocity. Now we're trying to find the position, because we want to figure out what's the position function. So to find that, we know that the position, well, before I do that, let me just back up one more step. Velocity is the same as the derivative of the position. So velocity is the derivative of the position. So we can figure out what's the position, s of t. We take s of t by taking the antiderivative of the velocity. So the antiderivative of negative 32t is negative 32, antiderivative of t, using the formula we have, you add t to the power, this is already really t to the power 1, so you do t to the power 1 plus 1, which is 2, over 2 plus, now we're going to have 12. The antiderivative of 12 would be 12t. And now we're going to have another constant when we take the antiderivative. So let's call this constant, since we've already used c, we'll call this constant d. So now we have an equation for s of t, but we still have a constant. Now we use our initial condition, and so if we remember back from the equation, initially the package was dropped at a height of 80 feet. So moving back down to here, initial condition we're going to have initial height, s of 0, is going to be 80 feet above the ground. In fact, we can simplify this because we have negative 32 divided by 2. So let me just write it down here. S of t is going to be negative 16t squared plus 12t plus d. And so plugging in our initial condition, s of 0, we get 0 plus 0 plus d is equal to 80. So we know d is 80. And now we can figure out what's the formula for height. So the formula for the height is going to be negative 16t squared plus 12d. And we had plus d before, but now we know d is going to be 80. So this is the equation for the height. What we wanted to do is we wanted to find what's the time when the package hits the ground. So what we want to do is we want to find what is t when your height is equal to 0. So we're going to set 0 equals to negative 16t squared plus 12t plus 80. And so we can solve this, maybe say using the quadratic formula or your graphing or however you like to solve equations, and we get that t is going to be negative 12 plus or minus the square root of 12 squared minus 4 times negative 16 times 80 divided by 2 times negative 16. And so this would give us that t is approximately negative 1.89, or t is approximately 2.64 seconds. Now we can't have a negative time, so we rule that out. And so we get for our answer, it takes about 2.64 seconds to hit the ground. Today we're going to talk about areas and distances. So let's first take a look at the curve y is equal to 1 minus x squared. If we were to plot that, what that graph looks like is something like this. So if this is 0.5 and we have 1, and so 1 minus x squared, that is a parabola facing down whose vertex is up at 1. So we have this, something like this. It crosses down here at the point 1. So now given this, how can we figure out what's the area under this curve? What is this area? Now we know how to find areas of nice geometric shapes like a rectangle or a triangle, but this is neither of those shapes. What we can do is we can make an approximation, and we can say, well, let's sort of break this off into two different rectangles. And so we'll pick the point right here, and we'll go across. We have something like this. And then, again, at this point right here, we'll go across, and we'll go back down. And so shading, what we'll get is we'll have two rectangles. But the thing is, this is an approximation, but it's a bigger approximation because this area right here and this right here, we're counting that in our approximation, and that doesn't fall in there. So in fact, maybe I should have colored this a different color. So this is all the extra shading, and that shouldn't belong there. Can we do a better approximation? Sure. So let's try. So instead of using two different rectangles, let's make 4 rectangles. And each of these rectangles is going to be equidistant. So this is going to be 0.25, 0.5, 0.75, and 1. And so we're going to go ahead, start up here, go across. We hit that. And then each time I'm going to start at the left, wherever this line touches our curve, I'm going to start right there. So we go ahead, go across, then we go up. Take that point, go across, up, and then go across and up. So now we have 4 rectangles that's approximating this, and this is getting a little bit better. So you see the error is better, it's not as much. And I'm going to draw our first approximation. So our first approximation actually went all the way up here and went all the way over here. And if we were to shade that, that first approximation had a much larger error, all of this area. So that's a pretty big area. Our second approximation, the error is just these areas. So we got a little bit better. We no longer had this as our error. So we're improving. Could we do better? Sure, let's just make more rectangles. So if we made more rectangles, so each of these rectangles would have a distance of 0.125 instead of 0.25, so 0.125, then what that would be is we'd have this first one, and now we'd go over here, and then following this, we go up, and actually I'm going to change my color for these lines. Okay, we have that, go right here, and then we keep having each of these. And so again, you're going to see our error is getting better and better and better. So now the error that we get is far better than ever before. Let me use a darker shade. So each of these errors is smaller and smaller, so we are getting more and more accurate. So compared to our first approximation where we used 2 rectangles, this is much better. And then we used 4 rectangles, it got better, now we're using 8 rectangles, and we can use more and more and more. And we get better and better and better each time. So, just redrawing this on a clean slate, so we get y is equal to 1 minus x squared. This point right here is the point 1 comma 1, and if we had split this up, and let's just do 4 approximations. So we have 1, or 4 rectangles rather. We have 2, 3, and then 4 approximations. Now this approximation, we're going over, so we're missing over too large of an area by that. Now this approximation, we're going to be using, for each of these rectangles, we're using the left-hand endpoint, and we're using 4 of these. So we're going to call this L4 for the left-hand approximation, left endpoint approximation, using 4 rectangles. So let's calculate what L4 is. We're going to approximate, or we want to calculate the area of each of these rectangles. Well, the width, so if our total distance was 0 to 1 for the x values, and we split it up into 4 pieces, then we know that each of these right here, each rectangle, has a width of 0.25. 0.25, 0.25, and 0.25. So now we need to figure out what's the height. Well, if our function f of x is 1 minus 2x, we're going to figure out, go all the way up, and we just plug in your left endpoint. So this one is 1, 1. We knew that. This was, or you could have thought of it as 1, comma, f of 1. This point right here is going to be 0.25, comma, f of 0.25. This point right here is going to be 0.5, comma f of 0.5. And then this point is going to be 0.75, comma f of 0.75. And so the area of a rectangle is base times height. So we're going to have 0.25 times f of 0. And excuse me, this is not 1, 1, this is 0, 1. So f of 0 plus another base times height for our second rectangle is 0.25 times f of 0.25 plus 0.25 times f of a half. And finally, plus 0.25 times f of 0.75. So I'm going to sort of move this over a little bit, and what we get is we get 0.25 times, well, the first value would be 1, plus, let me going to use fractions. 0.25 is 1/4 times 15 over 16, that's a times and a minus, plus 1/4 times 3/4, and then plus 1/4 times 7/16. I got each of these numbers by evaluating f of those values. F of 0.75 is 1 minus 0.75 squared, and we end up with 7/16. So adding this all together, we're going to get that the area is equal to 0.875. Or rather, this should be the L4. Well, we took the left-hand approximation. We can do the same thing. We can do a right-hand approximation. So we have our f of x is equal to 1 minus x squared. We have x and y. This is our point 1. We've got another point 1 right here. So we can still split it up into 4 segments. But instead of starting at the left and then going across, we would start at the right. So each of these intervals, each of these rectangles would go up, and then we'd go across. And here we'd go up and across, up and across, and well, right here that's already touching, so we don't need to go up at all, and we go across. But you may notice by doing the right-hand approximation, we're missing out on some areas right here. In fact, this is a pretty big area. So the left-hand approximation, we had overestimated, now we're underestimating, but that's all right. I mean, these are our approximations. And so this would be our R4 approximation, 4 rectangles using the right-hand approximation, or the right endpoint. And so each of these is going to be a width of 0.25, just like the last screen. So our first rectangle is going to be width is 0.25 times the height is going to be f of 0.25, since we're using the right part of this endpoint. Then we're going to use this next one, plus 0.25 times f of 0.5. This second rectangle, the right hand is going to be right there, plus 0.25 times f of 0.75. And then finally, this last rectangle is 0.25 times f of 1. But in this case, f of 1 is 0, so that would have gone away. Now, we could do another approximation. Okay, this is f of x is 1 minus x squared. Now, instead of doing a left or right approximation, what we could have done is at each interval, use the midpoint, go halfway up. And so I guess this graph shouldn't be there. It's a little sloppy, but we go about halfway up. All right, what we do, that's going to be our interval. We take the midpoint from here to here, and then we go up again. Take the midpoint, go up. And as you can see, by doing this, we're going to have some areas where we're overestimating, but we also have some areas where we underestimate. And so this midpoint approximation cancels it out. So this would be the midpoint approximation. We'll call it M4. Each of these still has a width of 0.25. So they all have widths of 0.25, but these midpoints is now going to be the midpoint. That's 0.125. This midpoint right here is going to be 0.375. This midpoint is 0.625. And then this midpoint is 0.875. So we would have midpoint approximation. We get, for our first rectangle, plus our second rectangle, and then our third rectangle, we'd get this, and plus 0.25 times f, 0.878. So these would be the approximations we get for our midpoint. So if you're trying to approximate the area under this curve, this is y is equal to 1 minus x squared, you can use, oh, that's pretty bad axis, you can use rectangles. And let's say we're just going to use the right rectangle. Using 2, we got a pretty bad area, we're missing a lot. Using 4 rectangles, we're getting a little bit better, but we still have quite a bit of error. If we use 8 rectangles, we're getting better. If we use 16, we're getting even better. We're getting closer and closer and closer the more rectangles we get. So if we then use more, we use 32. And so the more and more intervals we use, the better our accuracy. So now let's create a table. So the first column on the table is going to be, I'm just going to clear this all the way out. The first column on the table is going to be the number of sub-intervals that we have. Number of subintervals. And then if we use, say, the left hand or the right hand or the midpoint, so we'll have our right approximation. So the number of subintervals, we'll say that that's going to be our n, and then we have our right approximation, and then we have our midpoint approximation, and we have our left-hand approximation, L sub n. And if you remember, I'll sketch it right here. If we're doing the left-hand approximation, that's going to be over guessing because we have all this extra right here. And then if we do the right-hand approximation, we're underguessing. Okay, so and then the midpoint might balance it out. You have a little bit more in some spots. You'll have a little less in other spots. So like this interval right here, you overestimate it, but then you underestimate it, so that might cancel out. So if we have just two subintervals, the lower sum is going to be 0.375, or the right-hand sum. The midpoint is going to be 0.6875, and then the left-hand sum is 0.875. If we have four subintervals, we're going to get 0.53125. We're going to get 0.671875, and then 0.78125. And so if you notice, the left hand is going to be a larger number than the right hand, and then the midpoint should fall somewhere in between. Okay, let's go up to 16 intervals. And so the right hand approximation is going to be 0.63476. We'll stop. We'll do one more 6. The midpoint is going to be 0.66699. And then the left hand approximation is 0.697. I'm going to stop it at 3. Alright, so these numbers are getting closer to each other. If we went up to, let's say, 50 subintervals, then we'd get 0.6566, we'd get 0.6667, and then 0.6766. You might be able to see that these numbers are approaching something, but if not, we'll do a little bit more. 100 intervals, we'll get 0.66165, 0.66675, and then 0.6716. And if we say went up to 1,000, we would get 0.6661665, 0.6666675, and then 0.6671665. All right, and again, each of these values would have been computed by multiplying the width of each subinterval times the height, which would have been our function at either the left, midpoint, or right-hand side of that interval. And then taking the sum of all those. So this last one would have been taking the sum of 1,000 rectangles. So we notice that this is approaching, if we took infinite one, is going to be approaching 2/3. And so what we would say is the area is equal to the limit as n approaches infinity of r sub n, the right-hand approximation. But this is also equal to the limit as n approaches infinity of the midpoint approximation, mn, and the limit as n approaches infinity of ln. So we can get our area by taking the infinite limit. But this would mean we'd have to take the infinite sum of infinite rectangles. Now, let's just study some arbitrary curve like this. So this is y is equal to f of x. And let's find the area under this curve. So we have x and y, and let's just start from some point A to B. Let's divide this up into n intervals. And so we'd have We'll call this S1, S2, S3, and we'd have a bunch of ones in between. We'll have some arbitrary interval in the middle. We'll call this S sub I, and then a very last interval would be S sub n. So in between we have a bunch of stuff. So we start off, our first point will be A, and then we're going to start labeling each of these values. We'll call that x1, then we'll call this one x2, call this x3, so at the end of each section. So Si, the end of Si would be x sub I. But what about at the beginning of Si? Well, that's just the one before it, so that would be x of x, or xi minus 1. And then finally, the beginning of our Sn would be x sub, well, if this is the nth one, the start of it would be x of n minus 1. And I'm just going to put a couple of dots in between here so we know that there is maybe some arbitrary space. Well, what's the interval? What's the gap or the width of each of these rectangles? We'll call it delta x. Well, delta x is going to be, well, how far is the whole thing? The distance is going to be, or the length is b minus a. And if we're breaking it up into n intervals, then that length, b minus a, divided by n, is how long each of these intervals would be. So now, how do you figure out what's the value of x1? Well, x1, if we started off at a, and this interval has a length of delta x, x1 is a plus delta x. But what about x2? Well, x2, we started off at a, we added a delta x, and then we added another delta x. So x2 is going to be a plus 2 times delta x. x3 would be a plus 3 times delta x, and so forth. And so now, what we can do is we can figure out the approximation. The right-hand approximation, r sub n, for this would be the of each rectangle is length times height, or length times width. Delta x times our height. And so the height would be f of whatever x1, x1 or x2 and so forth. And we have our x1, x2 right here. So r sub n would be f of x1 times delta x. And remember, we're using the right-hand approximation. So for our first rectangle, we're using the right hand. The second approximation, we're going to use that right hand. So plus f of x2 times delta x plus f of x3 times delta x plus so forth. And I sort of ran out of space, so let me go up one more line. Plus dot 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 plus f of xn times delta x. So this leads us to our first definition. The definition says the area of the region, and we'll call that region S. And this is the region that lies under the curve or under the graph of the continuous function f is the limit of the sum of areas of approximating rectangles and here we go. Here's the formula. It's going to be area is equal to the limit as n approaches infinity of r sub n. And so if r sub n is what's written above, then this is really the limit as n approaches infinity of the following. F of x sub 1 times delta x plus f of x sub 2 times delta x plus so forth all the way to our last term, f of x sub n times delta x. And that's how we find the area under the curve. Now another way to write this infinite sum, is using something that we call sigma notation. Sigma notation is going to be as follows. If we're taking the sum, and we're taking the sum of f of x1 plus f of x2 plus f of x3 and so forth, instead of writing it all out, what we can do is write a sigma, like this, sigma, and we'll say some index number, some I goes from 1 to n, and we'd say f of x sub I times delta x. And what this means is that I is going to go from 1 all the way up to n, and so when I is 1, this is f of x1 times delta x plus, and then you move up in number. This now becomes, I becomes 2, and so this is f of x2 times delta x plus f of x3 times delta x all the way up to n. Now let's take a look at something called the distance problem. We know that distance is equal to velocity times time, because velocity is distance over time. So if you multiply both sides by time, distance is velocity multiplied by time. So let's say we're driving in a car and we don't know the odometer reading, but we do know how fast we're going. We do know our velocity. And so if we knew our velocity at certain time, we could figure out how far we've traveled. So let's say we're going to have time, and the unit for time is going to be in seconds. And then we're going to have our velocity. And the unit for velocity is going to be feet per second. So we start off when we start taking a look at our recordings at time is 0. So we're moving, you start the timer, time 0, we're going 25 feet per second. And then after 5 more seconds, we take a look and we're traveling 31 feet per second. And then after 10 seconds, we're traveling at a speed of 35 feet per second. In 15 minutes, then we're going to travel 43 feet per second. 20 seconds, we'll travel 47. 25 seconds, it'll be 45. And then at 30 seconds, we're traveling at 41 feet per second. How far have we traveled? Well, if we were to plot this, it would look something like we have a bunch of rectangles, and it starts to look like what we had before when we're finding the areas. So it goes up for the first 5 intervals, we're counting 25, 31, 35, 43, 47, and then it starts to go back down a little bit, 45, and then 41. This is not this graph is not entirely accurate, but it's close enough. So to figure out how far we've traveled, distance is velocity times time. And so if we're using, say, the left-hand approximation, which is kind of what I drew right here, then the distance traveled is going to be, so for the distance, that's going to be, we're using the left-hand approximation, so that's our delta x is 5 times our height, which in this case we didn't need to figure it out because it's already given, as opposed to figuring out what f of x sub 1 is or so forth. So 5 times 25 plus 5 times 31 plus 5 times 35 plus 5 times 43 plus 5 times 47 plus 5 times 45. And so calculating all this, we get 1,130 feet. Now, if we were to instead use the right-hand approximation, so in this case, the left-hand approximation leaves us, we're underestimating. If we did the right-hand approximation, we would overestimate. So let's just do that, the right-hand approximation. So it'll be 5 times our first rectangle. Using the right-hand approximation, we're going to start off with the second value. So 5 times 31 plus 5 times 35 plus 5 times 43 plus 5 times 47 plus 5 times 45, and then the last point plus 5 times 41. And what we get here is we get 1,210 feet. So we knew that we were a little bit over, but this is sort of an approximation. We don't know exactly how far we went in each interval. In between we could have sped up at the very end or sped up early, but we don't know. But this leads us to the equation for distance. And that is, distance is equal to the limit as n goes to infinity of, and we're going to use sigma notation, the sum, where I goes from 1 to n, of f of t, and this is sub I minus 1. So we're doing the left-hand approximation times delta t. Or if we did the right-hand approximation, this would have been the limit as n goes to infinity of the sum where I goes from 1 to n of f of t sub I times delta t. Today we're going to talk about the definite integral. So we'll begin defining what is the definite integral. If f is a function defined for x being between a and b and including on the endpoints, then we divide the interval a to b into n subintervals. And each of these subintervals are going to be of equal width. And we'll say that equal width is going to be called delta x. And if you remember from before, delta x is going to be b minus a divided by n. Now, if we let x0 be our first point A, and then we have x1, x2, so forth, all the way to the last point x sub n, and that's going to be equal to our b. And so b the endpoints. So each of these are the endpoints of the subintervals. Not intervals, but rather subintervals. And we let these points x1 star, x2 star, and so forth all the way to xn star. And we're going to say these are going to be any sample points. And so sample points really are just the points that can be the left endpoint or the right endpoint. And so we might want to pick sample points that would make sure that we're getting a pretty good approximation. Half of that is going to be above and half of it's going to be below. If you notice sometimes before, if we just did the left approximation, we might overestimate everything or underestimate. So sample points are something that allow us flexibility. So if these are sample points in the subintervals, so that x sub I star, so for some arbitrary I, this lies in the ith subinterval from x sub I minus 1 to x sub I. So we're not done just yet. And then we say, then we say that the definite integral of f from A to B, this definite integral is going to be defined to be the following. So this is not an s, this is an integral sign. The integral from A to B of f of x times dx, and this is the limit as n goes to infinity of the sum, where I goes from 1 to n, of f of x sub I star times delta x. So we have all this, and this is provided the limit exists. And gives the same value for all possible choices of sample points. If this does not exist, we say that if it does exist, so if it does exist, then we say f is going to be, and the definition here is integrable and it'll be integrable on the interval a to b. This definition is something that we call a Riemann sum. And Riemann sum is spelt R-I-E-M-A-N-N. So this is Riemann sum. And so just a note, this right here, this is the integral sign. And then if we're dealing with something like this, the integral from a to b of f of x dx, we're going to say that f of x is the integrand a and b are the limits of integration, a is the lower limit, b is the upper limit, and then we're always going to have this dx. It just simply indicates that the independent variable that we're dealing with is x. And so the whole procedure of calculating an integral, this is what we call integration. And again, this dx just tells us that that's the variable we're dealing with. We could have been dealing with another variable, say like the integral from a to b of f of t. And if t is our variable, then we would say dt. Or if it's r, it would be dr. So we have a couple of theorems. The first theorem says, if f is continuous on the interval a to b, or if f has only a finite number of jump discontinuities, then the function f is integrable on a to b. That what this means is, so that is the definite integral the integral from a to b of f of x dx exists. The next theorem states, if f is integrable, all right, and now we know how to find if it's integrable from the previous theorem. So if it's integrable on the interval a to b, then we have, I'm going to change my pen for this, we have the integral from a to b of f of x dx, which is equal to the sum where n, or excuse me, the limit, not the sum, but the limit so it's equal to the limit where n goes to infinity of the sum where I goes from 1 to n of f of x sub I times delta x. And this is where we have that delta x is b minus a over n, and our x sub I is really our starting point a plus I times delta x, depending on which rectangle or which subinterval we're dealing with. All right, let's do an example. If I'm given the limit as x, excuse me, not as x, but as n goes to infinity of the sum where I goes from 1, this is a terrible sum, let me rewrite that. The sum where I goes from 1 to n of the quantity x sub I cubed plus x sub I times sine of x sub I times delta x. Write this as an integral on the interval 0 to pi. Well, if we wrote this as the integral, this would be the integral from 0 to pi of the inside stays the same, so it's still going to be the same function, so except x sub I is just going to be replaced with x. So x cubed plus x times sine of x. And then when we finish this, we want to make sure we're integrating with respect to our variable x. So we put times dx. Now I'm going to go over some formulas and rules to help evaluate integrals. So the first one is the sum where I goes from 1 to n of just I, meaning we're taking I, or 1 plus 2 plus 3 plus 4, so forth, all the way to n. This is actually can be written as n times n plus 1 over 2. The next thing is the sum where I goes from 1 to n of I squared. So again, this is 1 squared plus 2 squared plus 3 squared all the way to n squared. This is n times n plus 1 times 2n plus 1. This is all over 6. The next formula we have is the sum where I goes from 1 to n of I cubed, and this is the quantity n times n plus 1 all over 2, this whole quantity squared. Now, here are some rules that would help us when working with sigma notation, and that is the sum where I goes from 1 to n of c. Well, c doesn't relate to I. So it's basically we're adding c n times. We're adding c plus c plus c, whereas before, so like in this case, this number changed. They went from to whatever I was changing to, but there's no I, so it's just c plus c plus c n times. So in other words, this is just n times c. If we have the sum where I goes from 1 to n of c times some a sub I, well, that c is a constant, so we can just say it's c times that whole sum. Let me rewrite my sigma notation. Times the sum where I goes from 1 to n of a sub I. Now we can do another one. So the sum where I goes from 1 to n of the quantity a sub I plus b sub I, we can split this up into two different sums. The sum where I goes from 1 to n of a sub I plus the sum where I goes from 1 to n of b sub I. And similarly, if we're subtracting, the sum, not n, but the sum where I goes from 1 to n of a sub I minus b sub I is going to be the sum I goes from 1 to n of a sub I minus the sum where I goes from 1 to n of b sub I. Alright, now let's do an example. Evaluate the Riemann sum for f of x equals x cubed minus 6x. And we'll use our endpoints a to be 0, b to be 3, and then we're going to pick n is going to be 6. So if n is 6, what's our delta x? So this is all what's given. So delta x is going to be our b minus a over n, which is 3 minus 0 over 6, or it's going to be 1/2. So if our right endpoint is a0, so our x sub 0, which is a, is 0, then the next point x1 is going to be, so we're going by 1/2, it's going to be 0.5, x2 is 1.0, x3 is 1.5, x4, 2.0, x5 is 2.5, and then x6 was our endpoint b. So x6, which is b, is really 3.0. So the Riemann sum, R6, is going to be the sum where I goes from 1 to n, or 1 to 6 rather, of f of x sub I times delta x. So we're going to get our first will be f of 0.5 times delta x plus f of 1.0 times delta x plus f of 1.5 times delta x plus f of 2.0 times delta x plus f of 2.5 times delta x plus f of 3.0 times delta x. And so, giving me a little bit more space, and remembering our function f of x is x cubed minus 6x. And so this all can be simplified. Since delta x is really 1/2, I'm going to factor out delta x from everything. And so we get f of 0.5 ends up being negative 2.875. F of 1 is negative 5. F of 1.5 is negative 5.625. F of 2 is negative 4. F of 2.5, so now we're getting to positive numbers, and that's 0.625. And then f of 3 ends up being 9. So this whole thing, we get negative 3.9375. And what you notice is this is actually a negative number. Well, if we were to have graphed this, what this would have looked like, something like that. And so we did pick a couple of points right here, our first rectangle, our second rectangle, our third rectangle, our fourth rectangle, and then our fifth rectangle comes positive, and then our sixth rectangle is also going to be positive. But if we're below the axis, then it's a negative value. And so that's why most of this is going to be below, and so we end up with a negative Riemann sum. Now, continuing on this example, calculate the integral from 0 to 3 of x cubed minus 6x dx. Well, what's our delta x going to be? The delta x is b minus a over n, and so b is 3, a is 0, so b minus a over n is 3 over n. We started off our x0 was 0. Our x1, if we're going at intervals of 3 over n, is 0 plus 3 over n, or just 3 over n. Our x2, we add another 3 over n, so it's going to be 6 over n, and so forth. x3 would be 9 over n. So in general, we'd get x sub I is equal to 3i over n. And this is since we're using the right endpoints. Well, since we're using the right endpoints, rather, we can write that this integral is equal to the limit as n goes to infinity of the sum, where I goes from 1 to n, of f of x sub I times delta x. And now we can fill in, we know what x sub I is, and we know what delta x is, so this is the limit as n goes to infinity of the sum, where I goes from 1 to n, of x sub I is going to be 3i over n times delta x. Our delta x is going to be 6 over n. And so now we know we can start filling some things out. Excuse me, not 6 over n, 3 over n. So using what we know, 3 over n does not relate to I, so we can pull this whole thing in front of the sigma, in front of the sum. So we get the limit as n goes to infinity of 3 over n times the sum where I goes from 1 to n. And what's f of 3i over n? Where our function was x cubed minus 6x. So this is going to be the quantity 3i over n cubed, 3i over n cubed minus 6 times 3i over n. Now you're probably thinking this is not the nicest thing, and you're probably right, it's not that nice. So this is going to be the limit as n goes to infinity of 3 over n times, now we'll go ahead and factor out inside here, or multiply. So this becomes 3i over n cubed, 27i cubed over n cubed minus 18i over n. Now we're subtracting two sums, or we're taking the sum of the subtractant. And so because of this difference, we can split this up into two summations. And when we split this up, this 27 over n squared and this 18 over n, they don't deal with I, so we can pull them out. So this is going to be 27 over n squared times the sum where I goes from 1 to n of I cubed minus 18 over n times the sum where I goes from 1 to n of just I. Now we know what the sum, we know this sum, and we know this sum. So let's keep forging ahead. This is the limit where n goes to infinity of 3 over n times the quantity 27 over n squared times, now this we know to be n times n plus 1 over 2 quantity squared. Oops, this should have been an n cubed way up here. That should be an n cubed, and that should be an n cubed because that was 3i over n quantity cubed. So sorry about that. And then minus 18 over n times, and then the sum where I goes from 1 to n of I, this is n times n plus 1 over 2. And I'm going to go ahead and I'm going to multiply this times this, and just 3n times that right there. So we get the limit as n goes to infinity of, we have 81 over n to the 4th times, squaring this, we also have an n squared, n plus 1 squared, and this is going to be divided by 4, minus, and we get 54 over, let's see, we have n out here. So 3 times 18 is 54, and n times n would be n squared. And then we still have times n plus 1 over 2. So we can still simplify some more. So doing that, we get the limit as n goes to infinity of, we get, from this first term, we can pull out the constants, 81 over 4. And now, let's see, this n squared and this n to the 4th cancels, so that'll be n over n squared. And so that's going to be n plus 1 over n squared. And in fact, we could do a little simplification. Yeah, so we get n plus 1 squared over n squared minus 54 times, 54 over 2 rather. So back that up. Sorry, we get 27 times n plus 1 over n squared. Still not the nicest thing, but remember, we're taking the limit as n goes to infinity. So we're almost there. This is going to be the limit, n goes to infinity, of the quantity 81 over 4. And this factor is n squared plus 2n plus 1 over n squared minus, and this is 27 times the quantity n squared plus n over n squared. And so this all becomes the limit as n goes to infinity of 81 over 4 times the quantity, and this is going to be 1 plus 1 over n, excuse me, 2 over n plus 1 over n squared minus 27 times, and then we get 1 plus 1 over n. All right, almost there. The limit as n goes to infinity, well, if n goes to infinity, this term goes to 0, this term goes to 0, and this term goes to 0, and we're almost there. So this is going to be 81 over 4 minus 27, which is negative 6.75. So this is what that area is under the curve that looks something like this. So we have that area and this area, more negative than positive, but that's what we got. And it was way better than our estimate using the Riemann sum, where we got negative 3.9375. I'm sure if we did the Riemann sum where we found a lot more, it would be a lot better. So if we did Riemann sum for 40, we get negative 6.39998. If we did when n is 5,000, we'd get pretty close, negative 6.7473. So you think about this, this was a very long method to do this problem, but it sure beats calculating when n is 5,000, doing 5,000 summations. Now let's do an example. Remember, calculating the area or calculating the integral of something is basically finding the area under that curve. So if we're trying to calculate the area under the curve of 1 minus x squared dx, and we're going from 0 to 1, or in other words, the integral from 0 to 1 of the square root of 1 minus x squared, that is the same as finding the area. So rather than actually going through and trying to calculate this, sometimes it's just useful to draw what that looks like. Well, what is this? If we had y is the square root of 1 minus x squared, if we squared both sides, we get y squared is 1 minus x squared, or x squared plus y squared is 1. So it's a circle centered at the origin with radius 1. And since this is the square root, meaning our y value is only going to be positive, so we can ignore this stuff below the axis. And then our x is going from 0 to 1, so really we're just going to be going from 0 to 1, so we're just concerned with this right here. This is 1/4 the area of a circle. So the area is 1/4 pi r squared, and since r is 1, this is just pi over 4. So we can calculate the area, or the integral from 0 to 1 of the square root of 1 minus x squared dx is pi over 4. Let's do another example. What about the integral from 0 to 3 of the quantity x minus 1 dx? Well, again, we're just trying to find the area under curve. So if we were to graph this, this is going to be at negative 1 at 0. It crosses the axis at 1. And it goes up. And when x is 3, your y value is going to be 2. What we have here are two triangles. We'll call these two triangles A1 and A2. If it's below the axis, it's negative. If it's above the axis, it's positive. Well, A1 is going to be, it's negative, but what is the area of the triangle? 1/2 base times height. So 1/2, 1 times 1. So that's A1, and this is going to be just negative 1/2. A2 is 1/2 base times height, so this is 2 by 2. And so this is going to be 2. So the integral is just this, negative 1/2 plus 2, and we get this is going to be 1.5. So sometimes calculating the areas or the integrals, not as bad as the last example we had did. Now, calculating the integral using the midpoint rule. The midpoint rule says the integral from a to b of f of x dx is equal to the sum, where I goes from 1 to n, of f of x sub I, and we're going to use bar, x sub I bar times delta x. And what this is delta x times f of x1 bar plus so forth all the way to f of xn bar. So this is, we're going to say our delta x is the same, b minus a over n, and our x sub I bar, that's the average, or the midpoint. So it's going to be 1/2 of the left part of the subinterval, so x sub I minus 1 plus x sub I, taking the averages of this. So in other words, midpoint of the interval x sub I minus 1 to x sub I. Now we're going to go over some properties of the definite integral. The first property says that, and let me change my ink right here. So the first property says the integral from, normally we go from a to b, so the integral from b to a of f of x dx, so if we're going backwards, this is negative the integral a to b of f of x dx. So if we go backwards, then it changes. Okay. What about if your a and b are equal? So this is the integral from a to a of f of x dx. Well, you don't have any area. There's nothing to go under since it's just a single point. So the integral is 0. Alright, so here's some more properties. The integral from a to b of just some constant c dx, well, that's just c times b minus a. Okay, this is where c is a constant. So if you think about that, constant, if we looked at the picture, the constant is just a horizontal line. So if you're from a to b of a horizontal line, we have a rectangle. Area of the rectangle is base times height. The next property we have, the integral from a to b of the sum f of x plus g of x dx. Well, this is really the integral from a to b of f of x dx plus the integral from a to b g of x dx. If we have an integral from a to b of some constant times your function f of x dx, this is just the constant times the integral from a to b of f of x dx. Again, c is the constant. If we have the integral from a to b of the difference f of x minus g of x dx, this is the integral from a to b of f of x dx minus the integral from a to b g of x dx. Now the fifth one, if we have some, let's say, looking on like a number line, if a is over here, b is over here, and c is in between, and you go a to c, and c to, so you go from a to c and then c to b, it's the same as going all the way. In fact, this works where c doesn't even need to be between a and b. C could be on the outside, but we get the following. The integral from a to c of f of x dx plus the integral from c to b of f of x dx is equal to the integral from a to b of f of x dx. And now we have a couple of properties where we compare the integrals. And so this first property says that if f of x is greater than or equal to 0, this is for a being less than or equal to x being less than or equal to b, then the integral from a to b of f of x dx, so if our function is always going to be a positive, then the integral will be positive. If we have f of x is greater than or equal to another function g of x for a less than or equal to x less than or equal to b, then we have the integral from a to b of f of x dx will be greater than or equal to the integral from a to b of g of x dx. And then if m is less than or equal to f of x, which is less than or equal to capital M for a is less than or equal to x is less than or equal to b, then we have that m times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to capital M times b minus a. And really, what we did right here was we took the interval, or the integral, of little m and of capital M, but using that property, property 1, the integral is just that. Today we're going to talk about the fundamental theorem of calculus. So the fundamental theorem of calculus states the following. If we have some function f and it's continuous on some closed interval a to b, then we have that the function g, and this function g is going to be defined by the following, where g of x is equal to the integral from a to x of f of t dt, and we have x is going to be between a and b. So if this is what we have, and now we're dealing with our function, it's g of x, and x goes right here, but really this integral is integrating over t. So our function is f of t and dt. So it's not f of x, like how it's g of x, it's f of t. So if we have this, then the function g of x, defined by that, is continuous on the interval a to b, and it's differentiable on the interval, the open interval, a to b, and we have the following. We have that g prime of x is equal to f of x. So if we were to take the derivative of this right here, taking that derivative of g prime is just going to give you f of x. So this derivative, this whole integral will give you f of x. Now think about this. This is mainly dealing with something related to t. the only x in here, so if we're taking the derivative with respect to x, the only x is going to relate to right here. And so the derivative of the integral, so going backwards, is just going to give you your f of x. Okay, now let's do some examples. Let's use the fundamental theorem of calculus to find the derivative dy dx if a, y is equal to the integral from a to x of the quantity t cubed plus 1 dt. So using the fundamental theorem of calculus, dy dx is just going to be the derivative of this whole integral and all we're doing is we're taking this inside function t cubed plus 1, and instead of using t, we write x. So this becomes x cubed plus 1. Okay. Now, if we had another function, let's say y is equal to the integral from a to x of secant squared t dt, the derivative dy dx, again, we're just taking the inside function, this secant squared of t, and we're replacing the t with x. So this is secant squared x. That's our answer. Now, if we had another function, let's say c, y is equal to the integral from x to 5 of 3t times sine of t dt. Well, this is slightly different because this is going from x to 5 instead of 5 to x. So, if we're taking the dy dx, and this is really the derivative, d dx, of the integral from x to 5 of 3t sine of t dt. Now what we learned the other day is that this is the same, this integral, if we switch it, so an integral going from a to b of f of x dx is the same as negative integral from b to a of f of x dx. So using this right here, this is going to be negative integral from 5 to x of 3t sine of t dt. And now, using the fundamental theorem of calculus, this is just going to be negative, and we're going to replace all of our t's in here with x's. So negative 3x sine of x. And that's your answer. Okay, so let's add another layer of complex. I'll make this just a little bit more complex. So d. If y is equal to the integral from 1 to x squared of cosine of t dt. What we do here when we take the derivative dy dx, this is going to be dy dx of the integral from 1 to x squared of cosine t dt. But now we're actually going to use a little substitution, okay? Because this is x squared and not x. So let's make the substitution. Let's let u equal x squared. So this becomes the derivative, and sorry, then this is not dy dx, this is just d dx. So what we get here is this is the derivative d dx of the integral from 1 to u of cosine t dt. And if we're trying to use the chain rule says that if we're taking the derivative d dx and we want to change it now that we're dealing with u's, we're going to write this as d du of the integral 1 to u of cosine of t dt times the chain rule, the derivative of u with respect to x. Now, this may look confusing, but really what we're doing here is this first part is the fundamental theorem of calculus. So this is the, using the fundamental theorem of calculus, this is going to be just cosine of u, because u is our new variable, times the derivative of u. And I'll write it as du dx. And sorry, this is u, not t. So cosine of u. And so cosine of u is, u right here is x squared, so this is cosine of x squared times the derivative of u is just 2x. So this is what the answer should be, or 2x times cosine of x squared. So looking back at this, what we had, this is where we started. The fundamental theorem of calculus says that this is going to be, well, looking at here, we still have cosine of whatever that is, cosine of x squared, but now all we did was we add the derivative of x squared, which is 2x. So let's just try one more, and we won't do all those smaller steps. Okay. So let's say we have y is equal to the integral from 4 to 1 plus 3x squared, and let's say of t squared dt. So the derivative dy dx is going to be, so what we're doing using the fundamental theorem of calculus, we replace this with that variable up here. So that's just going to be 1 plus 3x squared quantity squared times the chain rule times the derivative of 1 plus 3x squared. And so we get, this is 1 plus 3x squared quantity squared times the derivative here is 6x. Now we have the second part of the fundamental theorem of calculus. And this says the following. If f is continuous on the interval a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where we define capital F to be any antiderivative of our little f. So that is a function capital F such that capital F prime, the derivative of that, is little f. So the second part of the fundamental theorem of calculus states that the integral of this is really the antiderivative at this point minus the antiderivative at this point. And sometimes, instead of writing f of b minus f of a, we'll use the shorthand notation f of x, and this means we're going to evaluate this f from a to b. And sometimes you'll see it with just a straight line, and that just means f of x is evaluated from a to b. Now let's do some examples. The integral from 0 to pi of cosine of x dx. Well, what is this going to be? Well, the antiderivative of cosine of x is sine of x. Okay. If you remember that, the antiderivative of cosine of x is sine of x, and so this is just going to be sine of x evaluated from 0 to pi, meaning this is going to be sine of pi minus sine of 0, because the fundamental theorem of calculus says the integral from a to b of f of x dx is the antiderivative evaluated at the second endpoint, pi, minus evaluated at the first endpoint. So let's do another example. So let's call this example A, and we'll look at B. So now let's evaluate the integral from negative pi over 4 to 0 of secant of x times tangent of x dx. Now if you remember the antiderivatives, the antiderivative of secant times tangent of x, that's just secant of x. So what we have here is this is going to be secant of x evaluated from negative pi over 4 to 0. And I'm sorry, we didn't really finish this first one because we know what sine of pi is. What's sine of pi? Well, that's 0. And then sine of 0 is also 0. So this is just going to be 0. And so now we evaluated this integral without actually having to compute any areas of rectangles and whatnot. So same thing here. So now this is going to be secant of not secant of x, secant of 0 minus secant of negative pi over 4. Well, secant of 0 is going to be 1 minus secant of negative pi over 4. If you remember from trigonometry, that's just root 2. So we get 1 minus root 2. Now let's do another example. Evaluate the integral from 1 to 4 of the quantity 3/2 times the square root of x minus 4 over x squared dx. So now we need to figure out what's the antiderivative of all of this. Well, let's actually give ourselves a little bit more space so we can work with right here. So what's the antiderivative of 3/2 square root of x, or 3/2 x to the 1/2 power? Well, the antiderivative of that is x to the 3/2. So this is just going to be x to the 3/2 minus, and what's the antiderivative? And this is our little scratch work right here. What's the antiderivative of 4 over x squared? Well, it might be easier if we looked at it as 4 times x to the negative 2 power. And so the antiderivative of this is going to be negative 4 times x to the negative 1. And you can double check this by taking the derivative of this term and seeing that derivative of this term and seeing that it's equal to that one right there. Now another way of writing this is going to be negative 4 over x. X to the negative 1 is really the same as saying dividing by x to the 1 power. So now what we have is we're subtracting right here, subtracting a negative. So really we're going to add 4 over x, and this is evaluated from 1 to 4. So plugging this in, we're first going to go through this evaluating at 4, and then we're going to subtract this evaluating at 1. So evaluated at 4 we get not x, but rather 4 to the 3 halves plus 4 over 4, and then we're going to evaluate it at 1. 1 to the 3 halves plus 4 over 1, oops, 3 halves right there. And so we get, this should be 8 plus 1 minus 1 plus 4. And so this is going to be equal to 4. So now we can use the fundamental theorem of calculus to find a lot of things. If given, let's say, velocity, so if we know that v of t is the velocity of something, and we also know that s of t is the position, and if we're given that the velocity is the derivative of the position, then we could calculate the integral of the velocity from a to b dt. That's really s of b minus s of a. This is done using the fundamental theorem of calculus. And what is this? If we're subtracting our position from this endpoint minus the position of our start point, that's the distance traveled. So if you just need to know what's the distance you traveled, you just take the fundamental theorem of calculus of this antiderivative, or of this integral. We could also use this in applying, say, finding the area under a curve. So find the area under the parabola. This is y is equal to x squared from 0 to 1. So the solution to this is going to be, well, if our f of x is x squared, what's the antiderivative? What would capital F of x be? Well, the antiderivative of x squared is 1/3 x cubed. And so the area is going to be the integral from 0 to 1, because that's where we're going, from 0 to 1, of our function x squared dx. That's the area, and now, using the fundamental theorem of calculus, we're going to say this is the antiderivative, 1/3 x cubed, or x cubed over 3, evaluated from 0 to 1. So this is going to be 1 cubed over 3 minus 0 cubed over 3, which is just 1/3. So let's just combine everything and rewrite the fundamental theorem of calculus. And what the fundamental theorem of calculus states is, suppose f is continuous, on the closed interval a to b, then we're going to have two things. One, if g of x is equal to the integral from a to x of f of t dt, then g prime of x is equal to f of x. And then two, the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. And this is going to be where capital F is any antiderivative of little f, that is, capital F is equal to little f. Today we're going to talk about indefinite integrals and the net change theorem. Now the notation, if you write the integral of f of x dx, this is traditionally used for an antiderivative of f. And what this is called is the indefinite integral. And so if we wrote the indefinite integral, and we said this is equal to capital F of x, this means that the derivative of capital F of x is little f of x. So, for example, the indefinite integral of x squared dx, well, the antiderivative of x squared is x cubed over 3 plus c. And that's because if we took this term on the right, all this stuff, we took the derivative of x cubed over 3 plus c. Well, the derivative of x cubed is 3x squared over 3. And the derivative of c, well, c is a constant, so the derivative of a constant is 0. So this is just x squared, which was that function on the inside. Now let's take a look at this table of indefinite integrals. So the indefinite integral of some constant c times f of x dx is, you can just pull the constant out, and that's just c times the integral of f of x dx. Same thing if we're adding two functions, the indefinite integral of f plus g of x dx becomes the indefinite integral of f of x dx plus the indefinite integral of g of x dx. The indefinite integral of just a constant k times dx is going to be kx plus c. Remember, when we take the indefinite integral, we would be adding an integrating constant c. The indefinite integral of x to the n becomes x to the n plus 1 over n plus 1, again, plus c. The indefinite integral of sine of x, well, the antiderivative of sine is negative cosine, plus c, of course. The indefinite integral of cosine is going to be sine, since the antiderivative of cosine is sine, and then we again add plus c. The indefinite integral of secant squared of x dx becomes tangent of x plus c. The indefinite integral of cosecant squared of x is cotangent plus c. And the indefinite integral of secant of x times tangent of x is secant of x plus c. And then finally, the indefinite integral of cosecant of x times cotangent of x is negative cosecant of x plus c. So let's do some examples. Find the general indefinite integral of 10 x to the 4 minus 2 times secant squared of x dx. So using that table, we have two different things, so we can break it up into two integrals we're subtracting. And then also we have a constant in front, so we can pull these constants in front. This 10 and this 2. So we get, first off, we get 10 times the integral of x to the 4 dx minus 2 times the integral secant squared x dx. So this becomes the integral of x to the 4 dx becomes x to the 5th over 5. And so if we were to add the plus c over here, we'll call it a c1 minus, and then we have 2 times, and then the antiderivative, or the indefinite integral of secant squared of x dx becomes tangent of x plus, and we'll call this a c2. But we have a constant and we have plus another constant, so really what we can just do is just write it as one big constant, because it doesn't really matter as long as it's a constant. So simplifying this, 10 over 5 gives you 2x to the 5th minus 2 tangent of x, and then we just call it plus c. So really, you don't need to add a c1 and a c2 here. We could have just said plus c. Now, if we do another example and we take the integral from 0 to 3 of x cubed minus 6x dx, this is a definite integral, and so we're going to use the fundamental theorem of calculus as well as a table earlier in this video. This equals, and now we have two things, and then we look at each one, x to the 3rd and 6 times x. And so what we get is the x to the 3rd becomes x to the 4th over 4 minus, and then 6x is 6 times, and then x is x squared over 2. And then this is all going to be evaluated from 0 to 3. Okay, so again, we took this and split it up into two things. X to the 3rd becomes x to the 4 plus 4. 6x is 6 times x squared over 2. And we don't have a plus c because it's a definite integral, so we know exactly the values, 3 and 0, the bounds. So this becomes 3 to the 4 over 4 minus 6. Well, 6 over 2 is really, this 6 over 2 really should just be a 3x squared. So minus 3 times 3 squared minus, and then we get 0 to the 4 over 4 minus 3 times 0 squared. And so we're left with is going to be 81 over 4 minus 27, and well, that's just 6.75. Now if we did another example and we were to find the integral from 0 to 12 of x minus 12 times sine of x dx, what we get here is, well, the integral of x gives you x squared over 2, minus 12 times the integral of sine of x. Well, the integral of sine of x is going to be negative cosine of x. And then this is going to be evaluated from 0 to 12. So what we get is the following. We get 12 squared over 2 minus 12 times cosine, or negative cosine, of 12 minus 0 squared over 2 minus 12 times negative cosine of 0. And I guess these minus negatives can cancel and they can just become a plus. Cosine of 0, well, that's just 1. So this becomes 12 squared over 2. We get 72 plus 12 times cosine of 12. And then we get minus, well, that's just 0, that cancels out. And so we get minus 12. And so we're left with 60 plus 12 times cosine of 12. The last thing we're going to do today is something called the net change theorem. And this says that the integral of a rate of change is the net change meaning the integral from a to b of f prime of x dx, and this is f of b minus f of a. And so an example of this might be if we're dealing with the volume in a tank with respect to some time t, and we say that Vt is the volume coming in, or is the rate that water moves in, water flows in, then the change in amount of water in the tank is going to be the integral from some time 1 to time 2 of the derivative of v of t dt, and that's really just v of t1 minus v of t2. And this works for a bunch of different things. For example, if we have velocity versus position, the change in position, s of t2 minus s of t1 is just the integral of the velocity. Today we're going to talk about the substitution rule. Now, because of the fundamental theorem of calculus, it's important to know the antiderivatives. But sometimes the antiderivatives we don't really know. For example, if we have the integral of 2x times the square root of 1 plus x squared dx, what's the antiderivative of this? Well, we don't know that antiderivative just yet, but we can look at this, and look at this 2x and then the square root of 1 plus x squared, and we can make a little substitution. What if we introduce this new variable, u, and let u be what's inside the square root, 1 plus x squared? Well, what's the derivative of u? Du is going to be 2x times dx. And so this original integral, if I move it down here, that if I rearranged it and I move this 2x after the square root, we get the integral of the square root of 1 plus x squared times 2x dx. And now we can make some substitutions. So this is the integral, the square root of 1 plus x squared. Well, we know 1 plus x squared from right here is going to be u. And then 2x dx right here is du. So this becomes the square root of u times du. Or if you prefer as an exponent, u to the 1/2 du. And now we know what this antiderivative is. The antiderivative of this is 2/3 u to the 3/2 plus c. But remember u, we made that substitution, we defined u to be 1 plus x squared. So really, putting it back into x, because our original, actually I'll just write it up here, so this is going to be 2/3, u was 1 plus x squared raised to the 3/2 plus c. That is our answer. So this method that we did right here is using substitution. So we have something called the substitution rule. And this says that if u is equal to some g of x is a differentiable function whose range is an interval we'll say this interval, call it I, and f is continuous on I, then the integral of f of g of x times g prime of x dx is equal to the integral of f of u du. So basically what this is saying is that if we're taking the integral of some function f that of some variable times the derivative of that, that could be written as the integral of f of u du. So instead of writing it as g of x, we're writing it as u. And this all becomes that. So let's do an example. Let's evaluate the integral of x squared times cosine of x cubed dx. If we rewrote this and we moved these x squared after the cosine, so this would be the integral of cosine of x cubed times x squared dx. Now, this x cubed inside the cosine, that might be cause a little problems. So that's probably what we're going to want to let our u equal. So let u be x cubed. That means that du is going to be 3 times x squared times dx. And so making the substitution, we get the integral of cosine instead of x cubed. We're going to use u, but now we run into a problem. This is x squared dx, and this is not quite x squared dx. It's 3 times x squared dx. Well, how do we make it like x squared dx? we can divide both sides by 3. And so 1/3 du is equal to x squared dx. So this is going to be multiplied by 1/3 du. So to evaluate this 1/3, we can pull it in front. And so this is 1/3 the integral of cosine of u du. And we know this. So we get 1/3 times sine of u, the antiderivative of cosine is sine, and then we add plus c. But we're not done. Because the initial problem had x's in it, we cannot leave our answer with u. We have to always write back or convert back. So this is going to be 1/3 sine, our u was x cubed, plus c. That's our answer. Now let's do another example. Let's evaluate the integral, the square root of 2x plus 1 dx. So here, we look inside the square root, and because it has more than just x, we're going to have a problem. So that's what we're going to let our substitution be. Let u equal 2x plus 1. And then our derivative, du, the derivative of 2x plus 1 is just 2 times dx. Because the derivative of 2x is just 2. Derivative of 1 is 0. So it's just 2 and then times dx. So going ahead, making the substitution, this is the integral of the square root of u, but again, we only have just dx. So to get just dx, we divide both sides by 2. And so dx is just 1/2 du. So times 1/2 du. So we get 1/2 times the integral of square root of u, or rather u to the 1/2 du. I'm going to write it as an exponent. And so the antiderivative, or the integral of u to the 1/2 du, is going to be 2/3 u to the 3/2 plus c. And so this becomes 1/3 u to the 3/2 plus c, and u, we said, was 2x plus 1. So this is 1/3 times 2x plus 1, all raised to the 3/2 plus c. That's your answer. Now let's do another example, but very similar. Evaluate the integral of x times the square root of 2x plus 1 dx. So this is similar to the last problem, except now we have an x in front. So we'll make this the substitution. U is equal to 2x plus 1, just like we did before, and du is going to be 2 dx, which means that our dx is really 1/2 du. So this becomes the integral of, well, I'll leave that x for now, the square root of u times 1/2 du. So we're stuck with this x. What can we do with this x? Well, take a look at what we said over here. U is 2x minus 1. So if we rearrange that term, so if we rearrange this, we could solve for x. And so if we subtracted 1 from both sides, we could get u minus 1 is 2x, or if we divide by 2, we get x is u minus 1 over 2. So making that substitution, we now get the integral, and rather than having it u minus 1 over 2, I'll write it as 1/2 times u minus 1. Okay, so we get 1/2 u minus 1, square root of u is u to the 1/2, and then times 1/2 du. We have 1/2 and 1/2. We can pull that in front, so we'll get 1/4 times the integral. And I'm going to go ahead and just distribute this. U times u to the 1/2 becomes u to the 3/2 minus 1 times u to the 1/2 is just u to the 1/2, and then times du. So this is something that we'll be able to solve. So this is going to be 1/4 times the antiderivative of u to the 3/2. Well, that's going to be 2/5 u to the 5/2 minus 2/3 u to the 3/2 plus c. And again, we know that u was 2x plus 1, so this is going to be 1/4 times the quantity 2/5 times 2x plus 1 to the 5/2 minus 2/3 times 2x plus 1 to the 3/2 plus c. Now let's do an example. Evaluate the integral of cosine of 5x dx. So we let u equal 5x, then du is going to be 5 dx. So this is going to be the integral of cosine of u times, and so if we just have a dx, then we can write dx is going to be 1/5 du. So times 1/5 du. So we have 1/5 the integral cosine of u du, which is 1/5. The integral of cosine of u du is just sine of u plus c. And so substituting u is equal to 5x, this is 1/5 sine of 5x plus c. Let's do another example. Evaluate the integral of the square root of 1 plus x squared all times x to the 5th dx. So we make u equal 1 plus x squared, then du is 2x dx. And so we get, this is the integral of the square root of u, and now we have x to the 5th dx. Well, going back to this du, if we divide both sides by u, or by 2, we get 1/2 du is x dx, and so x to the 5th can be rewritten as x to the 4 times x dx. X to the 4 times x is x to the 5th, and so we get the integral of the square root of u times x to the 4, x dx is 1/2 du, but we're still left with x to the 4. But remember that we let u be 1 plus x squared. So x squared is going to be u minus 1. We just moved 1 to the other side. If x squared is u minus 1, x to the 4 is x squared squared. So u minus 1 quantity squared is x to the 4. And so now this is going to be, and I'm going to rewrite the square root of u as u to the 1/2. So this is u to the 1/2 times u minus 1 squared times 1/2 du. We can pull that 1/2 in front. We get the integral of u to the 1/2. I'm going to expand. U minus 1 squared is u squared minus 2u plus 1 du. This becomes u to the 1/2 times 2 is going to be u to the 5/2 minus 2 u to the 1/2 times u is u to the 3/2 plus u to the 1/2 du. And so now we can actually start taking the antiderivative or integrating. So this is 1/2 times, this is going to be 2/7 u to the 7/2 minus 2 times 2/5 u to the 5/2 plus 2/3 u to the 3/2 all plus c. And so writing this out, remember u was up here. I've got to go back up a little bit. U is 1 plus x squared. So this is going to be equal to 1/2 times 2/7 is going to be, well, in fact, this 1/2 will cancel that 2, cancels this 2, and it cancels this 2. So that'd be 1/7. This next term would be 2/5, and this would just be 1/3. So we get 1/7. Oops, not u, we're substituting. And so we said u is equal to 1 plus x squared. So 1 plus x squared raised to the 7/2 minus 2/5, 1 plus x squared raised to the 5/2 plus 1/3, 1 plus x squared raised to the 3/2 and plus c. Now we have the substitution rule for the definite integrals, and this says the following. If g prime is continuous on a to b, and f is continuous on the range of u equaling g of x, then the integral from a to b of f of g of x times g prime of x dx is equal to the integral, and now here's where we're going to make a change. If we're going to be changing from to u, our bounds from a to b also have to change. So our a, instead of going from a, it's going to go from g of a. Instead of going to b, it goes to g of b. And then we have f of u du. So we'll do an example. Evaluate the integral from 0 to 4 of the square root of 2x plus 1 dx. So we're going to make the substitution. We're going to let u equal 2x plus 1, and du is equal to 2 dx And then now, when we had initially that x was going from 0 and x went to 4, what we're going to do is we're going to plug in those values into our u. So if it went from 0, the new value is going to go 2 times 0 plus 1, which is equal to 1. And then it would go to 2 times 4 plus 1, which would be 9. So instead of going from 0 to 4, if it goes from 0 to 4, it'll go from 1 to 9. So now we have, this is the integral from 1 to 9 of the square root of u, and then dx, well, we knew from the other video, du equals 2x. That means that dx is 1/2 du. So here we have 1/2 the integral from 1 to 9 of u to the 1/2 du. And so this becomes 1/2 times the antiderivative of u to the 1/2 is 2/3 u to the 3/2 evaluated from 1 to 9. Our 1/2 and 2 cancel, so this is 1/3 u to the 3/2 evaluated from 1 to 9, which becomes 1/3 9 to the 3/2 minus 1 to the 3/2. So this is 1/3 9 to the 3/2 is going to be 27 minus 1, and so this is 26 over 3. So this is one way of solving these definite integrals, and some of you may find this confusing, having to change from 0 to 4 to 1 to 9. There is an alternate way of solving this. So the way I'm going to solve this is going to be the following. We have the integral from 0 to 4 of the square root of 2x plus 1 dx, and then we made the substitution for u. So this is the integral of the square root of u times 1/2 du. Now, notice I'm not putting our bounds in. Okay, and this is the same substitution we had before, where u was 2x plus 1, and then du is 2 dx. So that's the same substitution we did before. And now, so this is the integral of u to the 1/2, and actually I can bring it 1/2 integral u to the 1/2 du, which is 1/2 times 2/3 u to the 3/2 right here. And we're supposed to evaluate it from something to something. And we didn't make that change, but this is because we're dealing with u. Now, if we, instead of dealing with u, we converted back to x, so we have, this is 1/3, instead of u to the 3/2, we have 2x plus 1 to the 3/2. We can evaluate it back to our original thing, which was 0 to 4. Our original value was 0 to 4. So we don't have to convert it like how we did before from 1 to 9. We can leave it. And so now this becomes 1/3 times 2 times 4 is 8. Well, 2 times 4 plus 1 raised to the 3/2 minus 1/3 times 2 times 0 plus 1 raised to the 3/2. And this is going to be 1/3 9 to the 3/2 minus 1/3 times 1 to the 3/2. And so this should give us 9 to the 3/2 is going to be 27 times 1/3. So 27 over 3 minus 1/3, which is 26 over 3. And that's exactly the same answer we got from up here. You can see 26 over 3. So there are two different ways of doing it. This first way, we had to convert from 0 to 4 to 1 to 9. And we just made that substitution by plugging in for u. The second way of doing this is instead of having to change your variables, we just went back. So instead of changing the limits of integration, we went back and writing it instead of u, we put it back in terms of x, and then we could keep our original limits of integration. So now let's do another example with a definite integral. Let's evaluate the integral from 1 to 2 of dx over 3 minus 5x squared. Well, we're probably going to want to let u equal 3 minus 5x. And that means that du is going to be negative 5 dx. And so this becomes the integral of, well, dx should be negative 1/5 du. So this should be negative 1/5 du divided by the square root, not the square root, the square of u, so u squared. And now our limits of integration, if we started off where x was 1, our new limit would be 3 minus 5 times 1, which is 3 minus 5, or negative 2. So we're going to be at negative 2. And then if x was 2, so we're going from 1 to 2, the u would become 3 minus 5 times 2, which is going to be negative 7. So we're going to have the integral from negative 2 to negative 7 of negative 1/5 du over u squared. So it doesn't really look too pretty the way it is. So let's pull out the negative 1/5. Negative 1/5 integral from negative 2 to negative 7, and dividing by u squared, let's write it as u to the negative 2 du. Now this looks a little cleaner. This becomes negative 1/5. The integral of u to the negative 2 is going to be negative 1, well, negative u to the negative 1. And then we're going to evaluate that from negative 2 to negative 7. So we have, this is going to be negative, well, negative will cancel. So this is going to be just positive 1/5 of negative 7 to the negative 1 minus 1/5 of negative 2 to the negative 1. So here we have 1/5 times negative 1 over 7, and then plus, because again another negative, 1/5 times 1 over 2. They both have a 1/5, so we'll factor out 1/5. Then we have negative 1/7 plus 1/2. So we get 1/5 times, the common denominator would be 14. So this would be 2 over 14 plus 7 over 14. Negative 2 over 14 plus 7 over 14 gives us 5 over 14. So we get 1/5 times 5 over 14, our 5's cancel, and we finally end up with our answer, 1 over 14. Now, recall what it means if a function is even. So you might recall from algebra or pre-calculus that an even function is something that's symmetric about the y-axis. So it might be something that looks like something like that, and pretend that's symmetric, but or even, let's just say, a simple parabola that's going to be symmetric about the axis. A function that's odd is something that might look like this. And remember, we can graph an odd function by taking one of these quadrants, reflecting it over the x-axis, and then reflecting it again over the y-axis to get that. Now, the definition for something to be even versus odd is that if we plug in negative x into our function f of x, it comes out to just being the same thing. And it's odd if we plugged in negative x and we ended up with negative of our function. So this is what it means to be odd and even. In the context of integration, this becomes useful if you're integrating an even function, and instead of going from, say, like negative this part to this part, you only need to calculate half of this, half of that, and then multiply it by 2. And then for an odd function, if we're calculating something and the width is even, or it's like negative one value to another, the area under here is going to be positive, but then you go down here, that area would be negative, and it cancels out. And that's only for evaluating from the exact same value. So from like negative 2 to positive 2, or negative 10 to positive 10. So let's actually write this up formally. So integrals of symmetric functions, and this would say the following. Suppose f is continuous on the interval negative a to a. And then, first thing, if f is even, then we have the integral from negative a to a of f of x dx. This is just twice the integral from 0 to a of f of x dx. An even function, so we only need to do half of it and then multiply it by 2. And if f is odd, then we have the integral from negative a to a of f of x dx, that is equal to 0. And just the reminder of what it means to be even, that means f of negative x, f of negative x is f of x, and what it means to be odd is f of negative x equals negative f of x. So an example is, since the function f of x equals x to the 6 is even, and we can test that contested, so f of negative x is going to be negative x to the 6, which is just x to the 6, which is f of x. So since this is even, we have that the integral from negative 2 to 2 of x to the 6 dx is going to be twice the integral from 0 to 2 of x to the 6 dx, which is going to be twice the antiderivative of x to the 6, or the integral of x to the 6 dx, becomes 1 over 7 x to the 7th evaluated from 0 to 2. And so this is going to be 256 over 7 minus 0, so it's just 256 over 7. And then another example. Since f of x is equal to tangent of x divided by 1 plus x squared plus x to the 4, this is going to be odd. And why is it odd? Well, f of negative x is going to be tangent of negative x divided by 1 plus negative x quantity squared plus negative x quantity to the 4. Now tangent, we know, is already odd. If you recall from the graph of a tangent, tangent looks like that. In fact, it repeats on and on. But now, since tangent is odd, then what we have is this is equal to negative tangent of x divided by 1 plus x squared plus x to the 4, and this is negative of this whole thing. So this is just negative f of x. So now we know it's odd. So we have that the integral from negative 1 to 1 of tangent of x divided by 1 plus x squared plus x to the 4 dx, because it's an odd function, this integral is just 0. Today we're going to talk about the areas between curves. So let's say we have a curve that might look like this. We'll call this curve f. This is our function f of x. And let's say we have another curve that lies below the axis, and that's our curve g. Now to find the area under the curve, let's say from some point A to B, the area under f, this area, we already know how to find that. And if we do approximations, we can approximate by using rectangles, or when we take the limit as it goes to infinity, we can use integration. Same thing if it lies below the axis down here, we can use a bunch of rectangles, and when it's below the axis, the area is going to be negative, or we can also use integration. So finding the total area between these two regions, we really want to find the difference. We want to find this area above, and remember, if this is below, it's going to be negative. So we want to add these two, and so if we're adding a positive number and a negative number, really what we're finding is f minus g. So the formula for the area will be given by the following. So area is equal to, let me make this a little bit bigger font. Area is equal to the limit as n goes to infinity of the sum, where I goes from 1 to n, of the difference of f of x sub I star minus g of x sub I star, all times our delta x. Delta x. There we go. Okay, so this looks familiar. If we didn't have this minus g, but this looks familiar, the limit of the sum of f of x sub I star times delta x. Now, so this is one equation for the area, and another equation is going to be given with the following. The area, we'll call this A, of the region bounded by the curves y equals f of x and y is equal to g of x, and the lines x equals a and x equals b. So we're going to be between this curve and this curve down here, and between the vertical line and this vertical line. This is going to be where f and g are continuous, and we're going to have to assume that the f of x function is going to be the top function. So that's going to be greater than or equal to g of x. So in this case, order matters. The top number has to be greater than the bottom number. So f of x is greater than g of x. And this is going to be for all x in the interval from a to b. So this is given by the formula a equals the integral from a to b of f of x minus g of x times dx. So this is what we're going to use. And it doesn't have to always be above or below, but you might have your two functions. Let's say this is the function f, and the function g looks like this. F and g are both going to be above the axis. If we're going from a to b, this is the area underneath, and you can find that area using this formula. Now let's do an example. Find the area bounded by the two curves. Let's just call it, say, between the two curves y equals 2 minus x squared, and that's a parabola, and the line y equals negative x. So here I didn't give you what function to go from where to where, so we actually have to figure that out. So let's go ahead and plot what we have. This first function is going to be a parabola, and it's a parabola that goes up here at 2, and it's facing downwards. So something like that. Then we have a straight line with a negative slope of -1. And so we have that, and it crosses at the origin. So we want to find the area between these two curves, which is going to be this region right here. So this is going to tell us that this top curve, that's going to be the function we'll call f. So that's the parabola. So our f is going to be 2 minus x squared. And then this straight line is going to be our g function, and that's going to be negative x. So now we know our curve, which one is going to be f and which one is g, but we still don't know the regions. But we can figure that out. So when are these two functions equal to each other? So you get 2 minus x squared equals negative x. You set them equal to each other and you can solve. I'm going to move everything to the right side. So if I add x squared, and then I also subtract 2 and subtract 2, we get zeros on the left, x squared minus x minus 2, and we can now factor x minus 2 times x plus 1. And so we get x is equal to negative 1 and x is equal to 2. And so that's the points, negative 1 and 2. So the area is going to be the integral from negative 1 to 2 of your f function, your top function, which is 2 minus x squared, minus your bottom function, which is negative x. So the integral of 2 minus x squared minus negative x. And this is going to be all times dx. So now we can solve this definite integral. This is going to be the integral from negative 1 to 2 of, let's say, 2 minus x squared, and minus a negative x gives you plus x in all dx. So go ahead and finding the integral of this, the antiderivative of 2 is just 2x. The antiderivative of x squared is 1/3 x cubed, and the antiderivative of x is 1/2 x squared. And we're going to evaluate it from negative 1 to 2. So we get, evaluating at 2, we get 2 times 2 minus 1/3 times 2 cubed plus 1/2 times 2 squared minus 2 times negative 1 minus 1/3 times negative 1 cubed plus 1/2 times negative 1 squared. So we get 4 minus 8/3, and then 1/2 times 2 squared, so 1/2 times 4, or just plus 2, and then we get minus a negative, so we get, oh, we'll just do this. So 2 times negative 1, negative 2, and then negative 1 cubed is still negative 1, but minus 1/2 becomes plus 1/2, and then plus another 1/2. So we get 6 minus 8/3, and in fact, this should have been a 3. So sorry about that. That should be a 3. So 6 minus 8/3, because I combined those to make 6, and then we're going to subtract, and then we'll have negative 2 plus 1/3 plus 1/2, 5/6. And so we get, there's going to be 6 minus 8/3. In fact, instead of writing 8/3, I'm going to write 16/6. I just multiplied it by 2/2, so we can have a common denominator. Plus 2 minus 5/6. So now our 6 plus 2 will give us 8, minus, we get 21/6. And that 21/6, they both have a 3 in it, so we can reduce, and that becomes 7/2. And if we want to combine that into just a single fraction, it would be 9/2. So that's the area between the two curves. We'll do another example. Find the area bounded between the two curves
y equals the square root of x, and y is equal to x minus 2. So again, we're not really given much here, so we're going to have to figure out what this region looks like. So the first graph, y equals the square root of x, looks something like this. This is y is equal to the square root of x. And then the straight line, y is equal to x minus 2. That's going to be a straight line at negative 2 with a slope, maybe something like that. And just for sake, let's also add another stipulation, and this region will also be bounded below by the x-axis. So now we're not going to look at this part below, we're going to be restricted by the x-axis, this line, and then the y equals square root of x. And so this right here was y is equal to x minus 2. So this problem is a little different from the other one because we're actually going to break this up into two separate pieces. The first piece is going to be right here, and this is going to be between two curves. We're going to be between this upper curve and this lower curve. Then the other piece is just going to be this little piece right here, and this is bounded above by the square root of x. And that's it. When you just take the integral of the square root, or just the integral, it's the area below that curve and above the axis. So all we need to do is figure out what are these points? Where does it cross? Well, the graph y equals negative, or x minus 2, excuse me, it crosses the axis right here when x is equal to 2. So we know that point, but then to find this other point, that's when we're going to have x minus 2 equals the square root of x. So we need to figure out when they're going to be equal. Well, we have a square root of x, that's really not something we like, so let's actually square both sides. So we get x squared minus 4x plus 4 equals x. Moving x to the other side, we get x squared minus 5x plus 4 equals 0, or x minus 4 times x minus 1 equals 0. And so we're going to get two values. We're going to get x is equal to 1, or x is equal to 4. This value, x equals 1, is an extra root that comes out when we end up squaring it. And you can just look at the graph. 1 does not work. So we ignore that, and then we look at this point. So this is going to be right there. For the green region, we're going to have an integral between the 2 points, 2 and 4. And then for the blue region, we'll have just an integral from 0 to 2. All right, so area for the blue is just the area under the curve. So that's the integral from 0 to 2 of the square root of x dx, or the integral from 0 to 2 of x to the 1/2 dx, which is 2/3 x to the 3/2 evaluated from 0 to 2. This comes up to just being 2/3 times 2 to the 3/2 minus 2/3 times 0 to the 3/2, or 2/3 times 8. The green region, our area is going to be the integral from 2 to 4 of the top function, which is the square root of x, minus the bottom function, which is x minus 2 dx. And so we're going to go ahead and we'll rewrite this. This is an integral from 2 to 4 of x to the 1/2 minus x plus 2 dx, which is going to be 2/3 x to the 3/2 minus 1/2 x squared plus 2x evaluated from 2 to 4. And so we get 2/3 times 4 to the 3/2 minus 1/2 times 4 squared plus 2 times 4 subtracted by 2/3 times 2 to the 3/2 minus 1/2 times 2 squared plus 2 times 2. And then if we were to go ahead and simplify this, I'll tell you right now that that is equal to -2. So the total area is going to be the area plus blue, or of the blue, plus the area of the green. So our total area between the two curves is going to be 16/3 plus -2, which is 10/3. That is the area between the two curves. Right here. So now we know how to find the area between two curves when you have one curve f and that's above another curve g. But now, what if we have, say, our curve f looks like this, if we're going between 2 points, say A and B, and we had a curve G that starts off below and then it goes above and then maybe even below again. So if we're going between A and B, we're going to have a couple of different regions. We have this region where where f is above, so we call it, that's our g function, and another region where f is above, but in this region down here where g is above. So how do we really do something like this when it switches? So in this case, we knew what happened when f was above g, but when they alternate, what we're going to do is the following. Just simply break it up into different pieces. We'll have this one red piece right here, and maybe I'll make this other one over here red as well, and then we'll make this one blue. Okay. And then you just figure out where these points are, and you do you figure out where each of these intersections are, and you just calculate 3 separate integrals. Each integral, you're going to make sure you got to figure out the top function versus the bottom function, the top function versus the bottom, and so forth. Now, we might also have some sort of curve that's, instead of y equaling a function of x, we'll have the other way around. X is a function of y. So what that might look like would be, we might have something like this, and then this would be the curve. X is equal to g of x, x is equal to g of y, and maybe something that looks like this, and this is going to be x is f of y. These are functions in terms of y, and if we want to find the area between these two curves, let's say between some point C and some point D, so we want to find this area, we're going to integrate. So area would be the integral from C to D, but instead of it being a function of x, it would be a function of y. F of y minus g of y dy. And so we'll do an example to illustrate why this might be useful. Find the area enclosed by the line y is equal to x minus 1, and the parabola y squared is equal to 2x plus 6. What does this look like? Well, we have a parabola, y squared equals 2x plus 6. That's a parabola that opens to the right. Something like this. And then y equals x minus 1, that's a line that goes something like that. So now to find the area in between here, what we'd have to do would be to figure out these points of intersections. So we're going to have this equation y squared equals 2x plus 6, and then using the first equation that said y is equal to x minus 1, solving for x, we get x is y plus 1. We'll substitute, so we get y squared is 2 times y plus 1 plus 6, or y squared is 2y plus 2 plus 6, so 2y plus 8, or y squared minus 2y minus 8 equals 0. Then you get y minus 4, and y plus 2 equals 0, and so we know that it goes from down here, where y is negative 2. So we get our answer is y is negative 2, and y is 4. All the way up to up here, where y is 4. So now, to find this area, we're going to get that the area is equal to the integral where y goes from negative 2 to 4 of our upper function. So now, looking here, we need to figure out what's the upper function. So if you can sort of like tilt your head sideways, this is the y-axis. So the upper function goes out this way, so this is our upper function, and then this is our lower function. So it's just like how we did with a regular function, but just sideways. So we get our upper function is the straight line, and the equation for the straight line is going to be, well, it's what we need to do, because remember we were writing it as x is like a function of y, and then x was like a function g of y. So what we need to do is we need to write them in terms of x of just y's. So actually I'm going to move up a little bit more so we could see the initial equations. We had them right here. So I had written this first one, the straight line, but the parabola, that needs to be rewritten. Let's move that over here. So we want to just solve it for x. So we're going to get 2x is equal to y squared minus 6. I move 6 over. And then if I divide everything by 2, we get x is equal to 1/2 y squared minus 3. That's what we're going to substitute back into here. So a is going to be, well, the straight line comes first. So the straight line is going to be y plus 1 minus the parabola, which is 1/2 y squared minus 3 times dy. Giving myself a little bit more room, go ahead, and this is going to be the integral from negative 2 to 4 of y, and then can combine the 1 and 3 minus the negative 3, so that would give us plus 4 minus 1/2 y squared all times dy. And so now, integrating, we get 1/2 y squared plus 4y minus 1/6 y cubed, evaluated from negative 2 to 4. Plugging in the limits of integration, we get 1/2 times 4 squared plus 4 times 4 minus 1/6 times 4 cubed minus 1/2 times negative 2 squared plus 4 times negative 2 minus 1/6 times negative 2 cubed. Simplifying this, we end up with 18, and that's the area. Today we're going to talk about volumes. Now we already know how to find the area between two curves. Let's say we have a curve like this, and we have another curve like that. So this first curve, we'll call that f, The second curve, we'll call it G. So we can find this area between those two curves by calculating the integral of f minus g between those 2 points. But now, what about if we had something, we'll start off the shape like this, a cylinder. How would you find the volume of the cylinder? Well, the volume of the cylinder is just going to be base times height, just like the volume of a box. You take volume, if this is your height, and the cylinder has a radius r, the volume is going to be the base, pi r squared, times your height. And so we can do that even if we don't have a circle as a base. You could have some kind of weird shape like this. We can figure that out. We can figure out that volume. In fact, let's say we had some sort of volume that kind of got bigger like this, and like bigger like that, and cut one end like this, and then the end is circular-ish, but maybe not necessarily quite a circle. A little bit off, but because it doesn't have to be an exact circle. Well, what we can do is we keep taking slices across. So we'll sort of like slice it with a little plane. And when we slice it across, we'll see there's a cross section, and that would be what our base is. And so we just go through this. And so we'll have the following definition of the volume based off of this. So definition of the volume. We'll say let S be, and this is a capital S, so let capital S be a solid, so not something that's hollow, but solid that lies between x equals a and x equals b. If the cross-section, the cross-sectional area of S in the plane, we'll say p sub x, so in the plane of the x direction. So this means it goes through x and perpendicular to the x-axis is a of x, where a is a continuous function. So if we have this, then the volume of S is the following. We have V is equal to, and so just like before, we'd have the limit as n goes to infinity of the sum, where I goes from 1 to n, of a of x sub I star times delta x, which is equal to the integral from a to b of your cross-sectional area, a of x dx. So basically what we're doing, each of these a of x is like a slice. That's the area of a slice. And so we're going to add up all these areas of the slices. And so whereas before, when we found the area under a curve, and we added up all these straight lines because we started off with, the area of a rectangle, and as it got smaller and smaller, we got these areas like this. Same thing, let's just say if it was like a cylinder, maybe just something getting bigger, we add up one slice, we'll add up another slice, another, and so adding up all these slices, that's what we have. So now let's do an example. We're actually going to prove right now that the volume of a sphere is equal to 4/3 pi r cubed. You might remember this formula before, but now we're going to show how we got this formula. So if you look at a sphere, we have, so this is a three-dimensional axes. We have x, y, and then this would be z. The sphere, well, comes up like that. But then if we looked at each little cross section, what we have is we have circles, 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 and so forth. And so the equation of each of these circles is x squared plus y squared is equal to r squared. If we rearrange this, solving for y, we have y is equal to the square root of r squared minus x squared. So we're really looking at one of these circles right here, and then if these were our axes, so that was the x one, and that was the y one. If we want to find the area of this circle, well, we know area is pi r squared. So just by looking at this right here, the radius is this length, y. So your radius is really equal to y, which is the y that we're writing up here. So the area, a of x, is pi times y squared, or a of x is going to be pi times the square root of r minus x squared squared. So the square root squared just gives you r squared minus x squared. And now we have a function just in terms of x. Okay, so now we're looking at here, and remember this big sphere had a radius of r, so it went from negative r to positive r, went down here from negative r to positive r, and even on this axis, negative r to positive r. So if we're computing the volume is equal to the integral, and since we're dealing with x, because our function is going to be in terms of x, it's going to be the integral of a of x dx. Now what values did x go from? X went from negative r to positive r. So we're going to be integrating throughout all of that. So making the substitution for a of x, we get the integral from negative r to positive r of pi times r squared minus x squared times dx. And so integrating, what we get, since pi is a constant, we can pull that in front, so that'll be pi times the integral from negative r to r of the quantity r squared minus x squared dx. Now you may notice this function right here is even. And if you did notice that, then we can use the property that this, since we're going from negative r to r, it's just going to be twice the integral from 0 to r of r squared minus x squared dx. If you didn't notice that, you can still integrate it normally, but sometimes integrating with 0 as one of the limits can be a little easier. So integrating, we get this is going to be 2 pi times the antiderivative of r squared is x times r squared, and the antiderivative of x squared is 1/3 x cubed, and we're going to go from 0 to r. So we get this is 2 pi times, when we evaluate it at r, it's going to be x times r squared, or r times r squared gives you r cubed, minus 1/3 r cubed, and then when we put 0 in, it'll be 0 minus 0. So this is going to be 2 pi times r cubed minus 1/3 r cubed gives you 2/3 r cubed, and so this finally gives you 4/3 pi r cubed. And this is the formula that we know for the volume of a sphere. Now let's do another example. Say we want to find the volume created, or that's bounded by the lines y equals x cubed, y equals 8, and x equals 0, and then we're going to revolve this, or rotate it, about the y-axis. Okay, so first of all, let's draw what this figure looks like. So we have y equals x cubed. That's a cubic function, something like that. We have y equals 8. So we have something like this. And then we have x equals 0, which is that right there. So we have this right here, and then think about rotating it about. So we'll have something like that, bunch of circles, rotate it about, and the object looks something like this. So each of these circles that we're going to have, each of these circles has its own radius. And if this is the line y equals x cubed, the radius here, each of these radiuses are going to be the x value. So from this equation above, y equals x cubed, we can get that x is equal to y to the 1/3 power, or the cube root of y. So now we're dealing with something in terms of y. So our area, our cross-sectional area is going to be a of y, and we know that's going to be pi times the radius squared, or pi times x squared, or pi times, since we know x is from here, y to the 1/3, this is going to be y to the 1/3 squared, or pi times y to the 2/3. So that's the formula for a of y. Therefore, we get for our volume is going to be the integral from, well, what we're going to have it a of y times dy. So the limits of integration, your y goes from 0 all the way up to 8. So we're taking the integral from 0 to 8. Therefore, substituting our a in, we get volume is the integral from 0 to 8 of pi times y to the 2/3 dy. And now we can integrate this. We get y times the pi times the antiderivative of y to the 2/3, which is going to be 3/5 y to the 5/3 evaluated from 0 to 8. So we get 3 pi over 5 times 8 to the 5/3 minus 0 to the 5/3. And 0 to the 5/3 is just 0. Last step, what is 8 to the 5/3? Well, this is really 8 to the 1/3 to the 5th. So 8 to the 1/3 is going to be 2. 2 to the 5th So we have that's 32. And so therefore this is equal to 3 pi over 5 times 32, or 96 pi over 5.